and the speaker. Then we will hand over to the chair, and then we can start your program. And yeah, we have one speaker less. I think he is not here. So you can, if you want, you can have another 5 to 10 minutes. Is also possible. That depends.
Okay.
Yeah. So yeah, Dr. Midhan will introduce.
Okay. Welcome to day 2 of INTROMET 2021. So we are going to have the second plenary session of this conference. So this session will be chaired by Professor A. Jayaraman and Dr. Radhika Ramachandran. Professor Jayaraman is the former director of National Atmospheric Research Laboratory, Gadangi. Currently, he is an honorable distinguished faculty for research at IARSC, Bangalore. He has made fundamental contribution to atmospheric aerosol and their role in atmospheric radiation budget and radiative forcing of climate. Also, he is one of the lead author of IPCC's Climate Change Assessment Report. Dr. Radhika is the former director of Space Science Laboratory, Vikram Sarabhai Space Center, Trivandrum. She holds immense research experience in atmospheric and oceanic boundary layer, regional and mesoscale numerical weather prediction, climate change science and policy, and terrestrial CO2 emissions. In this session, we will have 2 plenary talks, one by Professor Brian Mapes. He's a professor in Department of Atmospheric Science at University of Miami. Mapes is an expert. Dr. Mapes is an expert on atmospheric dynamics and thermodynamics, especially interactions between cloudy convection and large-scale weather patterns. The second speaker is Dr. Andrew Turner. He's a professor in monsoon system in the Department of Meteorology, University of Reading, UK. Dr. Turner's general interests are in monsoon variability, predictability, and prediction, including interaction between monsoon system and other elements of climate system. So in this session will be chaired by A. Jayaraman and Dr. Radhika Ramachandran. So the selected questions from chat box will be conveyed or read out to the chairs by reporters. So now may I request honorable chairs to kindly take over the session. Thank you.
Thank you, and good morning all of you. So let us welcome you all to the second day of the INTROMET 2021 conference being arranged at the Cochin University of Science and Technology on topic changing climate, consequences and challenges. So today's proceeding, we are starting with a plenary session as usual, and myself, Achyutan Jayaraman, and my colleague, Dr. Radhika Ramachandran, are co-chairing this session. As we have been already informed by the organizer that Commander M.K. Singh from Indian Navy will not be participating in this session due to his other unavoidable commitments. So we have 2 talks as informed. The first from Professor Brian Mapes from University of Miami, USA, followed by Professor Andrew Turner from University of Reading, United Kingdom. So this will be have additional time which can be utilized for taking up more questions and discussions. So may I now request Professor Brian Mapes to deliver his plenary talk on convection thresholds and climate reasoning in the Western Indian Ocean. Professor Mapes, please.
Okay, great. Thank you very much. Thank you for the invitation, the opportunity. It's quite exotic to be speaking across the world like this. Let's see, are you able to see my PowerPoint? Can you see that?
Yes, we can see that. We can see your presentation.
Okay, now I go to full screen. Can you see it?
Yeah, it's now in full screen, yes.
When I change slide, do you see it?
Yes, of course, we see you.
Okay, great. All right. Well, thank you very much.
So we are set.
Yeah, I want to begin, of course, just with gratitude. You know, a chance to wear my long corto, even though I didn't get to fly around the world to join you all. and much gratitude to really what entrained me into the monsoon, which was the monsoon mission. And, you know, of course, IITM and the ministry, and I know less about IMD, but I'm grateful for the chance to get entrained into monsoon work. And especially they sent along Abi as a visitor, Dr. Abhilash. And we had a lovely time that summer, hiking in the mountains and cooking for my lovely wife. And anyway, it really turned into perhaps a long-time collaboration here. So let's see, here's my outline for today. I want to talk to you about a motivating thing, which is really Abi's work, which is the query: are there long-term trends in the convective character of rainfall for India? And you know, that might be an impactful question. And as part of that, I guess we need to talk about this business of how convection is kind of a threshold process. Usually people think in terms of the surface having threshold values, and that's sea surface temperature, but you know, moist static energy, or theta E, is also often used as a threshold variable. But you know, then the complications begin, and I'm fond of complications. So I'm going to talk to you about the actual threshold, which is the positivity of lifted parcel buoyancy. That's really the threshold for convection, of course, right at the process level. And then on the way out of the talk, I guess I'll talk to you about a synoptic threshold that's a little more tractable. And that's column water vapor. It has a longer synoptic kind of lifetime, and maybe kind of the key variable, I think, to get a handle on tropical weather. Short of climate, and you know, larger, more coherent than the convective process itself. So so here's a motivating slide recently. You know, deep convection, of course, is a you know, a fountain of water resources, but it's also a fountain of disasters. And this is, you know, recent of this fall, and I'm sorry if any of you know some of the lost people there, but you know, these heavy rains can be quite disastrous. And I got interested in this problem. Well, Abi trained me here into this paper here about Kerala floods in 2018, 2019. And as part of a long author list, I didn't get to, I learned more than I had to offer, except for a bit of editing. But what I learned was that that just in recent years and back to back, you've had these cloud bursts, which are rainfall exceeding 100 millimeters in 1 hour. And 2018, 2019 both had these. You can see that, you know, some fraction of the whole seasonal total in quite a wet place fell in a day or two. And that's quite disastrous. And so, you know, this was just documented those two events, and I guess what that led to was a next paper here that Abi and his group have sent along, and that I've joined a little bit more in person, which is to ask the question, you know, sharply: is West Coast India's rainfall becoming more convective? And it's a little bit speculative, this paper. It remains, because what we really, what Abi and his group really showed is that the seasonal mean cloud top height seems to be rising across the decades. And it may be that the top height of deep convection has something to do with how much it rains. It might be related to its cloudburst propensity, but that remains, I guess, to be, you know, there's a lot of steps in there to infill. So if we find this important issue is ripe for the study, then there are many levels in which of explanation that need to be done. But so that's really been the motivating thing for my involvement in this area. And I just want to walk you through, just because I'm a professor and a process guy, I'm sort of going to lecture you on surface climate thresholds and convection, and how to think about that. A little bit of history, interestingly, Indian centered in 1984. Sulachana Gadgil here proposed that sea surface temperature appears to be like a threshold for convection. They just had crude kind of cloudiness intensity, but you can see it really jumps up at 28 degrees as opposed to 26 or 24. And this was picked up maybe further in 3 years later in the 87 here. Sea surface temperature from 20 to 30, and you know, somewhere at I guess they drew little crosshairs here. Somewhere at 27 point something, you know, convection ramps up or begins. So that's the crude monthly mean, blurry version of a threshold. And of course, over the decades since then, we've noticed that you know, that there is a threshold-like dependence on SST, but of course that's climate dependent. It's not a magic number, 27.8 degrees. It's probably a shifting number over time, 27 and on up. And so this threshold estimate, you know, seems to have been rising over the decades. And so you need to adjust your threshold upward with time. There still is a threshold, but you need to adjust it upward in time. And this was from observations, but the same process is certainly seen in coupled climate projection models, that SST minus the tropical mean here, here's 0. So SST is above the tropical mean. You can see how steeply the rainfall rate rises when you get beyond the mean SST. And the peak is 2 or 3 degrees above the mean. And this is probably a tropical belt mean. Yeah, tropical mean. So a perspective piece by Adam Sobel on that very same paper drew this diagram about it, that if the whole sea surface temperature warms up, the threshold rises as does the SST. So there's always just some fraction of the world that exceeds the threshold, and that gets all the rain, and the part that's below the threshold, you know, gets none. So we have to think about SST relative to the global mean, and that's better. It's still a blurry monthly thing, but it's better. And you can apply this idea perhaps to the question of location of where the most intense convection is going to be. So, for instance, here are observational sea surface temperature maps. This is ERSST from the 1900s, 1900 to 1910, and with a relatively low color bar here. I've made it turn orange at 28 and red at 29. And you can see that in the in the early part of our previous century, the warmest sea surface temperatures were here in the Western Pacific, and there's just a little sliver of orange, warmish temperatures in the Indian Ocean. But by the time you get to the 2010s, the Indian Ocean is as warm as anywhere in the global warm pool. So it appears that the Indian Ocean has gone from being the edge of the warm pool to having its own warm pool that stacks up quite importantly. And there's reason to believe this might go on in the future. Here's one model I was able to lay hands on pretty easily, CESM2 and a large ensemble. And you can see here that model has a kind of an impoverished warm pool here in the far Western Pacific. But it remains true that their simulations of pre-industrial here have the West Pacific being the warmest place in the world and just a little sliver here in the Indian Ocean. But as we go to 2090 to 2100, the Western Indian Ocean is now in the top class of SSTs. And you can see I've adjusted the color bar here. Orange, this shade of orange here used to be 29.5 or 30, and now it's going to be 33 or 33 and a half. But again, the point is this relative SST. So the Western Indian Ocean may be becoming top class SSTs in the decades to come. Furthermore, the Western Indian Ocean has cooler upper air than the Pacific. This is a cross section here all the way around the world and up to 20 kilometers. And this is from the Meritu reanalysis here. and it's an average, it's a 40-year average, it actually looks a lot like this every year. But here's South America, here's Africa, here's the maritime continent. So this is the Indian Ocean, this interesting area. And I've taken the temperature at every level and subtracted the zonal mean all the way around the world. And this is right on the equator. And this is for all the Augusts. And but it's similar in July. So this is monsoon season temperature. And you can see here that the Western Pacific has the warmest upper troposphere. But here in the Western Indian Ocean, the upper troposphere is actually quite cool. In fact, it's some of the coolest upper troposphere in the world at these levels is right above the African coast. So top class SST, or top class relative SST here is actually sitting under possibly a relatively cold atmosphere. And so not only is it top class, it might be, might actually be the world's most convective place, conceivably, you can imagine. I just want to draw your attention here to this, this 350 and up, especially above 350. It may be peculiar to Merit-2, but 350 to 250 or so is this warm slab in the upper troposphere. And this sloping blue feature here over the East African coast and on into Central Indian Ocean. We'll meet those characters again later on. All right, so that's using SST and then relative SST, and the problem with that is that it doesn't include land. So there have been, and I won't go into this much, but people have taken the same idea to relative moist static energy or relative theta E, and that is so this is Bombardier and Boos just this very month here, and they define the relative moist static energy again as the difference between local and tropical mean surface air MSE. And that can be calculated over both land and sea. So that's in a way a nicer way to look at the convective threshold issue that encompasses both land and sea. And future changes in relative MSE correlate well with onset and demise date changes in model simulations, I think. So there's some nice ways to imagine, I suppose, that the Western Indian Ocean might be becoming interestingly more convective, possibly dangerously so. And you could ask, well, hasn't it already happened already? Have we observed it yet? And I haven't talked to Anna for a few years about this, but although sea surface temperature has risen across the Indo-Pacific warm pool, the expected accompanying increased rainfall has occurred only in the Western Pacific. So this all still remains a little speculative, at least as of 2013. Maybe he's in the audience and will write to me and there's been some update. All right, so that's the idea of thresholds as used in climate and projecting out decades and the grand problem of climate change. I do want to march you through the actual threshold process here, which is lifted parcel buoyancy, and I'll do it at some length here. So settle in. It's a thermodynamics lecture, I guess, for a bit here. But I feel like it's important to understand the true process and actually to begin to appreciate what a vertically structured system the monsoon is. Some people just think maybe 850 and 200 and you're done. But the South Asian monsoon has some interesting vertical structure, I find, and I just want to share some of that with you. So here's a sounding from the Seychelles. I picked this date somewhat at random, although somewhat because it had such interesting vertical structure. And I just want to walk you through this diagram. So here's a diagram. This is some of you look at SKUTs and things. This traditional aerological diagrams. I really dislike them. And today it's pretty common for people to know about these static energies, but I just want to walk you through it. So the idea is that we're really, the issue of convective instability is how's the energy distributed over mass? And here we have thermodynamic energy per unit mass, these specific energies, kilojoules per kilogram, S, H, and H sat, or dry static energy, moist static energy, saturated moist static energy. And here we have pressure, so that is mass. So when you multiply energy per unit mass by mass, of course, area is then total energy. And so that's a nice diagram. I prefer that to the log P, skewed T and log P and all that. And I have a nice package if any of you are Python users, MSE plots-pkg is what I'm showing you. So of course, and you probably all know this already, you take your pressure sensor data and you define a hypsometric height and you multiply that by G, and that's your potential energy. You take your temperature sensor data, that's temperature, and you multiply it by Cp, that's your enthalpy or heat energy. And then your moist static energy, H, is the dry static energy plus L times the mixing ratio of water vapor. It's a function of both the temperature sensor and the relative humidity sensor, the hygrometer. And so that makes this blue curve here. And then saturation moist static energy is S plus LQ sat of temperature. So this would be like at 100%. And just notice this is a function only of the temperature profile. So this comes from the thermometer only, this comes from the thermometer only, and the thing in between is just relative humidity. In fact, you can see here, it really is labeled as relative humidity, just equally spaced lines between the black curve and the red curve. And so this blue area here is the latent energy. It's L times the column water vapor. We'll hear a little bit about column water vapor later. So this is 41 millimeters of column water vapor, for instance, or 59%. The area between the black and red curves is 59% full of blue. The white area here is what we would call the saturation deficit. Yeah, so that's the parcel. That's the basic depiction of what the balloon sampled. The good thing about this, of course, is that a parcel of air from the surface conserves its value of H, so it's a vertical line on here. So you take the surface parcel, lift it vertically, and that is your undilute parcel. And it works out that if the green curves to the right of the red curve, the temperature of the parcel exceeds that of the environment, and you have a buoyancy. The parcel is buoyant. So that's the real threshold that makes convection go, and it is a function of height and a complicated function of height. All right, so let's get a little more detailed. Another thing that's nice about this diagram is that your parcel here, if you looked at a skew T and it has this dew point curve that's way over to the left, you don't know what to make of it. But here, everything is just energy. So entrainment is just a, here's your parcel. If it's going to mix with the environment, it is merely being drawn toward the blue curve, proportional to how far that is to the blue curve. So that's we actually have a quantitative vision of entrainment on this diagram. And I guess when I see a sounding, and I want everybody to see what I see in a sounding. When I see a sounding, I have a whole imaginative story about the air mass here. So let's think about that. Here's this sounding. We have a whole air mass. Of course, the balloon sampled a particular square inch of air or something, square meter of air. But we can imagine if you'd launched it 2 minutes later, 2 minutes earlier, there's probably some PDF of parcels around the surface. So we can allow for those to vary a little bit. Entrainment rates, we all know there's wide clouds and narrow clouds. So there's probably some PDF of entrainment rates, and you can specify those in the software. And, the atmosphere has a lot of wiggles and jiggles in it. So if you have adiabatic displacements of air, those follow the slope here of these red whiskers on this curve. And you can see that a pretty small, just 10 millibar up or down motion can really take these capping inversions. No parcel could get through this capping inversion. But if you just have a 10 millibar vertical displacement, that goes away and the parcel can get through there. So these lines are crucial to the diagram, and they're surprisingly steep, especially at low levels. It doesn't take much adiabatic vertical motion to lift or create these caps. And again, that's all in there. So when I see one of these and I use my software and I take my ensemble of parcels and I give them an ensemble of entrainment rates. And I'm already imagining, some parcels are going to go up here. They're going to hit this little 850 inversion, I guess you'd say. It's both dry and warm, and mostly they'll quit there. But so mostly they'll quit there. But some of them may get lucky, and maybe they get together and protect the middle one. And the middle one might make it through that little cap and achieve a little buoyancy right in here, and achieve a little almost neutral buoyancy here. Maybe if it's the lucky one and the lucky one, and it might get stopped by this little inversion here. And And some other one, lucky one of a lucky one protected by several might get all the way to this little inversion here at about 450. And maybe somewhere out here, some clouds off in the distance might be going all the way to the tropopause, where really no parcel can get beyond that. But you see, we might have really a multi-layered, multi-depth population of clouds here. And if I show you the picture of where this sounding went up, I think it's, it's not, I didn't mean for this to get all animation-y. I think it's not terrible. You do see some real deep convection here with the cirrus coming out. You see these little shallow-cues everywhere, and you see some mid-depth type of clouds here as well. So I think it's quite realistic that there are often these multi-depth convection fields, and that you see that in the sounding. So with that imagination, and if I fade out the imaginative clouds, you can notice, well, actually the moisture itself tells you that this is probably full of clouds, because look, it's all 80 or 90% saturated. So, some of that's probably cloudy. Here's a layer that's moist. So this is probably, full of clouds, and this is probably full of clouds, and maybe not many are making it up here because it just isn't very moist. In other words, the vapor itself kind of tells you about the cloud field in a way. And so, the question is, can you now just see it without all the props? I've walked you through all the props. Now you can look at a sounding and see what I see, which is an ensemble of clouds in a wiggling, jiggling environment that we happen to send a balloon up into. I hope so. So, all right. So that's all this static energies. And they're nice because it's energy per unit mass and stuff. All that niceness kind of goes away when you use potential temperatures. These, I don't know why people like potential temperatures, but anyway, there's potential temperature equivalent and saturated equivalent. And they now no longer has the property that it's, the heat plus the height plus the vapor. It's some formula with exponentials in it and stuff. But, it tells the same story, right? It tells the same story. So without all the props and without the energy by mass interpretation, I hope you can still sort of see the story here, because I'm going to show you a lot of soundings like this. All right. So then we can think about what happens at the surface when the SST, how does the temperature of the water affect these soundings? So here's that same sounding again, and it looks like the surface temperature is about 29 here, and so is the surface air temperature, within the widths of these numbers. But over here you can see that the surface air is only 70% relative humidity. And so, what happens when you, what's happening is that latent and sensible heat flux are drawing the surface air H toward the saturation H, which is the properties of the air that's touching the water, the lowest millimeter over the water. So you can almost think, you can just look at this distance on the graph and say, there's a spring here. Drawing the blue curve toward the red number, and the tension on the spring is proportional to wind speed. The windier it is, the stronger it's being drawn to the right. So, so if you go from 29 to 31 centigrade, that's quite a lot more tension here. That's quite a lot more flux driving this curve to the right. Whereas over here, the theta alone would be, this is the sensible flux. This is the latent flux. Yeah. All right, so that's so you're oriented, I guess, now to these diagrams, and I want to show you, getting back a little bit to the question of trends. So here's a theta E plot, and this is MERA2 data soundings from a place near Kerala. It's 5 north, 65 east. Actually, no, this is more pretty far west. It's halfway to the African coast, maybe 65 east. But so here we go. Here's and each of these is a July monthly mean, and 80 to 21 colored coded. And you sure see that the surface layer has warmed up, quite definitely in a trend-like manner. Definite upward trend near the surface. Blue to red, blue to red, blue to red. Definite blue to red trend near the ocean surface here. And so that was theta E, which is what the surface flux draws to the right. This is theta ES, which remember is the temperature only profile. And you can see that its upper levels definitely have an upward trend, blue to red. And of course, that is really, the surface parcels rise up here and achieve sort of neutral buoyancy with respect to the upper troposphere. And so, the warm SST warms the parcels come up here and they equilibrate with a warmed upper troposphere. So there's a clear trend in theta E at the surface. It's a clear trend in theta E saturated in the upper troposphere. And those things are, pretty rigidly tied together. Here's theta E and theta S on the same diagram. And just to show you, these middle levels here, 800, 500 or something. I'm not seeing it. Well, it's a little bit blue to red here, but it is far from a clear, simple trend in the middle levels. And that's really the moisture in the mid levels. And that's not directly driven by the SST and does not directly adjust like the upper level theta E and theta ES do. So that's kind of the wild card there is mid-level moisture, and that's flow dependent and everything else. All right, so that's our toolkit. Is these lifted parcel buoyancies. And I want to talk a little more eventually about column water vapor, which is that mid-level moisture. But I've been showing you some MERA 2 single profiles, and it's a little bit too blinkered. I want to walk you through just some, what MERA 2 sees of the monsoon. So here's your basic monsoon variables as seen in MERA 2, actually with also I-merge, the climatological I-merge rainfall is on here in a kind of transparent way. So most of you'll recognize the shape of monsoon rainfall, real thick on the western coasts of the land masses and up against the foot of the Himalayas. But actually a bunch of rain here down is on the upwind edge of this warm tongue in the equatorial Indian Ocean. So I've got both climatological SSTs, the thick ones here, and I have year-to-year SSTs, sort of jumping around amidst the climatology, just to show you how big interannual variability is. I think I'm just showing you, I'm just showing you 2000 to 2021 here, because those are the years of the rainfall data set. And that place I was showing you the trends in the sounding, 65 east, 5 north is about here, kind of on the north edge of this warm tongue of SST, which we're thinking might get warmer and warmer in climate change or become the warmest place in the world almost. So it's a relevant place to have put my little probe, and that's what we've been looking at. And it's, I suppose you'd say it is upwind of, broadly speaking, upwind of southwestern India here, where we're interested in the issue of cloud bursts and whether the rain's becoming more convective. In looking at a lot of this data, I picked out 2002 and 3 in July monthly means of 2002 and 3, I think are a decent kind of a real strong interannual, 1 year followed just the next year, kind of a dipole here that's sort of a little bit like pre-industrial and, 2200 or something, possibly. Anyway, at least in this region, it's a little bit the same thing, a cold year and a warm year. And you can see here along the west coast of India here, where I'm showing the individual year rainfall, you can see how it goes from very dry year to a quite wet year along the coast. So this is so 2002 and 3 in July, and this might have been an earlier, an earlier late onset. I'm not sure. These monthly means are so blurry. But down here you can see I have my little probe here, and you can see that the dry year, the theta E curve is far to the left. There's a lot of dry air, and there's a lesser change in the temperature itself. There's always this, Mera 2 always has this 350 millibar kind of overhang for its buoyancy. And we'll get back to that in a second. So a distinctive curve here in that profile. So all right, so that's what we've been looking at is theta E 975 minus theta E sat 400, and that's because down the boundary layer up to this 400, below this cap at 350. I had to learn to avoid that cap at 350. So here's another view. This is a perspective view from the south. Can you see that this is here's Madagascar in both of these. Here's the east coast of Africa. And here's this 2002 with its very wide, warm equatorial tongue of warm SST and rainfall. And oh, sorry, yeah, it only goes this far. And then 2003, it comes quite a bit further and is quite a bit warmer and quite a bit redder, which is theta E 975 minus theta E sat 300. So this whole thing, is pushed to the west and strengthened in 2003, and you can definitely see this this layer here at 350 that kind of overhangs, that puts a lid on the convection. Appears, yeah. Well, there you go. So there, here's this 350 millibar level is warm here and kind of caps things. Here's this sloping blue thing that we saw in the climatology. And I told you we'd meet this red and blue couple again. And you can see that couplet of temperature anomalies actually recedes and advances with the sea surface temperature. So I don't know quite how to interpret those, but they sure are distinctive, I think, and part of the vertically structured nature of the problem. Here's just another view. Now we are looking at a perspective view from the northwest, right? So here's India here, and Sri Lanka off its southern coast. Here's Arabia, and this is the equatorial. This is that equatorial cross section going all the way around the world of the eddy temperature field, the deviations from the zonal mean. And again, this is those 2 years. 2002, 3. Oh, this is 4 years. Anyway, you can see this red thing and this sloping blue thing and this red wedge at 350 and above. They really do go. They really do zip back and forth together, along with the SST. When it's warm, it pushes westward, and when it's cooler, it retracts back to the east. So this seems to be the structure of that of the warm and cold years of the Western Indian Ocean here at the equator. Are there questions or just noises occasionally? Just noises. That's good. All right, so this got me all quite intrigued at at how vertically structured this was. I hadn't expected quite so much structure. Certainly off the African coast here, where the water's cold, you can see that where the wind has chilled the water. You can see there's cool air right at the surface, and that's capped by a warm layer here at about 850. And that over here in the conserved variable sounding, you see there's that 850 millibar cap is prominent and variable as it goes east and west. And this red thing at 350, you can also see over here in the probe. I hope you guys are seeing my mouse pointer sometimes. So I was surprised to find that at least in Mera 2 there are really 4 caps to buoyant convection. Like I said, there's this 850 thing, quite low levels. And that's, you know, your traditional, I guess, trade inversion or something. And of course, there's a main tropopause up here. The 150 millibar is always warm, 250 pretty warm. So there's a main tropopause here. If we take an isosurface of the vertical derivative, you can see there's the main tropopause here at 150 or so. And then here's this 350 millibar overhang that's so frequently there. That appears to be part of this warm body of air that maybe is tied to the top of the topography over there. And sometimes there's a 500 millibar stable layer as well. So 500, sometimes the convection is of course capped at 850, sometimes it's capped at 500, sometimes at 300, and sometimes all the way to the tropopause. And of course, like in that sounding I showed you, maybe the whole populations of clouds are fighting their way through these, it might be, you know, four types of clouds and getting to different depths in that way. I wanted to find out how trustworthy that was, whether that was MERA-2 specific. So here's the MERA-2 August monthly mean, right off the West Indian coast, I think, where I've drawn a cross section here. And so here's your 850, your 500, your 350, and your 150. And if I look at ERA 5 from, you know, same monthly mean, same latitude, same longitude, they don't seem to have the 850 very well, I notice. This 500 is an actual overhang. You see these contours actually overhang, contours of theta ES actually overhang. So they have a much stronger kind of a cap at 500. There is maybe a little bulge sometimes at 350. And then of course the main tropopause is, you know, set by much larger forces. So I do think there just seem to be these four layers and that the reanalyses have different depictions of them. And I wish there were more balloon soundings from India that I could find. In the Wyoming site, they don't seem to have any from the entire nation of India, but I'd love to see some more actual balloon soundings from monsoon season. But a lot of this, so this 350 Kelvin, you know, cap to the convection, which is, you know, it's just a property of temperature itself. So I can depict here the altitude of the isosurface of 350 Kelvin, and the altitudes here in colors. And you can see that that 350 Kelvin surface is lowered into a bowl here over the heat lows and the elevated heat source of Tibetan Plateau. And you know, I've just shown you once a decade here for the 2000, 2010, 80, 90, 2000, 2010, 2020. So, you know, once per decade, you know, poor man's trend calculation. And it's not clear that, anyway, you'd have to be a little more careful. This could just be interannual variability. But, you know, we might imagine there might be a trend because the land's heating up. This is really, you know, upper level warmth over land. And so I guess if we're talking about, you know, is convection going to get taller here along the west coast of India? We would be saying, is the height of this capping surface getting higher? And actually, if anything, I'd say it's quite the opposite. It's moving southward along there, along the west coast. But this is a fixed 350, and of course, we should really be using some kind of relative value. So I've just been fishing around with the data, but and I haven't figured out how to make that relative in a meaningful way. All right, so that's just to orient you, I guess, some to this the vertically structured, the rich vertical structure of the monsoon, which I've just been enjoying studying for this talk. And I guess I'm down to my last issue to share with you, which is here's another maybe real threshold for rain in the tropics. It's not right at process level like partial buoyancy, but it's not kind of just empirical like SST. It's you know, it's clear how this would affect the clouds. When it's dry, they have to fight their way through entrainment, and when it's moist, they can make it to the tropopause. And a number of people over, past decade or two have been showing this in various ways. I just like this nicely because it has it shows the mean and the median and a range. And anyway, but the point is, when the column gets above like 75%, this really spikes upward. The expected value of precipitation really spikes up just from 75 to 85 or 90. This is much sharper than the SST quote unquote threshold. This is a hockey stick shaped threshold. So this is pretty darn clinching threshold, and almost surprisingly so. But anyway, so this column water vapor is really a tight constraint on convection. And I've been looking at that quite a bit too, and contriving my color scales to be about, to be evocative of this. And here's an example of an event in August. This is a summer monsoon event. And you can see this pool of moist air here. The column water vapor is above that threshold. And yeah, it's full of deep convection. It's not a vortex, it's not a storm or anything. It's just a pool of water vapor that exceeds the threshold. And look at that, the deep convection, is having its little mesoscale playground there for whatever structure it wants to have. But the vapor itself really lasts for days and days and days. The mean flow here is pretty weak. There's kind of a circulation around it on the equator, but mean flow is pretty weak. This thing eventually goes over and hits the east coast of Africa, which must be incredibly consequential there. And if you traced it backward, it just kind of extruded off this mass of moist air that is the monsoon. So I think this is and I've looked at this in all seasons and made a measure for it. There's quite several of these events per year that last more than a week. They'll break off, they'll sort of get extruded and break off from the western edge of the Indo-Pacific moist pool, not in all seasons really, and come over here and strike the east coast of Africa and last a long time in the meanwhile, which begs questions of the longevity and their propagation. So I think this is a very fruitful kind of a threshold. It's not blurry and empirical like SST and monthly means, but it's also not a parcel by parcel of convection. So I really feel like this might be the missing middle of making sense of these threshold-like behaviors of tropical rainfall that monthly means just don't do justice to. All right, so that's and all that was to say I'm recruiting a PhD student right now to study these. Just got the funding recently, so they're extruded from the moist pool not only in summer. I think the vapor itself is the memory variable. That's what's being advected and having coherence and identity. I don't see a lot of vorticity or kinematic structure here, and I think it's a fascinating new kind of a storm or something, and love to find a good student for that. All right, so I'm going to wrap up here. I've lost track of time. Hopefully not too long here. And all right, so down at the process level, buoyancy greater than 0 is the real threshold, cloud by cloud at the convective scale. But it's kind of impractically fine and not quite useful. Column water vapor is pretty darn useful. I guess I did. I had a save crisis on the file. Pretty darn steep or sharp as a threshold, and yet is also coherent from day to day, unlike convective clouds. So I think that might be a really useful middle variable. The top height of clouds, I still don't know, back to the motivating question, I'm not quite sure whether the clouds are capped at 350 or they go to 150. I'm not sure if that upper level buoyancy translates into more cloud bursts at the ground. That's a real convective scale issue. And actually that could be done with a cloud resolving model where you tweak the sounding a little and see how the upper levels affect the low levels. Of course they do, but it's not very direct. Of course, what's driving all this in a way is these trends. So we have sea surface temperatures rising in the Indian Ocean sector, both for like global ocean reasons above my head, but they're below my depth or something. And also greenhouse gas forest, and also interactions with those. So you know, if those are trends driven by the mass of the ocean and the greenhouse gases, they're likely to continue. So it'd be nice to be able to extrapolate them. But land heat also might affect these upper level capping inversions and things, and so maybe an interesting place of land-sea contrast. There might be some vertical structure to the land-sea contrast view of the monsoon yet to be painted out. The troposphere, of course, warms with the SST, and really with the broad scale SST. So really we should be doing relative in all these things, of course, including relative column water vapor. I guess I identified July 2002 to 3 as a, you know, really jumped out at me as maybe this super analog of a very retracted warm pool in the Western Indian Ocean and a very expanded and warm one. So maybe it's a little microcosm of these, you know, across the decades or centuries, what we can anticipate. So. All right, that is my entire talk. So thank you very much for your attention, and I'll take any questions.
Thank you. Thank you, Professor. That's for an excellent presentation and with excellent graphics. And I have a few questions, but let me see if there are questions from other participants. Otherwise, I will be just some clarification from my side. Okay. So since I am not seeing now as of now, let me start with my doubts. Basically, it's because of my ignorance. Okay. So in the first part of your talk, you are talking about the threshold, and there is a positive trend in the SST threshold. So I'm just wondering, when we are giving numbers like 28.5 or 29.5, because we are talking about the region where there is large spatial variability. So when are we talking about an average? And of course, when we take, don't you think, or we are talking about the peak? And don't you think we should also, even if you look at the peak, we have to talk about some area weighted peak or something? What's your comment?
Yeah, I suppose, right. There's the value, there's the longevity, there's the size of these warm pools. We should almost be thinking about, pools, not just local values. Yeah, it's always, it remains open question, I guess, how, I know what scales to look at this on. The sea surface temperature lends itself to monthly because it doesn't change very much from month to month. So that's just been convenient for a lot of people for a long time. Monthly means are just so convenient compared to anything shorter. Pentads seem to have gone out of fashion. So like this Meteorological data set I love so much, you have two choices, hourly and monthly. And I always disdained the monthly. This is the first time I've sat down with monthly mean data. Oh, and it is just tempting to only have one value per month compared to 24 values a day or 8 values a day. And there's just nothing in between. I think a lot of these questions of, I lose the thread a lot. You know, I think monthly means are a little too blurry, and so climate is off on its own ways of thinking. And hourly is too noisy, and so weather's off on its world. And this, the weather climate linkage, or how we can interpret these things down or aggregate them up, it would help a lot if we had some, if just things like Pentad data sets were more common. It's just these monthlies are, but they're wonderfully small. Monthly means are wonderfully small. That is their great virtue.
Of course, I see a question here from Uma. Since I have started, let me complete my list. Another question I wanted to ask you is about the vertical structure of buoyancy and the latent heat release. And in this scenario, how is that cloud feedback? And now we are talking about aerosol cloud interaction, particularly over the region where very close to the polluting landmass. So are they, how significant, or are we ready to tackle them?
Yeah, these microphysical effects and things, right? As another, yet another aspect of convection. I guess when I'm accustomed, I just think these changes in relative humidity are so large and important that I must think they kind of dwarf microphysical effects. That's just my bias, I guess. Yeah. That I think that, you know, the humidity, the water vapor field is just so, you know, the answer is probably mostly water vapor most of the time. And but some of these inversion tops, some of those could be, you know, pollution, you know, solar absorbing black carbon. Yes. You know, is detrained at some level, and then it heats, and then that makes more clouds detrain at that level. You know, these caps could be self-sustaining radiatively, including through, you know, pollution and things. So so maybe the water vapor follows along the convection, and the convection is actually sculpted in a way by these inversions, and some of those inversions might be feedbacks with radiatively active substances that are brought up to the surface, and not just water vapor. But I'm beyond my depth there. Yes.
And yeah, the last question doubt rather is about, you have very nicely shown the temperature profiles and the trend in the temperature profile somewhere close to the Indian coast, and we could see particularly at lower altitudes there is a temperature increase in the atmosphere, of course. So is it, of course, are we it's a very clear signature of the global warming, or it is highly localized, or yes, this is the profile. And so if you are collecting these profiles over, say, north and south or east and west, wherever we get, do you think this kind of similar trend, or how do they come up?
Yeah, well, I've just sampled a few points with that probe, and this is all MERA-2 data. You can see from the levels, and you can see from the way 350 always overhangs that this is MERA-2 data. But I think from the few points I've probed, this is quite a widespread trend. You know, it's not huge, but it's systematic, and definitely in temperature at upper levels, and then definitely at in theta E at the low level. And then, you know, out in the middle, it's more weather variable. So I suppose, you know, this is very much tied to SST, and it's quite easy to look at SST trends, and plenty of people do, and you'll have many talks about that. And I suspect the upper level temperature kind of follows along with the SST trends, which also govern the boundary layer theta E. And in the middle here is where all dynamics gets to come in and make its impact.
Okay, sir, thank you very much for your patience. And now we will take questions. Probably you can also see it in the Q&A section below. Anyhow, meanwhile, I will read it out. The first one from Uma, and she asked, rather than the top height, is it the depth that matters the most?
Oh, maybe I mean the same thing. You know, convection depth upward and top height, those to me mean the same thing. So you'll have to clarify what that distinction is, because I'm not sure what you're asking. To me, those words are the same, the depth of convection and the height of convection. We just call it depth because it's upward deep into the sky, but yeah. So maybe you can.
So Umar, I think you got the answer, yeah? As Professor said, it is when you say they mean the same, yeah? The depth. Yeah, so now we move to the second one from Mr. Umesh Prasad Verma. He asked, dear sir, with great regards for your marvelous talk, I have a question. Will you clear my question? Why we use SST and greenhouse gas in forecast strategy? Can it be utilized in Indian monsoon context?
Well, yeah, this is complicated, right? The greenhouse gases are, you know, well mixed through the atmosphere, and they, you know, drive all of climate change. but it's processed through the system in ways that, you know, the local impacts may be felt by the ocean temperature going up. And that might be partly, you know, by the radiation from the gases, but partly the, you know, the way I read it, the Indian Ocean is partly warming because it's connected to the North Atlantic, which is changing. So, I mean, it's such a global problem. You know, greenhouse gases, of course, are the ultimate source of the trend. Sea surface temperatures observed to be trending, and we don't know whether that's gas forced locally or non-locally, or actually there's just decadal variability in the oceans. So, you know, it's a giant research area that you're pointing at there, and I'm not the expert in a lot of that. So I'm afraid I can't illuminate you too much. Yeah. But very good questions anyway. Keep up the good questions. Yeah.
Yeah. So, any more questions from the audience? Of course, Professor, you may be knowing there is a group of people, they are need not be represented here in the participant. This is a small group of panelists, but there is a large group they are seeing, and so that we can expect questions from them also. So I am waiting. If not, I will, on behalf of the organizer and myself and my colleague, Dr. Radhika, thank you so much for an excellent talk and for giving this up-to-date information and the present state of understanding of this very complex system. Thank you once again, Professor Bernma.
Yeah, thank you too.
Thank you.
And please, you want to say something?
No, I'm fine. Thank you. I just wanted to thank again.
Okay,
For
good.
Yeah.
Now so I am handing over to, there is now your question is coming, but I do not know, Professor Ben, are you available since we have some time? Dr. Patnaik from YouTube, he is asking why Arabian Sea is more convective compared to Bay of Bengal. Is it SST or moist static energy? Professor Bernmax, if you are available, you can answer him why Arabian Sea is more convective compared to Bay of Bengal.
I'm not sure I know what more convective means. I think it rains more in the Bay of Bengal. There's more rain in the Bay of Bengal, but it may be that the Arabian Sea has more vigorous convection or something. I'm not sure. And it could be some of that temperature structure, you know, that cool upper levels hanging over the Indian Ocean from the Atlantic in one of my early slides. You know, that could make some of the Arabian Sea convection could have an upper level of vigor just because that cool overhang from the Atlantic, but I'm not sure.
Thank you for your patience, Bernmax. So now I'm handing over to Dr. Radhika Ramachandran. She will be conducting the session. Radhika, please.
Yeah, thank you, Dr. Jayaraman. Now we are moving on to the second talk of the second plenary session. It's by Dr. Andrew Turner from the University of Reading, UK. And the topic is effects of climate change on the global and regional monsoons. As Dr. Turner has already been introduced to the delegates, I'm not venturing into that, and it will also save some time. So thank you for accepting the request, and over to you, Dr. Turner.
Excellent. Good day to you all. Hopefully you can see my slides. Can someone confirm that, please?
Yes, we can see.
Yeah, we can see.
Excellent. Thank you very much. It's a great honor to be able to give this talk today at the INTROMET conference. I actually went to a previous INTROMET conference in February 2014 that was in Chennai at SRM University, and I have fond memories of that. And you know, I wish I could be there in person right now to give this talk. Not least because it would be later in the day than 5 o'clock in the morning, which it is currently here for me. So I hope you'll forgive me if my brain doesn't connect to my mouth in an appropriate way. I'm going to talk about the effects of climate change on the global and regional monsoons, and this really is a culmination of the work that many people have done on the IPCC 6th assessment report, working group 1 that came out in August of this year. And what you can see on this slide.
Will you please convert into presentation mode? It is smaller.
Okay. Are you seeing like the presenter screen?
Yeah, we are seeing presenter view. Yeah.
Oh, okay. I need to somehow swap the displays. Let me click that. Okay. Can you see now the full screen?
Yes, we can see the full screen. Yeah.
Excellent. Okay, good. Thank you very much. It's good that we've got that sorted out on the first slide. So what you can see here in this image is a composite photograph of an area near Hyderabad in India, and it's just demonstrating the impact of different sort of extreme years, if you like, on the monsoon in the same place. And I'm sure you're all very familiar with this. That it really makes the difference between something that's dry and not productive and something that's thriving and has a lot of output. And this is why we study this subject, is because we want to understand what it is that drives this giver of life. And the second image I'm showing on the screen now is just one example of the ways in which you might define monsoon areas around the world. And there's many different ways you could do this. This is just an example. The blue colors are showing the monsoon regions in the northern hemisphere, and the yellow region showing monsoon regions in the southern hemisphere. And the point to get across here is that certainly the Indian monsoon is the most famous of them all, but there are monsoons or monsoon-like climates in other parts of the world that need to be studied, and there are many research questions in those other monsoons if you're interested to study them. So why do we get into this subject? Well, we know that climate is changing, and we know that anthropogenic influences such as greenhouse gas emissions and as well as other things such as aerosol pollution and land use change have been going on. And the question is, well, how do they change the monsoon or other features of the climate? And there's a lot of change going on in the world as well. There's growing population, need for economic development, the requirement for food, energy, and water security. And so therefore being able to understand how the monsoon will change in the future and has changed in the past is vital for government and users of water resources and so on. And on the right here, this is just an example temperature time series, global surface temperature change from the IPCC. Just to orientate you, I'm sure most of you are familiar, but we have these different emission scenarios for the future, depending on the different choices that the world might make, that result in different levels of radiative forcing, which is given by these latter numbers here, and that gives us a different trajectory of how the global temperature might change in the future. And some of the timescales that we might be interested in when we're looking at this are displayed here. So the near term is really the next 20 years. We have the medium term after that, and then the long term right out to the end of the 21st century. So I'm definitely not going to claim that what you're going to see in this talk is my own work, because this is a huge team effort by the authors of the 6th assessment report of the IPCC, and of course all of the literature that they've assessed in creating this report. And you can see here the group of lead authors and coordinating lead authors that was involved in producing this report at one of the recent meetings. In fact, this was the last physical meeting we had in the IPCC before all of the lockdowns that we've been experiencing as a world. So a huge team effort by a lot of people. But I want to point out, and hopefully you can see them on the front row here, that there's some prominent Indian scientists here as well that have made huge contributions to this. And you may know Dr. Krishnan and Dr. Swapna, who I've highlighted here, Dr. Krishnan was a coordinating lead author of Chapter 8. And Swapna, of course, has been heavily involved in leading the efforts of IITM in contributing an Earth system model to the CMIP6 multi-model database. And this is the first time that India has taken place. India has put forward a model to this effort, international effort. And I really do want to emphasize that being involved in this activity is a fantastic sense of teamwork, and it's a lot of hard work. But if any of you out there ever get the opportunity to be involved in any form, then I strongly recommend that you take it. So I just want to show here something about how the monsoon information in the 6th assessment report, working group 1, is organized. And what we've got on this page here are various chapter titles. Towards the beginning of the report, we have some chapters on large-scale climate change. And this is where a lot of information on the global monsoon is kept. So in chapter 2, this is changing state of the climate system. That tells us something about the observed changes in the global monsoon. Chapter 3, human influence on the climate system. This is looking at those changes that have occurred, and it's trying to attribute those to human causes, if any human causes were found. And so the global monsoon is looked at in that context. And then chapter 4 is about the global scale future projections of climate change. And so we can think about the global monsoon in that context as well. Following those early chapters of the report, we then have chapters on climate processes, and the one relevant to the monsoons is that of chapter 8 on water cycle changes. And this chapter 8, is the one where the bulk of the region by region monsoon information is held. So that's your go-to chapter if you want to look at that. And then towards the end of the report, and this report has sort of advanced in this area over the previous IPCC reports, there's a collection of chapters on regional climate information. So chapter 10 was the chapter that I was involved in as an author. So this is about the methods really of linking global to regional climate change and all of the multiple lines of evidence that we need to think about. Chapter 11 was about climate extremes, and then chapter 12 was starting to get into the climate impacts, and this sort of makes a nice link with the Working Group 2 report that's expected early next year. And then finally, of the sort of normal chapters, there was a regional atlas which contained sort of almost at the country level information about how climate is going to change. And then this really new tool, this interactive atlas, which anyone can access, and it's a great fun way of exploring climate information. All of the monsoons information that's contained in here is then summarized in headline statements, either in the technical summary, where there is a dedicated 2-page monsoon box that captures everything about monsoons, and then finally in the summary for policymakers. And then there's also an annex on some technical details about how you define monsoon domains and that sort of thing. So for stuff that wasn't put in the main report. But just to emphasize that the detailed region by region monsoon information is kept in chapter 8. So what I'm going to be doing is going through from the global to the regional monsoons in some of these chapters, and just giving you some of the headline messages. So we start at chapter 2 and look at some of the global monsoon changes that have been going on. So a lot of these chapters, the point of the assessment is that you start from the previous sort of known position. So has anything changed? Has anything developed? You know, what is the starting point? So reporting on the previous IPCC report, the 5th assessment report, there was a weakening of the global monsoon circulation and a decrease of the global land monsoon rainfall over the second half of the 20th century. And in the latest report then, we've advanced upon this a little. So observed trends during the last century indicate that the global monsoon precipitation decline reported in the 5th assessment report has reversed since the 1980s. And that's mainly contributed from changes in the Northern Hemisphere monsoons. The Northern Hemisphere monsoons, there's a larger area there, they tend to dominate the signal. And we also know an important caveat that the global monsoon precipitation has exhibited large multi-decadal variability over the last century. And so if you were to try and measure trends over the whole century in the instrumental record, you really don't have much confidence in them. So just to give you a sort of a very brief explanation of climate modeling, because I know there's quite a few students there, you may not be familiar with some of these aspects. For the historical period, or the 20th century, we force our climate models, or GCMs, with known external forcings, both anthropogenic and natural. So these could be the CO2 emissions, it could be anthropogenic aerosol emissions, which, unlike CO2, these are not necessarily well mixed. So these have strong regional patterns, and that turns out to be important for the monsoons. So land use change, there might be changes in the solar cycle, that's all accounted for, as well as other greenhouse gases or short-lived climate forces, as we call them. We can also then perform a type of experiment for the historical period that's called detection and attribution. And what we do, first of all, is we do an all forcings experiment in which we're controlling all of the forcings, CO2, land use change, solar change, aerosols that happened in the 20th century, and seeing how climate varied. And of course, we can compare that to observations. But the other thing we can do is that we can run experiments of the 20th century, imagining a different world in which only one of the forcings change. So we might just change the CO2, or we might just change the aerosols. And that allows us to try and assign blame to a particular forcer as to how climate might change in the future, in the past, how it's changed. And then our future projections obviously rely on assumptions about how those emissions change in the future. Obviously, we don't have measurements of what all of these different forcings are going to be like in 2050, in 2060, and so on. So we have some socioeconomic pathways that allow us to project what those emissions might be. And those are based on different assumptions about what happens with global economics, essentially. So chapter 3 of the report looks at attributing changes in the historical global monsoon. Now, in the previous version of the report, it was reported that there was no detection and attribution assessment statements on that decreasing trend of the global monsoon precipitation. So that was something that was mentioned in the report, but it wasn't explained. But more recently, the 6th assessment report has tried to look at this in more detail. So what you can see at the top here, this is a figure from that report. And just to avoid doubt, whenever this banner comes up at the top here, the blue banner, that just means that the figure has come from the IPCC report. And you can see a short version of the figure caption at the bottom here. What you're seeing at the top is a representation of monsoon domains, a change in monsoon rainfall across the year in observations, and then on the right in what's called the multi-model mean of the CMIP6 models. And there is a good but imperfect simulation of the present day global monsoon domains. Now, if we collect together all of the rainfall that's happening in the monsoon domains around the world, we can come up with a time series of the global land summer monsoon. And if we measure that in several different observed data sets and in the models, we find that there's a decline sort of since about 1950 up to about the present day, sort of 1980s, 1990s, and then followed by somewhat of a recovery. And that's found in both the models and the observations. So the fact that it's happening, this downward trend and upward trend in both the models and observations, suggests that this is being forced somehow by external forcing that's being assigned into those models. And we see a similar signal, incidentally, in a measure of the northern hemisphere summer monsoon circulation. So somewhat of a decline and then a recovery. And this index, incidentally, if any of you are familiar with the Webster and Yang index for the Asian monsoon, this is basically an extended version of that index, but across the whole of the northern hemisphere region. And it's looking at the vertical wind shear in the zonal winds. So, attributing change of the historical global monsoon. The assessment statement made in chapter 3 of the 6th assessment report states that greenhouse gas increases acted to enhance the global land monsoon precipitation over the 20th century with medium confidence. And that's consistent with all of the future climate experiments that we make. So that helps give us some confidence in that. But it's also consistent with theory, because theory tells us that if we have a warmer world, then we're going to have more moisture available to the monsoons, and we're going to get more monsoon rainfall. But then this is something that's quite new since the previous report. So this tendency for the greenhouse gas enhancement of the monsoon was overwhelmed by anthropogenic aerosols from the 1950s to the 1980s. So this is really quite a high-level statement that's saying that anthropogenic aerosol emissions are acting to weaken the monsoons at the global level, and particularly in the northern hemisphere. So there is also medium confidence that the intensification of global monsoon precipitation and northern hemisphere summer monsoon circulation since the 1980s is dominated by internal variability. So there's a bit of a recovery in recent decades, and one might assume that has something to do with greenhouse gases, and some part of it might. But actually, there's a lot of evidence also that there are internal modes of variability in the climate system, and Brian mentioned these late in his talk. So decadal changes in the ocean that might help give rise to enhancements of the monsoon. And I'll talk a bit more about that towards the end. There's also some information at the paleo timescales, and I'll not go into that for the interests of time. So just because I've mentioned it, just to briefly mention about aerosol mechanisms. So the reason we're interested in aerosol, and the reason that they have their effect on climate in the way that they do, is that there are these direct and indirect aerosol effects that in some ways both act to reflect solar radiation. So the first is an aerosol radiation interaction. So aerosols, typically sulfate aerosols, they're reflecting solar radiation, and you see a layer here which acts to cool the surface. And so if you were to think about the monsoon in the simplest, most basic way possible, you would think about these very large scale meridional temperature gradients. And so if you're reducing the ability for that temperature gradient to become established, then you're going to weaken the development of the monsoon. And there are also these indirect aerosol effects, the aerosol cloud interactions, that a lot of work has shown also are involved in reducing monsoon rainfall. And the thing about aerosol is it's both local and global emissions that matter. And there's a nice slide I'll show at the end of some of the implications of this going forward over the next few decades. So then thinking about the regional monsoons in the historical period. So this is work that fell in chapter 8. And this is a very busy slide, very busy figure there, figure 8.11 from chapter 8. You can see here the world divided up into the different monsoon regions that we know about, as well as some other regions. And each of these little diagrams is showing these time series of what's happened in observations and models. And so you can see for the case for the South Asian monsoon, we sort of have this somewhat decline and then a recovery over the last decade or so. And these are extremely small, but I urge you to go and look into the report in detail. But what these are showing is the different signals that you get from different forcing agents. So the red box and whisker plot here is if we just force models with greenhouse gases, and this sort of strange sort of green-gray color down here is if we just force models with anthropogenic aerosol emissions over the 20th century. What happens to monsoons there? So what I've said here is that some monsoons feature clear opposing behavior under greenhouse gas and anthropogenic aerosol conditions. So notably South Asia, East Asia, and Australia maritime continent to some extent. So that's really quite a clear distinction between the effects of greenhouse gases or the effects of aerosol on a monsoon. So in the next slide, I've got a summary table of just some of the various attribution statements that are made in chapter 8 about the various different regional monsoons. And don't worry, I'm not going to read all of this out. But for South Asia, we saw this weakening in the second half of the 20th century, and that's been attributed to anthropogenic aerosols. And this is opposing the expected increase in monsoon rainfall due to greenhouse gases alone. For East Asia, that has a slightly different character to the monsoon of India and South Asia, in that, in South Asia, generally when the whole monsoon is weaker, that affects a lot of the country quite uniformly. In East Asia, that's a larger landmass, and the effect is quite different here. So when you see a weakening of the monsoon, it sort of has a withdrawal of the circulation to the south, and so you tend to get a drying north and a wetting south, and that's exactly what's been observed since the 1950s. And the attribution statement there is that, again, this relates to anthropogenic forcing, but they have stated that there's been a role for the Pacific decadal variability in that weakening since the 1970s. And West Africa is also an interesting case. And in fact, if you look in detail at the literature for West Africa and the Sahel, you find this is very interesting interaction between the effects of aerosols and the effects of greenhouse gas emissions. And in fact, there was a very sort of wet period in the middle of the 20th century, followed by a sort of decadal scale drought, so a dry 1970s and 1980s. And what happened at that time, there was a lot of aerosol emissions at that time coming from Europe and North America, and they were sort of spread over, advected over the whole North Atlantic region. So you had this very large scale cooling of that region caused by those aerosols, whereas the equatorial region was heating up due to greenhouse gas emissions. And so you sort of had this shift of the temperature gradient favoring the near equatorial region, and you got a retreat of that monsoon over the West Africa. But with air quality policies and a removal of a lot of those northern hemisphere aerosols, especially over the Atlantic Ocean, into the 80s and 1990s, that North Atlantic has warmed up again, and so it shifted the temperature balance back northwards. And so there's been this recovery in the mid-1990s of the West African monsoon. And then if we get down all the way to the end here, for Australia and the maritime continent, there is some observed evidence of increased rain in parts of North Australia since the 1970s. But at the moment, there's low confidence in human contributions. And this type of thing happens a lot in the IPCC reports. Sometimes we just don't have the evidence yet. And the IPCC is all about assessing the evidence in the literature that is available. So there are plenty of open research questions that can be tackled by targeting model experiments in these areas, for example. So in addition to 20th century modeling, one of the things you'll also find in Chapter 8 is the use of paleoclimate proxy evidence and also modeling experiments of paleoclimate periods. And what they show is that there has been strengthened Northern Hemisphere monsoons in warmer periods of the past. So particularly in South Asia, East Asia, West Africa, North American monsoon, and that's due to orbital forcing. So what about future changes to the global monsoon? So some of this was covered in Chapter 4, and its first message was about what happened in the previous assessment report, so the AR5. So in the AR5, there was no specific assessment of global monsoon changes in the near term. So that's the kind of next couple of decades. But of course, information could be derived from looking at time series and how they've evolved to get there. There was a basic pattern in the AR5 of something which we used to call wet get wetter, or sometimes rich get richer. But there is a large uncertainty in models and different simulations. And I'll not go into it here, but there is a bit of a change to what this means, because it actually matters the distribution of relative humidity in the future. So in the AR6, the global monsoon precipitation is likely to strengthen in the 21st century, with increases in its area and intensity while the monsoon circulation weakens. So that's the sort of headline message. And if we look at some charts of the near term, and what I've got here are the DJF, so the Southern Hemisphere summer, and then JJA, which is the Northern Hemisphere summer. And these are in two different emissions scenarios. And we're looking at the near term, 2021 to 2040. And what I've sort of summarized here is that near-term changes in the global monsoon precipitation and circulation will be affected by the combined effect of model uncertainty and internal variability, which together are larger than the force signal. And you could go away and read the figure caption for this. And there's a lot of quite complex instructions about how to interpret the hatched lines across the figures. But the fact that in all of the monsoon regions, all throughout the tropics, the fact that we're seeing these diagonal lines basically means that we can't get a signal of anthropogenic climate change in rainfall out of the noise. So no robust significant change. That's because internal variability is still dominating when we look at these regional levels. What about the long-term future? So based on CMIP6 models, it is likely that global land monsoon precipitation will increase with the change in global surface air temperature. And that's despite a weakened monsoon circulation. So you can see that here, we've got a measurement of the change in the global land monsoon precipitation. And you can see its evolution over the 20th century. In the models in the historical period. And then after that, we've got this projection forward to the end of the 21st century, which is, you can see, is dependent on emissions scenario, on the SSP that's chosen. And as we get to this very strong, this sort of high-end emissions scenario, we do get a much larger change in the monsoon rainfall. And as I said, this is despite an overall weakening of the Northern Hemisphere summer monsoon circulation, which relates to changes in atmospheric stability. And of course, individual regions have different signals, and we'll come on to that. But we can say that global land monsoon precipitation will likely increase by between 1.3 and 2.4% per degree Celsius of global warming. And chapter 8, of course, has covered this at the regional level for the different monsoons. So these are shown up here. The 3 different colors are just indicating 3 different emission scenarios, which get stronger as we go to the right. And then the 3 different box and whisker plots just go from the near term to the midterm to the long term. So the 3rd one in each case is at the end of the 21st century. And what we see here for these different monsoon regions is that there's a robust and consistent increase in some of these monsoons under the stronger emission scenarios, and of course, further into the future. And that's notable in South Asia, East Asia, and West Africa especially. However, some regions have considerable uncertainty. So you can see that those signals are spread around the 0 line. So no robust change. And that's particularly in the American monsoon regions. So I just thought I'd show this interesting plot that relates to the Indian monsoon. And this is from a paper that's come out since the IPCC 6th assessment report. It's by a German PhD student. And what she has shown very neatly is that there's a clear evidence for linear scaling of monsoon rainfall change when you relate that to warming relative to the present day. So in this diagram here on the left, we're looking at the change in Indian monsoon rainfall with the change in global mean surface air temperature on the bottom axis here. And this is just shown in several different emission scenarios, which are the different colors, and in many different models in the database. And if you just take the multi-model mean for each emission scenario, so there's now one line for each emission scenario, you can see that this relationship is very, very linear going into the future. So, and this is a message that's generally true with many aspects of the IPCC report. You know, every additional bit of temperature that you add is going to make changes happen more so. Okay, so in the case of the monsoon, it's adding more rainfall. So getting towards the end now. So one of the aspects that some in the scientific literature wanted us to consider a bit more seriously in this IPCC report was the idea of the possibility of low likelihood, high impact events. And in fact, a colleague of mine did a fair bit of work in this area. So Rowan Sutton here, he's writing a BAMS paper that says climate science needs to take risk assessment much more seriously. So often when we've looked at climate change in the past, we might think about taking the multi-model mean. So we might just take all of the models together. Let's look at the average about what happens. But that sort of ignores the tails of the distribution, which might incur significant risks to various sectors. And in fact, one can very easily write down a sort of a statement as how you measure risk, and you can say that risk equals likelihood times impact. And this is just a schematic cartoon of you know this diagram here. This first PDF is showing the climate sensitivity, or in other words, the way in which the global mean temperature will respond to a doubling of carbon dioxide. So you can see we have a likely range here. This was at the time of the 5th assessment of between 1.5 and 4.5 degrees. And of course, this becomes increasingly unlikely as you get to these high climate sensitivities. But clearly, if you had a high climate sensitivity such as this, you would have a much greater image or impact or damage if you're looking at various sectors such as agriculture, heat waves, all various sorts of sectors. And so this gives us a rather different risk profile to the original likelihood of the different climate sensitivities. So that's something that the report has tried to consider. And two of the ways in which that is relevant to monsoons is in the area of the Atlantic meridional overturning circulation, and also in terms of supervolcanic eruptions. So There's a statement on the Atlantic meridional overturning circulation. So this is one of the very large-scale, multi-decadal overturning circulations in the ocean. It drives a lot of heat northwards that wouldn't otherwise be there. And the findings of the IPCC assessment is that this circulation is very likely to weaken over the 21st century for the very different emission scenarios. But there is only low confidence in the magnitude of the trend. And the experts in this area have said that there's medium confidence that there will not be an abrupt collapse before 2100. But here is the sort of the risk part. If such a collapse were to occur, it would very likely cause weakening of the African and Asian monsoons and strengthening of the Southern Hemisphere monsoons. So this is something that, you know, it's not in line with the stuff about greenhouse gases and the monsoons getting wetter. It's just it's like a different storyline of what could happen if we did have a complete collapse of the AMOC. And the other area is in the effects of supervolcanic or very large volcanic eruptions. And this was actually assessed in a cross-chapter box in chapter 4. And you can read a very nice little piece on that there. And it states, it is likely that at least one large eruption would occur during the 21st century. Such an eruption would reduce the global surface air temperature relative to that time for several years. Although, just to give a caveat here, it will still be warmer than it is now. And that will give a relative decrease in the global mean land precipitation. It will alter the monsoon circulation and so on. And it's not as simple just to say that the monsoon will weaken, because it depends where that volcanic eruption occurs. If it occurs in the opposite hemisphere, then it will actually act to strengthen the monsoon. So this is just an example of some of these low likelihood, high impact events. So getting towards the end, just to give a bit of a brief sort of coverage of the technical summary. So there was a nice monsoons box, a 2-page box in the technical summary that gave the sort of headline messages for all of the monsoons. And basically what you can see in the diagram here for the different monsoon regions is a combination of greenhouse gas and anthropogenic forcing has been fundamental to driving changes in the regional and global monsoons in the past. But internal variability does also play a role. And I'll say a little bit more about that in a moment. But what we can see on this diagram, I've just highlighted South Asia there, that in the past, we might have had, if it was just greenhouse gases, we might have had increases in the monsoon. If we just had aerosol, we've had decreases. And add those two together, and we've sort of had this overall decrease in the monsoon rainfall. But the projections for the future of the Indian monsoon, and there's just this one emission scenario showed here, are for increasing rainfall out to the long term. So just what does that technical summary summarize about the monsoons? So global land monsoon precipitation decreased from the 1950s to the 1980s, partly due to aerosols, but has increased since then in response to greenhouse gases and also large-scale multi-decadal variability. And especially those northern hemisphere aerosols have been implicated in the weakening of some major monsoons in South Asia, East Asia, and West Africa in the second half of the 20th century. And these have therefore offset the increases that we would have expected due to greenhouse gases. And during the 21st century, the land monsoon precipitation is projected to increase in all scenarios. And that applies equally to South and Southeast Asia and so on. And then just to sort of finish there at the bottom, at global and regional scales, near-term monsoon changes will be dominated by the effects of internal variability. And I have a slide on that in a moment. So what else? There's a lot of things I've not discussed here. This was a nice cartoon I saw in Down to Earth magazine a few months ago. And you'll all be familiar with this problem, that in parts of India, you might be having floods, whereas other areas might be having droughts. And so this man up here, somehow in control of the cloud, is saying, let me divide it in equal halves for you. And of course, we know that doesn't happen. And sort of what I'm trying to get at here is that the monsoon is not something that's a uniform seasonal mean phenomena that happens everywhere all the same. We know from this IPCC report and others that we're going to have this intensification of the water cycle. We're going to have increased heavy rainfall extremes, longer dry spells, heat waves, and so on. So I just wanted to finish the talk with looking at three sort of major uncertainties going forward. The first of those is on the effects of internal variability that I alluded to in the near term as to being important. And we studied this quite a bit in chapter 10 of the IPCC report, and you can read more about it there. And it's the concept of interplay between internal variability and forced change. So the forced change being that sort of induced by greenhouse gases or aerosols or whatever. And what we have now in recent years compared to the previous report is that there are some new experimental designs around which help us understand regional climate variability and change. And these are based on the design of what's called the single model initial condition large ensemble, or the SMILE. So in this case, you take a single model, in this example, the MPI model, and you force it with many different ensemble members, 100 members, and you run those experiments for the 20th century and for the future period, in this case under the RCP 8.5 emissions scenario. And the fact that you've got this large ensemble gives you a PDF of outcomes, both over the 20th century and into the future. And you find that there's a lot of different variability in that, particularly in the oceans. So you get different phases of the Pacific decadal oscillation. You might get different phases of variability in the Atlantic Ocean as well. And how those different oscillations evolve also has some bearing on the monsoons, and there's a lot of work in that area. So this particular study was by a Chinese PhD student, Jin Huang, and she did this experiment and she applied it to the Indian monsoon. And what she's looking at here is the sort of future precipitation trend ensemble mean in the near term, so out to 2040. And that's showing the monsoon getting wetter. Okay, there's nothing unusual there. But if she looks at the driest 10 members out of this 100-member ensemble, or if she looks at the wettest 10 members of that 100-member ensemble, you get very different climate change signals. And that's illustrated in the time series here that I've blown up. So clearly, if you go to the end of the 21st century, this forced signal is dominating. But out to the near term, the internal variability matters, and you can actually either sort of enhance the greenhouse gas effects, if you like, or you can ameliorate them, just depending on what that phase of internal variability is. And so for an individual region of interest, the near-term climate projection must take account of internal variability. The second issue I wanted to raise for the near-term future is, what about aerosol emissions? So unlike greenhouse gases, which have a very long lifetime in the atmosphere, and of course that heat gets trapped in the ocean, aerosol changes are very rapid. So if you cut off the supply of aerosols within a matter of weeks, those aerosol burdens in the atmosphere will have come out. You'll have changed the aerosol optical depth. And so policy choices in the future could help determine near-term changes in the South and East Asian monsoons. And this is just an example from a recent paper by Bjorn Samset and colleagues about the emerging Asian aerosol patterns. And this is a trend in observed aerosol patterns over the Asian monsoon region between the late part of the 2010s and the early part of the 2010s. And this is observed from the MODIS Terra satellite. And what you can see here is a relative reduction in aerosols over China and a relative increase over India. So there's this sort of dipole pattern of change. But this is relevant then to also think about the future. So the future projections are based on these different SSPs. And these SSPs take different assumptions about how air quality might be in the future, with strong air quality policies in which black carbon and sulfates are in decline everywhere, or with medium or weak air quality policies in which there might be quite distinct regional patterns. And so clearly that could have an impact on the monsoon rainfall that might diverge between what happens in India and in China.
Sorry to
point,
interrupt.
Yeah.
Professor Turner, we are almost running out of time.
Okay.
So could you please conclude?
Yeah.
Thank you.
Thanks. Yeah, so this is the last slide. So persistence of GCM biases, basically the biases have not gone away. So the latest CMIP6 model biases are not especially dissimilar to earlier CMIP5 and CMIP3 models. So this diagram here from Bock et al. 2020 is just showing the annual mean rainfall in the multi-model mean of CMIP6 and then in its bias against observations. And what you can see here is drying over South Asia, a wet Indian Ocean, and that is the same signal that's been present in the CMIP5 models and in the CMIP3 models, so going back well over 10 years. And unfortunately, at the current GCM scales, it's not a simple matter of just increasing model resolution. That's not an instant solution to this problem. You can see here that in this set of model experiments known as high-res MIP, a comparison of the high resolution and low resolution models has quite a similar bias pattern over the Indian monsoon region. So to summarize, monsoons are changing in complex ways. Future projections of increased rainfall for global and South Asian monsoon, they scale with global warming. In the near term, internal variability is likely to dominate. For the Asian monsoons, aerosol pathways in the future are also going to be important, but model biases are a long-standing issue. So thank you very much for your invitation and for your attention. And I'll take any questions either now or you can get in contact with me as well. So thank you very much.
Thank you so much, Professor Turner. It was a very elucidating talk exposing the effects of climate change on global and regional monsoons. Unfortunately, we are running out of time, but I think we will take one quick question that has already come here. It is from Umesh Prasad Verma of MET University, Jaipur. His question is, does the climate change gradients confuse the forecast and predictability of seismic event? Seismic electric signals and VLF propagation will be hindered in terms of rate of intensity as corresponding to gradients variability for monsoon precipitation. So he's basically concerned about the seismic events.
I have to say that's a topic I know absolutely nothing about. I don't think, and certainly not in the IPCC report, it's not something that's dealt with, is the effect on seismic events. If I was to say any answer to that comment, clearly with heavier rainfall and so on, there's going to be far more landslides. But in terms of seismic activity, I can't comment on that because I don't have any expertise in that area at all. Thank you.
Okay, one more question by the same person. Are climate change consequences man-made or natural? If natural, how can its effect be minimized? Will aerosol cloud interaction be affected by greenhouse gas flux at regional basis? So it's a general question.
So the IPCC report states that it's unequivocal that climate changes are man-made, and it's clear from the IPCC Sixth Assessment Report that climate signals are now apparent in every region on Earth, with a human contribution to those changes. So there's really no longer any disputing that. And I suppose the other key message to get across is that with every additional degree of warming in the future, the climate impacts are going to get worse. So that gives us a strong motivation to make sure that we stop emitting greenhouse gases and try and bring this situation under control.
Okay. Okay, thank you so much again. I'm sorry we have to stop the questions here. I'm sure they can come offline and ask you the questions. So let me take this opportunity. I, along with thanking Dr. Jayaraman also, who supported me, and for the excellent talk, as I mentioned earlier. These are very interesting topics, especially as far as India is concerned, because of our dependence on the monsoon, the regional and the global monsoon, especially, you know, how it affects and all that. Thank you so much. I think I hand over to the organizers now.
Yeah, first
Dr. Jayaraman, would you like to have?
No, yes, it's fine. It's fine.
Okay. First, I would like to thank the two speakers, Professor Andy and Professor Brian. I think has given excellent two talks, and it is very useful for especially for our young researchers in this week. So we, on the behalf of the organizing committee of the Indian Meteorological Society, the INTROMET-2021, we would extend our sincere thanks for both of them. Of course, the chair, Dr. Jayaraman, as well as Dr. Radhika, has done extremely well. So we are also thank you for accepting our invitation and attended this, sharing the two sessions and the correct time. Okay, thank you, Dr. Jayaraman and Dr. Radhika for attending. Thank you all.
Thank you so much.
So there is an announcement. We'll be reassembling at 11:30 at all respective halls for the technical sessions. Thank you.
Thank you.
Hello.
Hello, sir.
Yeah, I'm audible.
Yes, sir.
Okay, fine.
Hello, who is the organizer? Abhilash is there?
Okay. First we will check and we will start.
He will take only 1 or 2 questions. So, Rukumar Pulli, Doctor.
Hello?
Can you hear us?
Yes.
Yeah. Sadin Behara, can you hear us?
Yes, can you hear me?
Yeah, we can hear you.
Okay,
Thank you for
How
joining.
are you?
good, good to see
Good
you.
morning. Good to see you.
So we will be starting the session soon. We are waiting for some
Hello.
speakers.
As
Good
Dr.
morning, Dr.
Rukumar
Behra.
mentioned in the chat, are you taking the questions from the chat box or
Yeah,
directly?
we will be taking that, but I think we will have time for maybe 1, maximum 2 questions.
Okay.
So, welcome all to the technical session technical session 2A of INTROMET 2021. So the session is on changing climate, observation, attribution, and model projection. So this session is chaired by Dr. Rukumar Kolli and Dr. Sadin K. Behra. Dr. Rukumar is the Executive Director of International Climate Monsoon Project Office, hosted by Indian Institute of Tropical Meteorology, Pune, India. He has good teaching and research experience, specialized in climatology and hydrometeorology. Prior to this, he had served for 13 years at WMO Secretariat, Geneva, Switzerland, as the Chief of World Climate Application and Service Division. He made significant contribution to development of regional climate centers and regional and national climate outlook forums. The second chair is Sadin K. Behra. He's the Director of Application Laboratory in Japan Agency for Marine Earth Science and Technology, JAMSTEC. He also serves as an adjunct professor at Department of Ocean Technology, Policy and Environment at University of Tokyo, and as a guest professor at Graduate School of Global Environmental Studies in Sofia University. In this session, we have a lead talk by Dr. K. Rajendran. Dr. K. Rajendran is a senior principal scientist at CSIR 4th Paradigm Institute, Bangalore, India. So his talk will be followed by Dr. Sabin TP and Dr. Suraj KP. Both are scientists working at Indian Institute of Tropical Meteorology, Pune. Dr. Sabin's expertise is in high resolution climate modeling and variable resolution modeling of present, past, and future. Dr. Suraj's areas of expertise is Indian monsoon variability and its response to climate change and predictability of tropical climate. After the lead talk and invited talk, we will have 5 more short oral presentation. The lead talk is for 20 minutes and additional 5 minutes for discussion. Invited talk is for 13 minutes and 2 additional minutes for discussion. And short oral presentation is for 9 minutes and additional 1 minute for discussion. So we kindly request the speakers to comply with the time allotted. Selected questions in the chat box will be conveyed to the chairs. So now may I request the honorable chairs to kindly take over the session. Thank you.
Thank you very much for that nice introduction. Good morning, friends. It's a pleasure to support the INTROMET session with my good friend, Dr. Behra, the association with whom actually dates back to several decades since his time in IITM. So it's a pleasure. And today's session actually is the core of science of climate change. Observations, attribution, and model simulations and projections. I think we have a very important topic that is to be covered in this session. We have eminent speakers leading the session, and also a number of oral presentations. We have a very tight schedule. We have about 105 minutes, and almost everything is taken up by the presentations. And I hope all the presenters are available here. So I invite my co-chair, Dr. Behra, to say a few words, and then we can get started.
Thank you, Dr. Rupkumar. It is a pleasure actually to see you. And as you said, we have long associations. And you already kindly introduced the theme of this session, and we have really good speakers, as you said. And I'm looking forward to hear all those talks, to an exciting session as well. Thank you.
Okay, we have the first lead talk by Dr. K. Rajendran from CSIR Fourth Paradigm Institute. So he is going to give us the lead talk on the progress in the simulation of the Indian summer monsoon, variability and teleconnections over different generations of IPCC climate models. Of course, there's nothing like IPCC models, but these are all CMIP models, of course, but they are in support of IPCC, although we can call them IPCC climate models. I think this is a very interesting topic, which helps us to understand how rapid progress we have been making over the past few decades since the IPCC inception. So I'm really interested in looking at what Dr. Rajendran has in analyzing the progress. Dr. Rajendran, the floor is yours. We have 20 minutes, and we'll leave about 5 minutes for question and answers. Dr. Rajendran.
Yeah, hello. Am I audible? Thank you, Chairman. It is on the outset, I would also like to thank INTROMET organizers for inviting me to give this opportunity. Okay, let me just start my talk. Is my slides are visible?
Yes.
Okay. Yeah, my title is already a little lengthier one, because I just wanted to talk about what are all the major progress in the simulation of Indian summer monsoon and its variability and teleconnections over different coupled as well as atmosphere alone models. So I have included AMIP as well in this analysis. Oh, my slide on its variability. So as you all know, because it is so essential for understanding the monsoon processes and simulation of monsoon characteristics. And also it is essential for predicting monsoon and its variability, for building the confidence in projection and obtaining a reliable climate change information, which is crucial for impact studies. Okay. So just before showing my results, I will quickly go through some of the background, which is known to many of you, but still I am just listing out few. In the beginning of modeling era, that is in the early 1970s or mid 70s, the simulations of Indian monsoon address seasonal variation of circulation and role of mountains and mean features, especially the great work from Manabe, 1974 and 75 with a series of papers. Then comes to first notable model intercomparison study showed that many models were able to simulate the circulations very well than rainfall distribution. Especially the rainfall distribution has major lacunae over the orographic region. Then comes to the other aspects, because of as the modeling studies involved, the simulations were found to be so sensitive to various parameterizations used in the model, and also the impact of soil moisture and vegetations used in the model. And there are series of studies, only a few studies I have noted here. Another notable feature was the orographic effect of Tibetan plateau, because again, those period it was considered, and that also it is so important because it is an elevated heat source for the Indian summer monsoon. And subsequently, another important aspect, that is the slowly varying lower boundary condition, that is the SST, is found to be so crucial and influencing monsoon simulation. Then there is a monsoon numerical experimental group have planned for an intercomparison study, which also showed significant rainfall biases, but major focus was to simulate the year-to-year variability, especially for the major excess and drought years. Of 87 is a drought year and 88 is an excess year of monsoon year, and which was captured by many of models which was participated in that program. The mean state was found to be a crucial, most an important aspect, which is also brought out in all these analysis. So by the end, in summary, it has been in a position that ability of this model to simulate the mean monsoon is became a critical benchmark to qualify reliable simulation of tropical climate variability. Okay, then comes to the second phase of MONET, in which the model intercomparison project is well planned, and also observed climate is assessed through a standard set of experiments. And as a result of this, and this first AMIP-1, a set of models and simulations were available to the scientific community. Basically, this is a very short duration at that time. It is only for 10-year period, but with the same SST forced by different models. And one of the notable study which I wanted to show here is by Sperber and Palmer, who suggested that importance of better simulation of mean summer monsoon rainfall over India for simulating the IAV of ISMR. Then there is another notable study by Gargil and Sajini. They showed that it is important to better simulation of mean seasonal variation of the major rainbelt for the Asia Pacific region to achieve realistic simulation of IAV. So in mid 90s, WCRP initiated the coupled MIP, that is the ocean and atmosphere together, which was developed from atmospheric components came from AMIP-1. And basically the designs of CMIP-1 and CMIP-2 was simple with the long control simulations, but the major the change came in the CMIP-3, which had an elaborate 20th century simulation, and output of AMIP-3 and CMIP-3 were made available to the scientific community at large for various studies. And again, I just wanted to suggest that in this also there is a paper by Rischler and Kim suggested that among the three the generations of CMIP-3 is better in various aspects of the monsoon simulation. Okay, by this time, meanwhile, the major factors behind the IAV of ISMR were identified as: one is the El Nino Southern Oscillation over the equatorial Pacific, and the IOD and the related equatorial Indian Ocean oscillations. Okay, the inverse relationship between ISMR and ENSO, with ISMR deficits often associated with El Nino, as extensively studied since Walker and Bliss, and later by Sika, and after that many studies. And the ICINO has been shown to impact ISMR with its positive phase favorable for Indian summer monsoon rainfall by the study of Gargil et al. 2004. And later on, very recently, a composite index derived through the bivariate analysis of ENSO and this equatorial Indian Ocean oscillation indices against ISMR was found to explain about 54% of ISMR variance, and was better correlated with ISMR excessive, especially for extremes. Okay, now comes to the fifth generation of CMIP-5, which includes idealized processes and feedback-oriented experiments whose output facilitated further understanding of the climate system. Again, there is a very important study by Sperber and analyzed the CMIP3 and CMIP5 models and found that CMIP5 multi-model ensemble outperforms that of CMIP3. Which is in the study found that is on almost all diagnostics used in the analysis, especially during the boreal summer monsoon season, shows the similar result. They also documented that the lack of sufficient skill in the event of in even the most sophisticated CMIP3 and CMIP5 model in simulating important aspects of ISMR and its variability. Whereas recently, WCRP came up with a CMIP6 model in which more than 60 global models were participating, and the data is available to the scientific community. So in this background, it is important to ask how much the climate model have improved over the past 20 years, 25 years, or how far we can trust this latest generation of coupled model, especially the CMIP6 in simulating ISM or the Indian summer monsoon, which is crucial. As we have learned from many of the previous talks, that prediction and future of the projection, which also the ISM monsoon simulation is also an important factor. A diagnostic assessment of the simulation of mean and internal variability of ISM R by CMIP6 model is thus relevant and important. This is the major objectives which we were focused in this present study. What we were trying to see is how the CMIP6 models in representing the climatological mean Indian summer monsoon rainfall compared to its atmosphere alone counterpart, that is AMIPS, and with this previous generation of AMIPS, starting from AMIP1 to 3, 5, and CMIP3 and CMIP5. As you know, each generation of MIPS is expected to have a range in performance, but it is necessary to understand the general improvement across different phases. For this, the one way of seeing is since the data volume and is so large, the one way of doing it is multi-model ensembles, means and mean characteristic analysis. The second aspect we looked into is how is the annual variation of Indian summer monsoon rainfall represented, especially in CMIP6 models, and how good the teleconnections in especially with ENSO and the Equatorial Indian Ocean. As I mentioned, this is I'm not going to spend more time here because we have used the various generations of the model, starting from AMIP1 to AMIP6 and CMIP3, with the number of models are increasing from AMIP1 to AMIP6, and same way in CMIP6 as well. We used several reanalysis products as well as the observational rain measurements from various sources, and including IMD data. And then we have used the Hadley SST data for the comparison of the SST simulation by coupled model compared with observation. Then we also see the cloudiness and ERA reanalysis data. Let us come quickly on the mean rainfall simulation as well as the wind simulations in these two models and how it compares with observation. I will come to AMIP in the next slide. Now, at the top, what you have seen is the observed rainfall in shade, and there are purple contours which represent the SST, and the wind is represented by the vectors. So, and the bottom panel is the multi-model ensemble mean from the CMIP6 simulations. And what we can see here, the model by and large captures most of the major rainfall, but there is a systematic dry bias over the core monsoon region, that is over the central Indian region. And another important factor is over the western equatorial Pacific, where you could see in the top the purple SST contours are shrink in the CMIP6. That shows that there is a very large cold bias. Okay, now only change is in the bottom panel. Now this is the respective AMIP6 simulations, and here you can see that because here the boundary forcing is SST, is observed SST, so SST is same, Only difference what you need to see is in the shaded contours, that is the rainfall. What you can see in the EMIP simulations are giving more rainfall over southern peninsular region, or the western orographic rain is over simulated in the EMIP6 model. So which will be finally contributing, if you compute Indian summer monsoon all India average, this quantum of rain will compute and you will contribute, and you get a larger magnitude of ISMR. So next, which has been widely discussed already by previous talks as well, this is the mean bias from CMIP6 and AMIP6 multi-model ensemble means. And again here shades shows the rainfall bias, and the contours shows the SST, and this is only significant difference is plotted here. That is why it is patchy. And what you can see in the central Indian region, there is a large dry bias in CMIP6, which is almost persistent, but slightly weaker in this. But you could see that southern peninsular India get larger volume of rain for EMIP6. Whereas the similar cold bias you can see in the West Pacific on top panel, the contours of SST is much about 0.22 degree difference you could see. Okay, now as I mentioned, the number of models we started analyzing is about 60. For presentation purpose, I am just showing only 15 models. That 15 models we have arrived by taking into the model selection criteria. Basically, what we have seen is the spatial pattern of climatological June to September rainfall over the Indian region, and how the models are able to represent the better interannual variation of ISMR. This has been achieved by through considering the pattern correlation. We have considered two type of pattern correlation. That is, one is over the Indian landmass and one is over a broad region to take care of the both oceanic ITCs as well as the land ITCs. And we have also considered the spatial standard deviation, centered pattern, RMSE, and mean bias. In addition to that, for the temporal, the coefficient of variation, by using the temporal mean on standard deviation divided by the temporal mean over a period of 60 years, we have considered for this one. So just to give a flavor, I wanted to show how these CMIP6 models are climatological June to September rainfall simulation over Indian region from various models. What is important is on the left side, the first three panels are different observations, and the first two is IMD and the other two are land-based, gauge-based observation, and then GPCP. And I also show how good the 15 models which we have selected based on the previous criteria compare well with observation. So the models are better able to simulate, or maybe the mean pattern is much more closer to observation. And the other 15 models which is included is the members of this multimodal ensemble of the particular group. And remaining models are, shows a wide spectrum of monsoon simulation, because some models are completely dry over India, which is given at the last. And some models is able to generate certain rainbelts, like the continental rainbelt. Some may be able to simulate the oceanic rainbelt as well. Okay, there is a one way of concise all these things to a single figure, that is the Taylor diagram, and which has a lot of information, but we can see that the one way of doing is the pattern correlation, which can be seen in the azimuthal direction, and the radial direction, or the radial thing, will be representing the standard deviation. And there is a bottom, there is a symbol IMD, and there is a semicircle which is going above IMD that will represent the bias in the model. And there are different symbols, and also there is an arrow mark which is showing downward and upward. Downward means there is a dry bias because the bias in the model is negative, and there is a length of the arrow represents different percentage of bias. By and large, we can see that CMIP6 model shows a large dry bias over the Indian region. And what is notable point is from CMIP1, CMIP3, 4, 5, and 6, there is a considerable or the improvement in the simulation of Indian summer monsoon in terms of standard deviation, mean, and bias. And the same is slightly lesser in AMIP, but that the similar trend of progress is also can be seen. And also I have put several black dots, that is the different observations, which observations themselves differ each other. That may be because of the different method or interpolation scheme, and the number of observations also matters. Okay, now the mean monsoon rainfall, there's the same thing I am showing in a slightly different way using the box whisker plot, in which I have put CMIP6, MIP6, and then CMIP5 and 3 and 1 in the single plot. And here what you could see, the line represents minimum and maximum, and box represent the first quartile and the second quartile, which is nothing but median, and the third quartile. And same thing is done for every the generations of the model. And you could see that from MIP3 to MIP6, there is a systematic increase in the pattern correlation, which shows that the patterns are better captured. And the improvement is much more visible in CMIP6 compared to CMIP5 and CMIP3. And on the right side, what I have shown is the mean summer monsoon simulation, and it's the axis is in the millimeter. What you can see
5
that.
minutes.
Oh, okay.
Yeah.
So I will just keep that, which is already summarized there. Now let us come to the teleconnection pattern. What we have is understood. This is the teleconnection pattern between observation, especially the Indian summer monsoon rainfall over the rainfall over different pattern and the rainfall over everywhere. Second panel shows the SST and SST and with rainfall, which shows there is an opposite relationship between the Pacific and Indian monsoon region. And what is important here is the SST relation and ENSO rainfall relationship is opposite with the ISMR relationship on the top panel, but everywhere except over the Western Equatorial Indian Ocean, where the sign is same. Okay, so why it is important? Because that shows that Indian summer monsoon is positively related to the Western Equatorial Indian Ocean. This aspect is simulated by some of the models, but it is generally weak compared to observation. That can be seen in the inset figure here. Okay, the next aspect is the ISMR-ENSO relationship. So this is very important. What we have shown here is the All India summer monsoon rainfall average, the rainfall from year -1 to year 1. And the black line is representing observation. And I have shown only 15 models, which shows that the rainfall in observation, the correlation peaks during the monsoon month, and especially towards the later part of the monsoon, whereas in the model, which peaks much earlier, and also it is over amplified. And another important aspect is the IOD, which is known, and how these models are able to simulate the IOD. What we have done is the standard deviation of the Indian Ocean Dipole Mode Index for every month from all this model. And what you have to see is observations towards the end, but the models have a general tendency of over amplified dipole structure simulation in many of these models. And CMIP6 and CMIP5 more or less similar, whereas in CMIP6 you could see more number of models, but also the one more aspect is the IOD index peaks towards the later, means it is onset is occurring during the monsoon, then peaks after the monsoon and decay in the winter. whereas in the CMIP6, it peaks much earlier. Okay, so that is one of the aspects which we have seen, and also the teleconnection pattern. What we have seen, the IOD and ENSO relationship is much stronger in the CMIP5 and CMIP6, whereas the relationship between IOD and ISMR is much smaller. Even in the observation, it is weaker, and the model is slightly over amplified because the dipole structure is able to capture, but many times many models shows a opposite sign in that. So this is the other aspect which I have mentioned, that is the IKINU, which is known to be the counterpart of IOD. Here, as we have known that over for example, the negative IOD is the usual period where climatologically SST over the Eastern Equatorial Indian Ocean is positive, and here the Western Indian Ocean is negative. Then there is a westerlies, whereas during some years this will get reversed, and that is positive years, in which period the equatorial easterlies, westerlies become easterlies. So the IKINU index is basically based on the surface equatorial the wind anomaly. So based on that, how this CMIP6 models were able to capture this ISMR IKINU relationship in the model. Some of, for example, the right-hand side, what we have shown is the East Equatorial Indian Ocean PRN, precipitation anomaly, and the scatter plot between the east and west, which shows the dipole kind of a structure. So the dipole structure observed correlation is minus 0.54. A couple of models were able to get the similar one, but not in the but the relationship between the Western Equatorial Indian Ocean and Indian summer monsoon is much weaker, and it is slightly strong in the convection, that is in the OLR, but in rainfall it is much more weaker. Whereas some models, some of the CMIP6 group models capture this inverse relationship between Western Equatorial Indian Ocean and East Equatorial Indian Ocean rainfall, but correlations are much weaker, as I mentioned. This is similar with CMIP5 models as well. Whereas in in observation, an index of IKINU is strongly correlated to ISMR, explaining about 19% of ISMR variance. But none of the model is capable of simulating the significant positive correlation between IKINU index and ISMR. Many tend to simulate an inverse relationship. So this might be a major reason why models fail to correctly capture the observed interannual variation of ISMR. Okay, so in summary, what we have seen, there is a theoretical understanding, improved physical parameterization, and increased number of observations and the computational capability, which leads to the complexity of climate models substantially increased, and current models are far more superior than models of 90s. And correspondingly, the ability of climate models to simulate major characteristics of climatological summer monsoon over India, the interannual variability of Indian summer monsoon rainfall, and its teleconnection with ENSO, the dipole structure of IKINU, all these features are improved from generations from the 1 to AMIP 1 to AMIP 6 or CMIP 3 to CMIP 6. So this systematic improvement is much larger or best for CMIP 6 models. But as I mentioned, there are the model understanding or the theoretical understanding is improved, but still there are parameterizations, and as and when models are getting more and more complex, more and more process models are added to it. But how these process models are inducing errors or how these errors are compensated is not yet answered. So that also causing shows that there is a further room for further improvement in the Indian summer monsoon simulation. And another aspect is the resolutions of this model. It is still on 2 degree framework we have done. So better, higher resolution models may give a better simulation, though the CMIP6 high resolution model intercomparison project shows the pattern doesn't show much difference, but maybe then it suggests that other process component may also contribute to that. And very important aspect which we wanted to highlight is most of the models are not able to simulate ISMR-ICNU relationship. So once we are able to understand that further or able to get that relationship in reasonable way, we hope we can further improve the simulation of Indian summer monsoon rainfall. Thank you. Most of these results are now got published in one of the recent paper in Climate Dynamics. So the reference is given below. Thank you. I stop here and I would like to take questions.
Thank you, Dr. Rajendran. And since I don't see any question in the chat box and we are running behind the schedule, so what I will suggest is probably any questions can be put in the chat box and maybe you can reply to them in the chat box.
Okay.
Thank you. So our next speaker is Dr. Sabin from IITM. I think he is well known to this community, so I don't think I'm good to introduce him. And he is going to speak about the climate change, monsoons, IPCC AR6 assessment of regional monsoons. So various aspects are included in that, climate change, monsoon, and probably we'll continue to hear what we heard from Dr. Rajendran just now from Dr. Sabin. Dr. Sabin, please.
Yeah, thank you very much, sir. Hope I am audible.
Yes, very much, yes. Thank you.
Yeah, thank you, chairs, and thanks to the organizers for the invitation. Good morning, all. This talk will try to cover the state and status of regional monsoon and its future projections. So if we observe the trend in seasonal mean precipitation for the last 5 to 6 decades, we can clearly see that the most striking patterns are the Sahelian drought and the weakening of Indian summer monsoon and the north-south asymmetry in East Asian monsoon. But however, these patterns are changing, especially in the recent decades. So if we reproduce this trend for the most recent period, that is from 1979 to 2014 or so, you can see that there is a clear signal of recovery of African monsoon, and the weakening signal of Indian summer monsoon is confining only over the North Indian plains. However, the north-south asymmetry enhanced over the East Asian monsoon region. Now, if we want to compare this with how the CMIP6 models are, whether they are able to capture these type of signals or not. So the upper panel is the trend from CMIP6 ensemble mean from 1979 to 2014, and which is taken from all-forcing or historical simulation. The lower panel is from the observation, that is from the CRU for the same period. Here you can clearly see that the CMIP6 models are mostly able to reproduce this enhanced precipitation over the African region, and mostly able to reproduce the declining signal over this North Indian plain. And however, the north-south asymmetry over this East Asian region is not yet reproduced. Dr. Rajendran sir gave a detailed explanation of the bias and all those things in this model. But however, you can see that over the equatorial American region also, the declining precipitation, comparatively, it is well captured by the model if you compare with the observation. North American region also captured almost okay. So in general, we can say that the CMIP6 models are able to capture most of the prevailing patterns what we were experiencing in last 3 to 4 decades. The traditionally monsoon is defined in terms of the seasonal reversal of prevailing wind structure. It was the first attempt, mostly came in 1971 by Ramage. So what he did was he mostly considered the wind, if the wind shift between the winter and summer is more than 120, that region is mostly considered as the monsoon region. So according to this wind criteria, if we confine, the yellowish shaded regions where only can be considered as monsoon. But we know that monsoon-like precipitation is occurred over this North American region and South American sector also, which Dr. Andy Turner was also mentioning in his morning talk. So in order to include all these things, Bin Wang, Kitto, and many others proposed the idea of global monsoon perspective, in which simply they computed this based on summer minus winter precipitation. If it is exceeding 2.5 mm per day, and if the total summer precipitation contributing more than 55% to the annual rainfall, that region can be considered as the monsoon region. So in this method, if you follow, all these red dotted regions in the upper panel can be considered as the monsoon region. Mostly in AR5 assessments, this was the criteria which was mostly accepted or mostly followed. But however, there was slight differences over certain regions. For example, the lower panel is the new IPCC AR6 monsoon domains, which we developed for the AR6 assessments, especially for the chapter 8. And you can see that especially this North American monsoon region, which is denoted in the purple color, was mostly out or not mostly considered in the AR5 assessment region. And the precipitation receiving over this equatorial American region was not monsoon type precipitation. So there are a lot of information, a lot of literature suggesting that this South African rainfall is also not something like a monsoonish type of rainfall. So what we did is that we redefined the monsoon domains by incorporating the regional information that provide more accuracy in selecting the boundaries more perfectly or more acceptable way. So for example, if we examine the literature, we can see that the West African monsoon never crossed this 30-degree east latitude, longitude belt. However, in the AR5 assessment, it was spreading towards entire this east of African continent. And over over South American region was also there was certain mismatch. So basically, we redefined all this monsoon region in AR6, including all the regionally available, incorporating all the regional available information in terms of published literature. And using this, we made critical evaluation of all the monsoons, which is so one more point I just want to mention that these two dotted regions, Equatorial America and South African monsoon, we just assessed as this region received huge amount of precipitation, but these are not termed as monsoon region, but all other 6 shaded regions are we denoted as monsoon regions in our assessment. So first we can just see how the northern hemispheric monsoon, which is in the JJA season or the boreal summer season, respond in last 1951 to 2014 period. The time series is showing the color time series from the observation, and the black line is the precipitation anomaly from the CMIP6 model, where you can clearly see that if you focus over the South Asian monsoon region in the middle panel, if you focus, you can clearly see that the models are able to capture the declining signal at least till the beginning of 2000, and then there is a slight enhancement in precipitation over South Asia. And West African monsoon region, if you focus, the observation showing a sharp declining signal till at least 1993s, and then after that there is a reviving is clearly visible, but models are not able to capture this declining signal at the initial phase, but later the reviving is well captured by the model. So in a way, we can say that most of these aspects of these long-term changes are well captured in this CMIP6 model. And the upper panel, which is demonstrated as the box whisker, is from the detection attribution perspective from the CMIP6 experiments. Here, what we plotted is that trend in precipitation from the respective experiment, where you can see that this red box whisker is from the simulation or from the models, which is only forced with greenhouse gases. And so you can see that the precipitation would have been much higher if the models were only forced with the greenhouse gases, whereas the green box whisker is from the aerosol only simulation. So what it means is that if you see the mean precipitation from this dotted precipitation, these dots denotes the observed trend, and whereas this black is from the historical simulation and the blue is from the historical natural. So basically all historical natural simulations, you can see that there was not change, which is somewhat near to the zero line, and the mean is mostly modulating between the black box whisker. If you focus, the mean is mostly modulating between the greenhouse gas and aerosol, and which is dominating. That is the most crucial factor, which is mostly acceptable in East Asian region, North American region, and everywhere. But West African region, you can see that even in greenhouse gas and in aerosol experiment, the precipitation seems to be increasing. I will come to that point in the next slides. Now, just let us see how the southern hemispheric monsoon is behaving. For this, the season will be obviously DJF season for South America and South African precipitation region and Australian maritime continent region. This equatorial American, again, it is in the northern hemisphere. So this precipitation is from JJS season. You can see that Australian maritime continent region, the precipitation seems to be declining till at least 1990s, and then started a recovery. South African precipitation region showing a moderate decline, and after that there is a slight increase in signal. However, the South American precipitation having huge multi-decadal type of variation, so the changes is also not clearly visible. The equatorial American precipitation region showing a clear decrease in precipitation. From the detection attribution point perspective, we can clearly say that almost this increasing or the recent increasing signals are mostly attributable to the greenhouse gas related enhancement in precipitation. So from the spatial analysis of trend in aerosol only experiment shown in the upper panel, we can clearly attribute the decline in precipitation over South and East Asia to aerosol in the atmosphere. Whereas if the model forced only with the greenhouse gas, the precipitation would have been increased over this region as shown in the lower map. So we can say that the possible precipitation enhancement due to greenhouse gas is mostly offset by the presence of aerosols so far at least. However, now we can see that over African region, precipitation already started recovering. If we investigate the concentration of aerosol, this will be clear. So shown map is the concentration of the sulfate, black carbon, and organic carbon aerosols from 1850 to 2100, where we can see that till 1990s, aerosol was increasing, and afterwards the concentration stabilizes till at least 2000s, and then started declining. This is happening due to various stringent government policies and its implementations. However, we can see that the concentration of carbon dioxide we cannot reduce rapidly. Even in moderate emission scenario also, carbon dioxide values change from 400 ppm to nearly 600 ppm by end of 21st century, as if we consider. So we can say that the enhanced aerosols were decreasing the shortwave radiation till 1990s. That is something solar dimming, and after that it was slightly recovering, and as a result of that, the precipitation also started enhancing over the northern hemispheric monsoon regions. So now just let us see how the projected future changes over these various monsoon.
You have 2 minutes.
Yes, sir. I will be finishing in 2 minutes. Yeah. Now just let us see how the projected future changes in different monsoon regions. We can see that what here we did is that we considered all the monsoon regions and these dotted precipitation regions, and what shown are the percentage change in box whiskers with respect to the present day, and time is we split it into near term, that we can roughly say as 2030s, and mid term something we can say 2050s, and long term 2090s. These are all the three consecutive box whiskers from the same color, and different color box whiskers are corresponding to the low emission scenario, moderate emission scenario in yellow shade, and the high emission scenario or SSP 58.5 in the maroon or reddish shade. So here you can clearly see that if you follow the moderate emission scenario, just focus on the South Asian monsoon region, our precipitation enhancement in by near future, if you took a average over this pink shaded region, we can say that almost 3 to 3% increase we can expect, and by mid of 21st century we can expect something 5% increase. By end of 21st century we can expect something near 10% increase in precipitation. So this is mostly consistent in East Asian region, West African region, but North American monsoon seems to be declining. And if you come to the lower panel, you can clearly see that Equatorial American region precipitation seems to be decreasing. South American monsoon, as I mentioned earlier, there is no clear signal as it is, since it is still having a lot of multi-decadal kind of variability. South African precipitation seems to be increasing. Australian maritime continent region also, you can see that precipitation seems to be increasing in future. But if we examine carefully the near-term changes in precipitation from moderate emission scenario, the spatial variability, we can clearly see that spatial variations is seen even in this smaller domain also, where the maritime continental precipitation during the DJF season, we can see that over this maritime continental region precipitation seems to be increasing, whereas the Australian region precipitation seems to be decreasing. But if you see the summer variation, the African precipitation is clearly enhancing. Indian precipitation and East Asian precipitation also clearly enhancing. And if we quantify the percentage change in total land precipitation, which is shown as the line diagram at the bottom, we can clearly see that there is a moderate increase even in the SSP 245 if we consider the global land as a whole. So just I want to pass a message that in the CMIP 5 and CMIP 6 model, one of the most important striking problem was the precipitation seems to be increasing. And if you focus the figure D, the convergence seems to be decreasing. So we can say that the precipitation is increasing, but the circulation is weakening. So this is a paradox over the entire region, because we know that most of the monsoons are tightly convectively coupled systems, but somehow the models are not able to reproduce this pattern properly. But when you put the moisture, moisture convergence seems to be increasing. So people are explaining this in terms of precipitation enhancement is mostly happening due to the convective type of precipitation, whereas atmosphere is stabilizing, and that leads to the weakening of the circulation. But in high resolution simulation, we are able to get this pattern reasonably well. For example, this is a high resolution simulation from one of the previous paper, which we used LMDZ simulation, where you can see that monsoon decline is clearly associated with the weakening of circulation. Where if we noted this in model, in our CMIP6 model, precipitation was increasing, but the circulation was weakening. So this discrepancy should be addressed. In order to address this, in CCCR IITM, we take up one project which is ongoing now. What we are doing is that we are doing an AMIP type of high resolution simulation. Dr. Rajendran sir also mentioned about the importance of high resolution simulation. So in this simulation, we took the IITM Earth system model and its atmospheric component we configured with the T574 resolution. So that will give a 27-kilometer output throughout the globe. And we are doing, since it is expensive, we are doing time slice experiment. That is, we will have a near-term simulation from 2021 to 2040, and then another simulation for end of 21st century. And for comparison, we will have a present day. You can just see this map on the left side. The coarser resolution model, which is showing in the middle, was having a dry bias over land, which is a serious issue as mentioned by Dr. Rajendran sir. And the bottom panel, you can see that the high resolution is relatively improved the precipitation over Western Ghat and over the central Indian region with a much more intense low level circulation. So we can say that this high resolution model is better. So I'm just summarizing. As a take-home message, we can say that the role of aerosols are diminishing, and the monsoons are now responding mostly to the greenhouse gas forcing, which may enhance the global as well as regional monsoons in future. And that can lead to unprecedented episodes of enhanced rainfall in most of the monsoon region. So here I'm stopping. Thank you very much.
Thank you very much, Sabin. That's a very interesting and excellent talk. And in fact, you have taken on many challenges in this study, and I'm really happy to see that you are addressing this paradox of weakening circulation and enhancing precipitation. So I think these are questions which have been bothering the science community for quite some time. So I'm happy to see that. So now we are actually way beyond the schedule, and we also don't have any questions on the chat box. So thank you very much for your presentation. So we'll go on to the next presentation.
Thank you,
sir. By Dr. KP Suraj from IITM on the dynamics of rainfall extremes in the context of Indian summer monsoon. Suraj, the floor is yours.
Whether my PPT is visible?
Yes, make it full presentation, please. It's still not full screen.
Now it is full screen.
Yeah, now it is full screen. Go ahead. Go to the first slide. Yeah.
Just wait. Yeah. Thanks to the organizing committee for providing me an opportunity for this invited talk. The topic of my presentation today is the potential role of subtropical deserts in modulating the Indian summer monsoon. As an introduction, earlier studies, am I audible? Hello, am I audible?
Yes, you are audible. Go ahead.
Yeah. Earlier studies highlighted the significant influence of the Indian summer monsoon on the subtropical deserts lying to the west of Indian summer monsoon, which is usually known in the literature as the monsoon desert mechanism, which is very much well known. So in this monsoon desert mechanism, the subtropical deserts of the northern hemisphere is rather a passive recipient. But however, from a different perspective, it is also argued that the heat loss and the changes of surface heating over the subtropical deserts can also exert significant control on the monsoon systems at different time scales. So, for example, the Indian summer monsoon is known to be influenced by the atmospheric variability over the subtropical desert regions. So these considerations motivate us to re-examine the monsoon desert mechanism so that our study aims to unravel new facets on the role of the hot subtropical deserts on ISM, on the Indian summer monsoon. So basically, I am presenting results from the three studies which are showing the multiple evidences on the potential role of subtropical deserts in modulating Indian summer monsoon. So these are the models, observation, and data sets which I have used, INTROMET, GPCP, and so and so. And then I have used two couple models, which is one is Syndex F2 and the other one is IATM CFSP2. And I am also using long controlled iterations coming from all these from these two models. And also I am doing some sensitivity experiment using these two models. So these are the configuration of the couple models. I'm not going to detail into that. Okay, this is well-known model, so people already know that. Okay, so firstly, here I'm trying to understand more insights on the dry monsoon rainfall biases over the tropics, in particular over the Indian landmass. As already told by Dr. Rajendran Sir, state-of-the-art global models still show realistic unrealistic simulation of boreal summer rainfall climatology with a prominent dry rainfall bias over the Indian monsoon region and also the African monsoon region and so on. Okay, so the question is, will we be able to address it in a proper way? That is the question. Okay, so this is the skin temperature biases against IRA entry for the boreal summer season. I have taken from the two models. This is plotted from the two models, Syndex F2 and CSF2 for the control integration. Okay, so as you can see, both models exhibit similar bias with severe cold bias over the land regions, and in particular there is a prominent cold bias over the subtropical deserts, which are Sahara and deserts. You can see Sahara deserts and Arabian deserts. You can see prominent cold bias. So note that the state-of-the-art simulfy couple models also shows similar cold temperature bias over the northern hemisphere continents, in particular over the subtropical deserts lying to the west of Indian monsoon domain. So we did addition analysis, which reveals that this cold bias is in these two models is linked to the errors in the surface total surface albedo representation, and not to the bias in the downward shortwave radiation, okay, which actually controls the temperature in the surface radiation in the surface temperature budget. Okay, so that means that this suggests there is a incorrect representation of the land surface albedo in these models have contributed to the cold bias in over these regions. So in this direction, what we did is we did some sensitivity experiment using these two models, CFS-V2 and IITM CFS-V2 and Syntax F2. So we did sensitivity experiment by replacing the prescribed diffuse albedo in these two models by similar estimates coming from the satellite observations. So, and we call this runs as MODIS and MODIS Syntax and MODIS CFS. Okay, and next we are showing the skin temperature bias during the boreal summer period for these two simulations, MODIS Syntax and MODIS CFS. It is actually shown in the right-hand side of the plot. And for reference, we have given the corresponding bias from the origin, from the control integration as well, that is AB in the left-hand side. Okay, so our modeling efforts show that a realistic representation of surface land albedo darkens the northern hemisphere, and it actually enhances net radiation, and there are more heat energy in the northern hemisphere. So it also, subsequently, it leads to a reduction of the cold temperature bias. So if you compare these two and these two panels, you can see that it actually it leads to a reduction of the surface temperature cold bias over the subtropical deserts, and also it partly corrects some part of the bias in the control runs if you compare the left-hand side and the right-hand side. And also the realistic representation of the surface albedo also leads to subsequent improvement in rainfall. So this one is actually the rainfall plot, the rainfall difference between the MODIS and the control run. So here it is for MODIS CFS minus CFS, and this is between MODIS minus control. This is MODIS minus control for CFS and Syntax. So this actually shows that the realistic representation of surface albedo leads to a subsequent improvement in rainfall, and also our additional analysis showed that there is improvement in the atmospheric circulation also over the Afro-Asian monsoon domains, and it leads to large-scale rainfall improvements over the other parts of the tropical regions also. So, so this study fundamentally shows that the tropical rainfall areas are partly linked to insufficient surface thermal forcing over the subtropical deserts, which are lying to the west of Indian monsoon region. It also shows that a realistic representation of the surface albedo leads to subsequent improvement in rainfall and circulation over the Afro-Asian monsoon domains. So this is my first evidence for the potential role of deserts affecting the monsoon. So next, in the next study, we again studied the same. We try to have more insights on these aspects of the role of deserts in controlling the in influencing the monsoon. So we have used CFS and Syntax models, and here we imposed different sets of albedo, surface land albedo over the hot subtropical deserts. So these are the couple model experiments performed using CFS-V2 and Syntax models. And the first one is the control run. So the control run is nothing but it is actually the model, what we have discussed earlier, MODIS runs. Okay, and then we again did two more experiments. That is, one is desert M20 experiment. That is a sensitivity experiment. In that, what we have is a slightly idealized experiment. So here we have, it is similar to control run, but the expression that we have decreased the background land albedo over the hot subtropical deserts in this domain, as indicated here. Okay, and for the next experiment, which is denoted as desert P20. Here, instead of decreasing, we have artificially increased by 20%. So this is just for understanding what is the response. If in a model, what is the response? In a couple model, with all the complications with all the complications in the model, how if you perturb the temperature, the temperature response to the albedo perturbations, what will be how the monsoon is going to respond? So here we have CFS is mainly used for checking the robustness of the results as an independent couple model. So this is the in this we have shown the first one is the upper panel is for the rainfall evolution over the Indian or along the Indian monsoon longitudes over the 70 to 90 degree east. So from the controlled integration, and that means the mode is running itself. And the B and C in a panel, middle panel and lower panel, we are actually showing the anomalous response coming from these two experiments. One is desert M2, this is desert M20, and this is a desert P20. So what it shows, the results, our results show that the darkening of the deserts in these two couple models, the length and intensity of the rainy season over the Indian region are both significantly increased. That means the ISM onset is, the monsoon onset is advanced by 1 month with a rapid propagation of the rainfall band over the Indian domain to northward. Okay, and when you reverse the 2 minutes left, please. Okay, yes. Reversing the sign of the albedo perturbations of the deserts, these two regions gives an exactly opposite and non-linear response. Okay, so I'm just skipping this. So this is the finding from this study. So this is my last study. So this recent observation study on the dynamics of daily rainfall extremes over India again provides more evidences in this direction for the impact of deserts on the monsoon. So this is a time lag evolution of the rainfall from lag 16 to lag 0. Lag 0 means the average, the maximum rainfall anomalies at the identified date of maximum rainfall. So this is this figure shows the upper panel shows the anomalous surface forcing, anomalous skin temperature anomalies for the spatio-temporal evolution starting from lag 12 to lag 0. And in the lower panel, it is for the moist energy anomalous, and for the lower panel is for the humidity. So essentially it shows that the result shows that the surface thermal forcing and moist process over the northwest Indian arid region, I'm talking about this region, can be a very good precursor, can be a significant contributor for the monsoon daily rainfall extremes over the monsoon growth zone. So we also, our study further revealed the surprising existence of a strong positive feedback over the drier, positive water vapor feedback over the drier arid regions at daily time scale. So this is actually surprising. And then this is in line with the strong long wave greenhouse effect as already been mentioned in the context of global warming in several papers. Okay, so the enhanced warming and the amplified water vapor feedbacks over the arid region may be another significant factor for the increasing trend in the rainfall extremes over the Indian landmass. So these are I'm just summarizing the results here. So the first study pointed out the insufficient thermal forcing over the deserts in northern hemisphere, which can actually contribute to the rainfall errors in the coupled models. And the second study pointed out the ISM evolution and intensity are significantly affected with the opposite polarity to the prescribed negative and positive surface albedo perturbations over the subtropical desert. And finally, it is an observation study at daily time scale. It shows that the surface warming over the arid regions, that is over the northwest India, is found to be another significant contributor to the recent increasing trend in rainfall over the Indian landmass. So I am summarizing. I have given a schematic here, the monsoon desert process. So it's basically surface heating over the deserts, and then there is a strong water vapor feedback over that region. So it leads to desert amplification, and you have enhanced north-south pressure gradient, and you have it leads to cross-equatorial moisture transport, and finally it leads to rainfall extremes over the Indian continent. So these are the concluding remarks and perspective. So the robustness of the relation between the deserts and the ISM suggests that these driest regions may play an increasingly significant role in the ISM evolution in the future climate through the modulation of the Indian surface warming. And also desert amplification, which is especially over the Sahara and Arabia, is one of the major modes of global warming. So we need to revisit the classical monsoon desert mechanism in order to improve monsoon projections. Thanking you once again, thanks to the organizing committee for this invited talk.
Thank you, Dr. Suras, for the nice talk and comparing syntax with CFS to understand the biases, also to understand the mechanisms.
Yeah,
it's a really nice talk. Thank you. Since I don't see any question in the chat box, I recommend everybody to please put your question and comments on the chat box, so we can pick them up for asking the speakers, or also the speakers can interactively give the explanation using the chat box. Okay, since we are behind the schedule now, so I would like to move to the next talk. Thank you, Dr. Suraj, again.
Thank you, thank you, thank you.
The next talk will be given by Dr. Naga Rajesh from SRM Institute of Science and Technology. And he is going to talk about the quantification of double ITCZ bias in CMIP-6 model. This is a big issue, so I'm looking forward to your talk, Dr. Naga.
So, is the PPT visible for you?
Yes, so you need to put it in. Yes, please.
Fine now?
Yeah, please go to the first slide. Okay, it's perfect.
Yeah. So myself, Nagarajesh from Advanced Science Research Laboratory, an assistant professor from SRM Institute of Science and Technology, Chennai. Okay, to start with, so my title is about quantification of a double ITCZ bias in CMIP-6 models. So how we can quantify it, and so how it is can be studied. So of course, it has been studied historical. So I have made my work so significant with respect to future scenario, representing for shared socioeconomic pathway of 5.8.5. So let me start with the intertropical conversion. What is it about? It is actually a narrow band. So if you can see where you find the heavy precipitation and the deep convection clouds over Eastern Pacific, Northern Hemisphere, Central Atlantic, and Equatorial South Africa. So it's found within 350 kilometers of the equator, about 8 to 300 kilometers wide. You can find two ITCZs, one in month of January and in July. So in July, the January ITCZ lies about 15 degrees south, okay, over South America and Africa. And in July, it lies about 25 degrees north over Africa and about 30 degrees north over South Asia. Okay. So then, so what do you mean by double ITCZ bias? So we find excessive precipitation in Southern Hemisphere tropics, which resembles Southern Hemisphere counterpart to the Northern Hemisphere ITCZ. So this is double ITCZ bias. It's been a long-standing problem in the climate models since early days of the development, and it is continues to be a serious problem still. And so over the last two CMIPs, it has shown its the climate models have shown their improvements from CMIP 3 to CMIP 5 and then now to CMIP 6. So what are the reasons we explore? So it is about some local mechanisms in the tropics where we find SST errors in the coastal upwelling region of Peru and compounded by a deficit of stratocumulus. And about cold sea surface temperature, especially along equatorial Pacific, with strong trade winds, and you find more evaporation there, and also solar damping by clouds. And it can be, and this problem of double ITCZ bias can be reduced by closure of a convection scheme by modifying cumulus parameterizations or changing the surface wind stress formulation. So these were previous reports, and how we are quantifying here is about by using the double ITCZ bias indices, like a tropical precipitation asymmetry index, equatorial precipitation index, southern ITCZ index over the Pacific, southern ITCZ index over the Atlantic. So we are using these four double ITCZ bias indices to understand so whether it is more or less. So we give our interpretation here, and sorry, I give my interpretation here, and so I've studied based on the annual mean precipitations for over a climatological period, or historical taken from 1985 to 2014. So that's the baseline of CMIP6 project. So here totally 21 models we have chosen of the R1, I1, P1, F1 variant, R for realization, I for initialization, P for physics, and F for the forcing index. So 21 models we have chosen, taken the ensemble main and to study this, as well as we have studied for the individual models also. So in order to have, there are different resolutions have been put up here. So in order to have common footing or common resolution, so we agreed it to 2.5 degree by 2.5 degree. So what do you mean by this tropical precipitation symmetry index? So it is the difference between the northern hemisphere's tropical mean precipitation. So where you find the area average precipitation from equator to 20 degrees north, and also in the southern hemisphere from equator to 20 degrees south, and you normalize it with from 20 degrees north to 20 degrees south. That gives you the TPAI value. So what do you understand from this TPAI values? The more the TPAI, the global TPAI is, the less the double ITZ bias the model has. Then same way we have equatorial precipitation index. So it's a ratio of equatorial mean precipitation from 2 degrees south to 2 degrees north, and the tropical mean precipitation. So 20 degrees south to 20 degrees north. So the larger the larger the model EPA, you have the smaller the double ITZ bias. Then you have southern ITZ index over the Pacific. And so this can be estimated like from the long-term annual mean precipitation bias over the southeastern Pacific. And the larger this index value, the larger the double ITZ bias. And you have another index like southern ITZ index over the Atlantic. So the long-term annual mean precipitation bias over the South Atlantic, that is 20 degrees south to equator and 30 degrees west to 0 degrees. It's an area average precipitation. So the larger this I say a value, the larger the double ITZ bias over the Atlantic is. So keeping this all these four important points which have been highlighted here. So we are going to understand double ITZ bias persistence in the climate models. So these are the typical range for individual models which have been reported by Baijun Tian, and in his work about understanding the double ITZ biases in individual models. It typically varies this TPI values between 0.15 to 0.28. And for EPI, it is between 0.7 to 1.5. And for southern ITZ index over Pacific, it is 0.1 to 2.6. And southern index over Atlantic, it is 0 to 3. So this simple comparison. So this CMIP5 results is from the Baijun Tian et al. So we have done work for the CMIP6 models, and how the CMIP6 models, the same models which have been improvised in CMIP6. So we can check here. So how the double ITZ bias is being reduced when you compare with the previous generation models, either with CMIP3 or CMIP5. So for example sake, we have taken around 5, even though I have stated that 21 models been taken. So that the ensemble multimodal mean we have here, it is also represented for 21 models. And these are 5 models for to tell and so to discuss here about how they have been improvised. You can see, as I said, that if you have the larger the TPAI, you have the smaller double ITZ bias. The same, the larger the SAA or SIIP, you have the more double ITZ. So less values to convey you the lesser double ITZ bias value. So that is why here it's been highlighted separately with the red color font here. So you can see you can take one of the indices. Let us suppose SAIA. So it's been reduced from CMIP5 to CMIP6. So we can understand that double ITZ bias is also reducing. With respect to now here, this values are for the historical period for these 30 years, 1985 to 2014. So when it comes to the work, like with respect, suppose we are considering the SSP5 scenario. So So maximum possible radiative forcing that we have considered here. That is why especially gone for SSP5 here. So which is also fossil fuel development scenario. So this future poses high challenges to mitigation and low challenges to adaptation, and emphasis on economic growth and technological process. Here, these are the things that are being considered for the SSP5 future emission scenario. So as per that, so we have estimated the indices value for the individual models also, as well as the multimodal mean. So this is for the period 2015 to 2044 for this set of 30 years of period. And what we have noticed is for every 30 years period of time with this SSP 5.8.5 radiative forcing. So here we can notice that for every 30 years it's also been reducing the ITCZ bias. So under the future emission scenarios also. So if we take this SIA index value.
You have 1 minute, please.
Yes, sir. 1.53. And the same you can notice here, it reduced to 1.38 in this particular set of climatological period, 2045-2074. So it means that this index value is reducing, even the ITZ bias value also gets reducing here. So what we can understand is over the generation to generation, we find there is some improvement in this ITCZ bias reduction. So this is observational, where you find the annual mean precipitation considering this is observation data. So when this is a multi-modal mean for a same historical period, so you find the large amount of ITZ bias. So what you can understand from this annual mean precipitation plots. And for every climatological period 2015, 44 and 45 to 74, so still this ITZ bias persisting, right? So what we can understand is from model to model means from generation to generation, this ITZ bias shown there is some considerable reduction, and also in future emission scenarios also, even when you take with respect to CMIP6, there will be some impact of ITCZ bias on the future climate change studies, whatever undertaken in future. Okay, thank you.
Thank you, Rajesh. That's an excellent study. I think this is a very important problem. I'm happy that you are able to give some clues on how this bias can be understood and addressed. So we don't see any questions, and as Dr. Behra said, I think we'll use the chat box to see if there are any questions, and you can probably monitor that for discussion on your work.
Thank you very much, Professor.
Yeah, we'll move on to the next speaker, Dr. Santanu Haldar from IITM, on the quantification of enhancement in atmospheric CO2 background due to Indian biospheric fluxes and fossil fuel emissions. Dr. Haldar.
Is my screen visible?
Yes, make it full screen, please.
Yeah, thank you, sir. Okay. Yeah. Yeah, my talk will be different than the earlier talk. So I am Santanu Haldar.
Still not full screen. So can you make
not? Now?
No.
But it is full screen from my side.
Yeah, but if you are using two screens, probably there may be a problem in selecting which one to share.
Sir, you again share the screen. Firstly, you stop the sharing and
okay, stop sharing. Then share screen. Now, is it okay?
Not yet, but I think maybe you can go ahead.
Okay, fine, sir. Thank you. Okay. Good noon to all. I'm Santanu Haldar. Today I'm going to present the investigating long-lived greenhouse gas fluxes using forward and inverse modeling and concentration observation over India. So as we know, the greenhouse gases are the fundamental factor for keeping the Earth's surface temperature warm. And two major greenhouse gases are CO2 and CH4. From the recent IPCC report, we can see that CO2 has the residence time more than 100 years and radiative forcing 2.16 watt per meter square with a global warming potential 1. On the other hand, the CH4 has the residence time more than 10 years and its radiative forcing 0.54 watt per meter square and its global warming potential 86. The GHGs increases due to the anthropogenic activity such as deforestation, fossil fuel, and the cement production. And the anthropogenic GHGs are related to the recent days global warming. And in the CO2 viewpoint, we can see the CO2 has been increased from a pre-industrial era of 280 ppm to today's values of 410 ppm. This bottom panel shows the killing curve, which is the long-term atmospheric monitoring over the Mauna Loa, and from the recent days observation, we can see that atmospheric CO2 already elevated more than 410 ppm.
Your slides are not moving.
No, I am. Oh my God.
We are on the title slide. Yeah, now. Yeah.
Is it okay, sir?
Yeah, now we are on the introduction slide.
Okay, fine. Then for our study, we have used an offline global temperature transfer model NISTM. The NISTM uses 3-hourly varying meteorology from the JCDAS and 3-hourly varying PBL height from the ECMWF. And its horizontal resolution 2.5 by 2.5, and it has a 17 vertical resolution. Yes, this figure shows a snapshot of NISTM simulated atmospheric CO2 at the model surface level. And the further model details and description can be found out Valley Capital 2011 and the India calculated from 2000 to 2018 from the carbon tracker 2019B, and the shade shows the uncertainty calculated from the 3-hourly varying any fluxes over India. The right figure shows annual mean fossil fuel fluxes in gram carbon meter square per day over India for 2016. Then we validated our model. The NISTM is run from 2000 to 2018 with the implied fluxes, biospheric, ocean, fossil fuel, and the fire emission fluxes. And the further that the simulated atmospheric CO2 is also validated with the global observation as well as the regional observation. At Mauna Loa, the seasonal amplitude 5 to 6 ppm and the growth rate 2.5 ppm per year is well simulated by the NISTM. At the Seychelles, this is the oceanic site, and the seasonal amplitude at the Seychelles is also well reproduced by the NISTM. But come to the regional inversion, it's very difficult and challenging to reproduce the atmospheric CO2 over the regional at the regional site. At the CRI, the growth rate is reproduced, but they fail to reproduce the seasonality because of the weak biosphere. Coming to the Srinagar, which is operated by the IITM, and it is 50 kilometers away from the IITM. So over the Srinagar, the observation failed to reproduce in implied fluxes except the biospheric growing season. Now the methodology comes. The NISTM is run 3 years for with the Indian biospheric or the fossil fuel fluxes in separate experiment, considering two major fluxes, that is the biospheric and fossil fuel fluxes, and 12 months from January to December, there are a total 24 experiments. The enhancement is represented as the average 6-hourly model concentration in ppm from m-1 to m+1 for those values ±1 sigma, where m is a particular month, that is January, February, etc. To compare the model enhancement with satellite derived XCO2 enhancement, we followed the satellite data processing by the two methods. One is the Park-et al. 2020 and the Hakkarainen et al. 2019 in two separate attempts for the consistency. Now we will come to the result, and here we have shown the surface enhancement of atmospheric CO2 due to the Indian fluxes. Here, the enhancement means any given space and time, the discernible concentration of atmospheric CO2 from a global background that is generated by the Indian fluxes. This information is valuable because any observation that is satellite or the ground base, resolving it gives a value addition in the inversion of the Indian fluxes. The left figure shows the surface level atmospheric CO2 enhancement due to the Indian biospheric fluxes, and the right figure shows the atmospheric CO2 enhancement at the model surface level due to the Indian fossil fuel fluxes as well. From the biospheric point of view, you can see the maximum enhancement we can see during the JJA, and it is 1.2 to 1.6 ppm. The biospheric also acts as a sink. That's why the scale ranges from the minus to plus. But the fossil fuel is already also the emission. There is no sink for the fossil fuel, so the scale is always the positive. From the biosphere, we can see the maximum sink. In the sink perspective, the maximum enhancement can be seen during the biospheric growing season, SON, in the about of minus 2.6 ppm. For the fossil fuel, we can see the overall all season, we can see 1.4 to 1.8 ppm enhancement during all the season. Then the question comes, how good is the satellite capturing the area of enhancement? So we have also calculated the atmospheric CO2 enhancement at the different model level. From the model enhancement, we can find out the area of enhancement of 0.2 and 0.5 ppm represented by this blue and the cyan line respectively. Within this contour, we have calculated seasonal number of observation per day from the GOSAT satellite and also the OCR satellite, and we can find that both the satellite capture the similar number of observation per day for each season. But for the GOSAT during JJA, the GOSAT satellite hardly observed any footprints over the India during the prevailing cloud cover, but because of the high frequency observation and high SWAT, the OCO2 captures some observation over the India. But the OCO2 performance degraded with respect to the other season of the OCO2. Further, we have verified the model enhancement with corresponding the satellite enhancement. This left figure shows the satellite XCO2 enhancements produced with the Park-et-al 2020 in case of GOSAT. The right figure shows the satellite XCO2 enhancement with respect to Hakkarainen 2019 in case of GOSAT as well. And we can see for both the method is able to capture the similar enhancement, a positive enhancement during the MAM, and also the negative enhancement, that is the biospring growing season. This is during the SON. With the guidance of our area of enhancement from our model experiment, we are able to discern the corresponding values of satellite XCO2. The amplitude, pattern, and seasonal mean agreed between model and satellite XCO2 enhancement. We have also repeated the similar experiment using the OCO2 satellite and found out the similarity in capturing the positive enhancement during MAM and also the negative enhancement during the biosphere growing season, that is the SON. The summary of our study is the surface level CO2 enhancement due to the biospheric fluxes is as large as 1.4 to minus 2.6 ppm during JJ and SON respectively. The corresponding enhancement due to the fossil fuel fluxes are as large as 1.8 to 2.4 ppm. The model result gives a guidance to extract the similar enhancement captured in satellite XCO2. The result shows that average enhancement of plus minus 2 ppm can be captured in the satellite XCO2, which is a vital information for satellite for CO2 flux inversion modeling. So our future direction is to develop the inversion. So for that, the systematic observation to monitor Indian surface fluxes for the inverse study, to develop the process-based model with the observation and build inventory so that the flux can provide realistic assessment in the inverse modeling, develop regional inversion combining Lagrangian and Eulerian model, and reduce sourcing compensation among the models to have the consistent regional budget. I would like to acknowledge my guide, Dr. Yogesh Tiwari and Dr. Vinu Valsala sir. I would like to acknowledge Executive Director, Dr. Krishnan sir, Director of the IITM. I would like to acknowledge Dr. Samil Maksutam and Rajesh Ganadhanan sir from the NIST Japan, Dr. Praveer Patra sir from the Jamstack Japan, Academic Cell, RRF Committee, family and friends. Thank you.
Thank you, Dr. Santanu. It is a very good talk. I think all the best for your efforts and for your future work on the inversion model. Yes, it is very important for the climate modeling community.
Yeah.
Again, I don't see any question for you, and I request everybody to post their question using the question box here, and you can answer them if you have any questions. let's move on to the next talk. The next speaker is Dr. Soumya Singh from BHU Varanasi. And the talk title is Performance Evaluation of Regional Climate Model Ensemble for Simulating Extreme Temperature over India. So regional climate modeling for extreme climate temperature over India. Yeah, I can
hello?
see your, yeah, I
sir,
can see your file.
Okay.
Can you make it full screen mode?
Yes, sir. Good afternoon, one and all. I am
Perfect,
Soumya
thank you.
Singh from a research scholar from Banaras Hindu University, and I'm here to present our work on performance evaluation of regional climate model ensemble for simulating extreme temperature over India. So to begin my presentation, I would like to quote. Okay, my slide is moving. I would like to quote IPCC AR6 statement that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Ample of research evidence supports the fact that with rising global temperature, extreme weather events, particularly extreme heat events, have become more intense, frequent, and of longer duration in the recent decades, and which has also caused huge mortality across the globe. However, the scale of changes and the impact felt at a regional level is much more severe and larger than global level. To frame a regional perspective, regional climate models have evolved as an important and efficient tool to measure and project these impacts of extreme events at a regional level. And with the same motivation, CODEX program has been initiated to improve the understanding of the regional climate information, and CODEX experiments have been widely used for the evaluation and projection of mean and climate extremes in various studies overall. So the motivation of my study is that the reliability of the future projection of extreme temperature events will depend upon the ability of regional climate models to simulate the observed regional climate information, that is observed climate extreme temperature. So is moving. Hello,
You are on the introduction slide.
Yes, sir. I am trying to move the slide. Yes, it is moving.
Yeah.
Sorry for the interruption. So we have framed two objectives of the study. First is to evaluate the performance of CODEX South Asia Regional Climate Model Ensemble in simulating the extreme temperature over India, as well as in simulating and capturing the spatial variability of heat wave events over India. Coming to the data, we have taken two regional climate model ensemble from CODEX South Asia experiments, which are CCAM and IRXCM4, driven by 8 GCMs, which are XS CCSM4, GFDL CNRM CM5, NOR ESM, MP ISM LR, LMDZ, and GFDL ASM2M respectively. And for observe, we have taken daily graded maximum temperature data from IMD. Both the data sets are at a resolution of 0.5 degree. And for the study period, we have taken the hot weather season of March to June during the historical period 1971 to 2005. Coming to the methodology for the assessment, first we have analyzed the climatology which is the climatological seasonal mean maximum temperature during the study period to assess the bias produced in the RCM ensembles with respect to the observed. And in order to remove the bias, we have used variance scaling method, bias correction method, to bias correct the RCM outputs. And the assessment of the assessment have been evaluated on standard performance, that is Taylor diagram, root mean square error, mean absolute error, etc. And in order to see how extreme temperature is being evaluated, we have taken two ETCCDI indexes, that is TXS, that is the seasonal maximum value of daily maximum temperature, and 95th percentile of the daily maximum temperature, which is also set as very warm day threshold in the PSCI indexes. And we have analyzed the simulation of heat wave events using the IMD criteria, which differs for plain, coastal, and hilly region, depending on the threshold of the temperature and a departure from normal, which is 4.5 to 6.4 degrees Celsius.
Hello, I
and
think there is some problem with your mic. In between, it is becoming very low. So please make sure that you are close to the microphone.
Okay, sir. Okay. So coming to the results, first we have analyzed the climatological mean, which is taken for the period 1971 to 2000. And as we can see, the observed climatological seasonal mean, we can see that the CCM ensemble RCMs have overestimated the climatological mean maximum temperature for most of the region of the country, while RCM ensemble RCMs, whereas Rexium ensemble RCMs have underestimated the climatological mean maximum temperature, showing a negative bias of -28.6%, particularly GFDL-ESM2M. A common observation in both the ensembles that we have observed is that for the northern hilly region, a cold bias is shown, a consistent cold bias is shown by both the ensembles. In order to remove this warm and cold bias associated with the regional climate model outputs, we have used the variance scaling method and analyzed its statistics on using Taylor diagram and standard matrices like RMSE, MED, where we can see the root mean square error has been reduced significantly from 7.9 degrees Celsius to 0, given the ability of the method to correct the mean as well as the variance of the RCM outputs with respect to observation. Here we can see we have also analyzed the kernel, we have also plotted the kernel elasticity estimate for each of the meteorological subdivisions of India to assess which model performs better for which subdivision. A common observation that we found was that the CCAM ensemble models have overestimated the maxima in most of the subdivision, which ranges from 6 degrees Celsius to 11 degrees Celsius, whereas the Rexium ensemble have underestimated. But after bias correction, most of the models are following the observed pattern of maximum temperature. Now, simulation of extreme temperature, we have two extreme analysis. Here we can see that the maximum, here again we can see that the CCAM ensemble is overestimating the maximum temperature to a greater degree, reaching up to 50 degrees.
Soumya, I think your voice is very low now.
Sir, okay. Sir. I'll speak loudly, sir. Sorry, sir. So the maximum temperature, CCAM ensemble have overestimated the seasonal maximum temperature for most of the region of the country, reaching as high as more than 55 degrees Celsius, while the observed one has been around 47.9 degrees Celsius. But the very warm day threshold, that is the 95th percentile, is simulated similarly by both the ensembles, similar to the observed. That states that we can further evaluate the performance of the model in simulating heat wave events over India, since the standard threshold of the percentile is evaluated similarly by both the ensembles. Coming to the heat wave events, we have found that both the RCM ensembles were able to simulate heat wave events in the most heat wave prone regions, which is the northwestern, central and south central region of the country. But we found that LMDZ4, GFDL ESM and MPSM and GFDL CM3 have been found to simulate the cumulative heat wave events frequency and spatial variability in similar to the observation, while excess CCSM4, CNRM, CM5 have overestimated the frequency as well as the spatial variability of heat wave events. The trend results were not very satisfactory, but they also point out, as most of the trend results show that access and CNRM, CM5 are showing a negative trend of the heat wave events over the regions, while only LMDZ and GFDL ESM2M have shown a reasonably well trend analysis result for the heat wave events as with respect to the observation. Based on these statistics, we can say that RCM and Rexium4 ensemble, and particularly LMDZ and GFDL ESM2M models, are able to simulate the extreme temperatures similar to the observation. And coming to the conclusion of the study, we have found that out of the Cordex South Asia experiment that we have taken, CCM and Rexium-4 ensembles have respectively overestimated and underestimated the seasonal mean max temperature. Variance scaling bias correction method have removed the bias and improved the model simulations to a very good extent. And overall, LMDZ and GFDL-ESM2M of Rexium ensemble of Cortex South Asia experiment have been found to be better performing in simulating extreme temperature as well as frequency and spatial variability of heat wave events, which can be used for future studies as well. Thank you. Here is.
Thank you very much, Soumya. That's a very important study, given that heat is a major global problem now with the climate change. And it's very important for us to identify and eliminate biases in the way heat waves are projected in the model simulations. I think this is a very important study, and I wish you all the best for your future work. And there is a lot of additional work that needs to be done in terms of the heat waves.
Thank you very much, sir.
So we don't have any questions for you. So we'll move on to the next speaker. In fact, the next speaker, I understand, is not available. So we'll go to the last speaker, Dr. Sanjeev Kumar Sahu from IIT Delhi on high resolution downscale future Indian summer monsoon rainfall projections over India. Dr. Sahu.
Hello, sir. Next one is
hello, sir.
Yeah, go ahead.
So is it audible?
Yeah.
Yes. Good afternoon, sir. This is myself, Sanjeev Kumar Sahu, a senior project scientist working under Somnath Boytrai, associate professor of Center for Atmospheric Sciences, Indian Institute of Technology, Delhi. So today my talk is on high resolution downscaled future Indian summer monsoon rainfall projections over India. Based on the last 2 days, we are talking about how climate is changing, how those changes affecting this summer monsoon rainfall over India. I'm not talking about the introduction. So many people given the talk in introduction, then I'm skipping this part and I'm going to my objectives to identify the best physics configurations and initialization protocols that performs the best in simulating the current as well as future projections over Indian region. And second objective of my study is develop a high resolution data sets in graded format for meteorological variables for current as well as future projections, and develop a district scale data sets in Excel format for current as well as future scenarios. In this study, I have used this weather research and forecasting model, that is WRF. It is a leading mesoscale atmospheric model in the world, and it is used for many downscaling applications. Solves the conservation equations for the atmospheric in the discrete space using the numerical techniques. It has numerous options to represent physical and dynamical processes in the atmosphere and boundaries. And WRF has the most million lines of codes in Fortran, and it is run in parallel code using MP and on a high performance computing system. And these are the equations which are used in the WRF, and mostly on conservation of momentum, conservation of mass, ideal gas laws, conservation of energy. These are the equations are used in the WRF model. And going to my methodology, I have adapted the model configuration optimally. It is model configured with careful selection of domain size and geographical coverage, horizontal and vertical resolution, physics options, and preference schemes. And in this case, we have used 8 sensitive studies to carry out our simulations to identify the best physics configuration and initialization protocols. And my main focus is on initialization protocol, which we have given, which we have divided into two parts, that is with reinitialization and without reinitialization, to identify the best model configurations. What are these initialization protocols? This is reinitialization. What is the reinitialization? Reinitial approach, where the model is initialized from 00 UTC of each day and run for the 24 hours. And output of this, since we are made the simulations for monthly wise, and similar 30 consecutive day long runs are concentrated to generate a month-long downscale data sets. And that is without regression is nothing but a continuous approach where the model is initialized at 00 UTC to the, and it is still run to the 30th days of the month and generate a month-long downscale data sets. And we have taken the initial and boundary condition data from NCAR CSM. Why we choose CSM here? We have choose CSM here because it is a global bias corrected data. Why not other models? Because other GCMs are giving biases. That's why we have going for CSM. Why not CMIP 6? Nowadays CMIP 5. Why we choose CMIP 5? CMIP 5, CSM CMIP 5 is which is comparatively compatible to WRF. Why not CMIP 6? Because it will take 3 to 4 years we will made it from bias corrected to compatible to WRF model. That's why we have chosen the CSM CMIP output for this model and RCP 8.5 scenarios. And going to the sensitive experiments, we have chosen 8 sets of sensitive experiments with PBL schemes, microphysics schemes, and cumulus schemes. And for these sensitive simulations, we carried out 2 seasons, mainly dry season January and wet season July for consecutive 2006, 7, and 9 years. And in between that, we have all the reinitialization and without reinitialization with 8 sets of experiments. We have completed all the 3 years runs, 3-year January, July runs. Based on the result of spatial distribution, spatial correlation, and some of the statistical analysis is carried out with IMDA and ERA5 resolutions. The results show that reinitial approach doesn't provide any significant advantage over continuous simulation for our domain and resolution. Moreover, it is computationally slightly more extensive than the continuous approach. Hence, we selected the continuous approach with set 2, that is PBL scheme with YSU, WSM6, and CAP schemes for our simulations. And we for the current scenario, we have made the simulations for the year 2006 to 2015, and for the future scenario, we have going with 2091 to 2002, and validation with observation with ERA5 analysis and IMD reanalysis. And this is our model domain. We have carefully designated the domain size and all the physics options, time integrations, all the dynamics and the physical configuration are showing in this feature. And validation, we are mainly these data sets we have prepared mainly for precipitation, temperature, latent heat flux, sensible heat flux, long wave, short wave, and all some 8 to 10 variables we have extracted all the data. But here only I have showing only for rainfall, how this rainfall validation is compared with IMDA reanalysis and ERA5 analysis. From this analysis, it is showing that the RMSE of precipitation remains low throughout the country with a value mainly based on 5 to 10 millimeter, and the error is comparatively high in complex terrain in northwest region or in Western Ghat region. This still it is a concern for that model. And if you see the time series from 2006 to 2015 in between downscaled CSM from our model and from IMDA reanalysis and from ERA5 reanalysis, it is showing a complete same structure phenomenon. So that's why this data gives the accurate projections over Indian region. And here we have showing this seasonal rainfall analysis of different seasons with from current scenario with future scenario and the difference between this future and current scenario. And this shows, and here we also compare where we are showing this statistical significance with a 90 value of 90% and 80% is showing it is clearly significant. And my conclusion is high resolution data sets of meteorological variables under current and future scenario can be used to drive hydrological models to understand the spatio-temporal variability of water resource and estimate the hazard vulnerable to climate change. Results show significant regional effects of climate change and monsoon precipitation, especially strong in Western Ghat and the Northwest region, and some reductions in the central India. While in the monsoon seasons, the signal of precipitation change is there in the all the except post-monsoon seasons, where the trend is a little bit high over the overall. All the downscaled CSM precipitation can satisfactorily capture the rainfall pattern over India. Hence, the downscaled precipitation can be used to study various rainfall-based processes in future scenario at high resolution. The downscaled data sets made available at three temporary resolution, daily, monthly, and monthly climatology time series periods for current and as well as future periods in WDC repository, which are given below in the we have submitted this submitted data in the WTC respiratory, and also submitted a paper in Nature Scientific Data. And we for this work we acknowledge the mainly National Mission for Clean Ganga for giving this highly valuable project in which I'm working, and thanks to my guide Professor Somnath Vaidrat for helping me. Thank you.
Thank you, Dr. Sao. Very nice work and very nice presentation. So I hope you can continue to improve the downscaling of monsoons and try to focus on some specific regions to compare your results and apply them.
That is our main focus, regional basis.
Yes, please. All the best. And we are behind the schedule, but I understand that Dr. Neetu is here, so we missed her talk. So may I request now, Dr. Neetu, to present your talk, if it is okay. And you are going to talk about the projections of heat waves over 7 temperature homogeneous zones of India from CMIP 6 model. So before you start your presentation, I would like to remind Dr. Santanu, there is a question for you in the Q&A box. You could answer that. Okay, please go ahead. We can see you.
Sir, screen is visible?
Yeah.
Yes, can I start?
Yes, please.
Good afternoon, everyone. Myself, Neetu, from CSIR 4th Pandemic Institute, Bangalore. And here I'm going to present on the projections of heat waves over 7 temperature homogeneous zones of India from CMIP 6 models. And the outline is followed like this. And nowadays, India is experiencing a number of extreme weather events, and heat waves are one among that. So the days with extremely high surface air temperature are generally known as heat waves, and sometimes it lasts for long days. And over India, generally heat waves are occurring during the pre-monsoon season. And the severe heat waves are mainly found over the central India, northwest India, and the states like Odisha and Andhra Pradesh. And now the heat waves have become one of the major natural hazards with taking a lot of casualties. And as we know that the global surface air temperature is showing an increasing trend at 0.85 degrees Celsius. And the important thing is that during the last 60 years, the increasing trend is 0.72 degrees Celsius. And now the studies have showing that the heat waves are an increasing trend, and it is projected to be more intense and frequent in future over India. So it is really important to study how the heat waves occurrence and distribution in future. So here we will be concentrating on the projections of heat wave coverage over the 7 temperature homogeneous zones of India from different climate change scenarios. So this is the study region. Here we have classified the Indian region to 7 regions like the Western Himalayas, Northwest, North Central, Northeast, Interior Peninsula, West Coast, and East Coast. The data used here is the high resolution bias corrected daily maximum temperature from the CMIP-6 experiment. And the study is conducted for the historical period 1951 to 2014 and the future projections from 2020 to 2100, especially for the pre-monsoon season like April, May, June. And here the CMIP-6 experiments are based on the shared socioeconomic pathways and representation concentration pathways. So here you have taken 4 scenarios, SSP 126, 245, 370 and 585 scenarios from the 13 models. And these are the list of 13 models we have used in the study. All are in bias corrected and in the same resolution as 0.25 degrees. So the methodology here will be using like initially we will be validating the TMAX simulations, CMIP-6 historical TMAX simulations with the IMD gridded maximum temperature data. And the heat waves are identified based on the 19th percentile threshold of maximum temperature. That is, if the maximum temperature is greater than the 19th percentile of percentile threshold of Tmax, and where the climatology of maximum temperature is greater than 35 degrees Celsius, and if it is continuously persisting for 3 days or more, it's considered as a heat wave here. And here comes the validation of CMIP-6 historical simulations with the IMD. Here it is the multimodal mean of the seasonal Tmax and with the IMD seasonal mean. And it is clear that it is most of the places it is giving a good validation, and especially over the Western Himalayan region, the model simulations are giving an underestimated results compared to the IMD simulations. And this is giving a climatological cumulative heat wave coverage distribution for the historical period and the future period. And cumulative heat wave coverage, it is the product of the area of occurrence of heat waves and the number of days. It is the multimodal mean for the CMIP-6 models, and it is giving a good validation with the IMD observation. And the cumulative heat wave coverage is comparatively more over the interior peninsula region than the other regions, and it is clearly found that there is a significant increase in the future heat wave coverage, and it is varying from the SSPs 126 to 585. And here it is showing how the multimodal mean of projected cumulative heat wave coverage vary over the time period. That is, it is for the near future and it is for the far future. And the near future, there is not much increase in the cumulative heat wave coverage, but a significant increase is found over the future period like 2051 to 2100. And the projected cumulative heat wave coverage is likely to increase from SSP 126 to SSP 585 for all the 7 regions. And this is the multimodal mean of change in Tmax. That is the difference in projected Tmax from the historical simulations under the different climate change scenario, SSP 126, 245, 375, 370 and 585, that it is clearly visible that there is an increase in temperature at the end of the century. And in the SSP 585, there over the northwest and north central India, there is an increase in temperature which is more than 2 degrees Celsius is found. And the regions which are generally devoid of heat waves are the west coast, and there are some small pockets of high temperature change is observed. And this is the multimodal mean of change in the heat wave days with respect to the historical simulation under the different climate change scenarios, SSP 126 to SSP 585. And the regions, this west coast, are generally devoid of heat waves. And it is found that there is an increase in the number of heat wave days, especially over the parts of north central and the northeastern part, and the interior peninsula and the southern parts of the east coast. So the conclusions are the CMIP-6 climatological distribution of Tmax and cumulative heat wave coverage are in good agreement with the IMD observation. for the period of 1951 to 2040. And the projected cumulative heat wave coverage is likely to increase from SSP 126 to the SSP 585. And by the end of the century, that heat wave days will increase more than 2 days per year over the parts of Northeast, North Central, and the southern parts of Interior Peninsula and the East Coast under SSP 585. Thanks to DST and IMT for the. Thank you, sir.
Thank you, Dr. Neetu, for that excellent presentation, which nicely complements the earlier presentation on the with the regional models. I think these are important areas. So with that, we conclude the session. I think we have had excellent presentations by different experts, and in fact, we have nicely covered all the aspects of the theme. Including some application-specific ideas. I think it's very important for us to recognize that there is a tremendous progress that has been made both on the global scale and also within the country. I think we are on the verge of actually providing quality-specific information that is more reliable in the present circumstances. So with that, the session is concluded. Before I conclude, I request my co-chair, Dr. Behra, to make any closing remarks that he may have.
Thank you, Dr. Rukumar. It was a pleasure to co-chair this session with you and also to listen to excellent talks from Dr. Rajendran to Dr. Neetu. All were very nice talks on different aspects, climate change, modeling, even regional scale, monsoon, and also heat waves and temperature. So it was very nice, and I think I have no more any other things to add to what already you have said. So thank you very much, everybody. And there are two questions in the question and answer box. I think they are not answered, and the rapporteurs have put a link, hyperlink to those questions. So I request Santanu and I think Rajesh to answer to those questions if possible. Yeah. Thank you very much.
Thank you, Dr. Rukumar and Swadhin Behra for chairing the session. So we will be reassembling around 12:10, sorry, 2:10 for the next session. Thank you.
Thank you.
Thank you. Bye.
Thank you. Bye-bye.
Hi all. Welcome to the technical session 3A of INTROMET 2021. This session is on data assimilation technique and numerical weather prediction. So this session is chaired by Professor A. Chandrasekhar. So A.K. Sahai was also expected to chair this session, but due to some unavoidable circumstances, so he will not be joining this session. So I request Professor A. Chandrasekhar to chair this session. Professor A. Chandrasekhar is an outstanding professor at Indian Institute of Space Science and Technology, Trivandrum. He has contributed immensely to the field of numerical modeling of atmosphere, data assimilation, mesoscale modeling, regional climate modeling, etc. So in this session, we have two lead talks and one invited talk. Two lead talks by one Dr. A.K. Mitra and another one by Dr. P. Mukhopadhyay. So A.K. Mitra is a scientist G and head at National Center for Medium Range Weather Forecasting, Noida. He made outstanding contribution to various fields such as coupled ocean atmospheric modeling and ocean initialization, air sea interaction, model verification and diagnostics, monsoon prediction from days to season, merged satellite gauge rainfall datasets for hydrometeorology, and multi-model ensemble prediction. Dr. Parthasarathy Mukhopadhyay is a scientist F from Indian Institute of Tropical Meteorology, Pune. His areas of expertise includes high-resolution GCM and mesoscale modeling of monsoon, heavy precipitation events, and thunderstorm. Another invited talk is by Dr. Govindan Kuti. Govindan Kuti is an associate professor at Indian Institute of Space Science and Technology. His areas of research interest includes improving the understanding of predictability of extreme weather events through data assimilation and ensemble approaches. So in this session, the lead talk will be for 20 minutes. Additional 5 minutes will be given for discussion. Invited talk is for 13 minutes and additional 2 minutes for discussion. And short oral presentation is for 9 minutes and 1 minute, additional 1 minute for discussion. So we kindly request request the speakers to comply with the time allotted. Selected questions in the chat box will be conveyed to chairs by rapporteurs. So now may I request the honorable chairs to kindly take over the session. Thank you.
Yeah, good afternoon to all the participants and those who are presenting for this particular afternoon session on day 2 of the INTROMET 2021. Let me at the outset welcome all of you. So without much ado, let us start the lead talk. I invite Dr. A.K. Mitra, Head National Center for Medium Range Weather Forecasting, who's going to talk today on seamless modeling and data assimilation at NCMRWS. Dr. Mitra? Yeah.
Thank you. So I will just share the screen. 1 minute. Is it visible, my first slide?
Yes.
So I will just make it full screen.
Full screen.
Is it full screen now?
Yeah. Yes.
Okay, thank you, Professor Chandrasekhar and the INTROMET organizer. I'm thankful to giving me this opportunity to convey what we are doing at NCMRWS. So I decided to select a topic. We have put a seamless modeling system. So I will tell about that. What is the seamless modeling system in place? It's one of the very advanced thing we have in the country. So mostly I will talk about seamless modeling system, which is operational, our recent activities, And I will not be covering what research and publications we are doing. So it is mostly describing the operational system. So as you know, INTROMET is under the Ministry of Earth Sciences. Our main mandate is to underpin the forecasting capability of the nation. And we are mandated to do the global and regional data assimilation. And one of the mandate was to develop a seamless prediction system, which is already in place now, which I will be talking about, and also to develop new application. And this center is also doubling as the BIMSTEC Center for Weather and Climate, as a regional center for weather and climate. So you all know that this global modeling and data assimilation capability, only few centers in the world we have. So we are very fortunate, and India is one among them where we have this global forecast and modeling capability. And like any other center, all the data comes. So we receive the data which goes into the model from the global telecommunication system, from satellite, from bilateral relation with NESDIS, EUMETSAT, ISRO, and many other centers. Then once this data comes, it goes through the quality control. Then we have two global data assimilation systems here. One is for the GFS assimilation system, another is for the So I will talk more about the system here. Then all this initial condition which is produced in this center, it goes to the model forecasting, ensemble forecasting, deterministic forecasting, and a lot of host of application and users are there. And that's the same thing in another schematic diagram. All kind of satellite in situ observation, including radars, it goes through all this assimilation. And finally, what you see on our web is chart, but this digital data is also available for the users to derive and do develop applications. So one of the most important thing is over the years, the number of observation, particularly the satellite data, if you see here, what we are receiving through internet has increased manifold. What it used to be 10 years back, it's gone many times. And we also keep a tag by comparing our data with ECMWF, so that we know at any time what type of data we are receiving, so that, you know, this data makes a lot of impact on the forecast. So ECMWF is a standard data monitoring center. So by comparing with them, we know where we are lacking or we are at par with them in terms of quantity of data. And we have this following data assimilation system. One is global 4D VAR system, which is based on ensemble ETKF. And this provides initial condition to 22-member ensemble prediction system, which I will tell. Then we also have a 4D VAR data assimilation system, which is 4 kilometer in grid. Then we have land surface data assimilation system, part of the data assimilation system. And recently, 2 years back, we have configured a global ocean and sea ice data assimilation system. And it also runs in real time and provides initial condition to the coupled model ocean and sea ice part. And as I told, we also do this global and regional assimilation for the GFS and WRF, HWRF system, which is operational in IMD. And these are the list of all kind of data, surface and profiles, aircraft, satellite wind. So you can see a huge amount of satellite wind, then your radiance data, all the satellites are named instruments. So they all go into the assimilation system. And we have a very interesting system called to study the impact of this different type of observation. So we keep on doing this. It's called a forecast sensitivity to observation, FSOI. And this is published, you can see. And so any new data type, so it's a very useful tool. We work with ISRO that if they're planning for a new satellite or a new sensor, what will be its impact? So all the observation system simulation experiment impact studies can be done. Or if a new simulation data is added to the system, what is benefit? For example, I will talk about a loose wind, which is this. You see, it's having a good impact. It shows, and the number of observations are on the right hand side. So it can be done globally for a region, for a particular period. So it's part of the data assimilation system, but very useful in deciding what priority to give which data, and the cost benefit of this can be worked out. And one of the example I will give we keep on adding any new satellite data comes, so a lot of effort goes into making the data operational. So recently we have included this space-based LiDAR data, which is called ELUS horizontal line of sight, HLOS wind, and we started receiving the data, then compare it, then after thinning it, how much goes to the assimilation. So at every stage, this quality, etc., we studied. Then we studied some impacts. What's the impact during monsoon in the lower level and the upper level? Then we compare with the available AMBs. And once we are sure that the data quality is good, then we put it into the assimilation system. So this is already operational in the global data assimilation system here, and we have seen it's producing good impact on the tropical cyclone and severe weather systems. And these are the future satellite data we are getting ready to use it. One among them is the ISRO's upcoming OceanSat-3, which we'll be using. And there are many other satellites. So we keep track and we are in touch with NESDIS, EUMETSAT, ISRO, any satellite data producer, what they're likely to produce in coming 1 or 2 years, and how to receive those data and process it and see the quality and how we can assimilate it. It's a continuous work which goes on in the center. So related to this data assimilation, we have produced 2 reanalysis. One is global GFS-based analysis system for reanalysis data for 20 years. And another thing is this IMDA regional reanalysis. So which is a 12 kilometer, 1979 to 2018. And you can see about this in our webpage, and it's freely available. One has to just register, download the data and start using it. So it has become very popular, and many users are started using, and they're writing research paper, and they are using it for their application purposes. So it's basically a regional 4D data assimilation system. And we got all the old data, 1979 to 2018. And beyond 2018, on demand up to 2020, the data is reproduced. So we got all the old archive from ECMWF, our NCMWF own archive, UCAMET office, IMD. And this also has a surface data assimilation system. And we have seen at every stage the quality of the data. It's very useful. And we have published a couple of papers. So if you see the papers, it tells you what kind of data has gone into the reanalysis. And this data is very popular now for the process studies, and you can pick up any past cases and study. So just to show some example, we have studied the onset withdrawal and how good is the precipitation in this reanalysis data, and how is the temperature represented. So people can use this data for studying heat wave, cold wave, heavy rainfall events, extreme weathers, and cyclones. The Kerala event also, we saw it's captured very well in this reanalysis data. And now coming to the model. So a part of the seamless modeling system. So we have the same dynamical core, that's the seamless model. So that's configured for global deterministic model, global ensemble model, 22 member at the same resolution, 12 kilometer. Then we have the 4 kilometer deterministic model, regional up to 72 hours. Then we have an ensemble prediction system based on the regional model, which is 4 kilometer, 11 member operational. Then we have this coupled model. So we run it every day up to next 2 weeks, every week up to next 4 weeks for extended range prediction. And now recently from last year, every month for next 4 months for seasonal prediction. So it has atmosphere ocean. So I will show some slide about that. And another important aspect about the regional data assimilation is we are using the maximum DWR data available from IMD. Apart from assimilating in the regional data assimilation system, we are trying to use it to derive rainfall. So there is some project where we want to make composite of the radar data and merge gauge data and satellite data so that we get very high resolution data. So soon this product will be available for public. And we have also studied the impact of radar winds on this regional. It's all beneficial and having a good impact on the severe weather. And coming to the land surface data assimilation system, we assimilate the ASCAT soil moisture, and we have seen the benefit of that soil moisture in monsoon depression case we just picked up. It is operational, both in global and regional data assimilation system. But in the regional system, we picked up some cases of monsoon depression, and we studied because of the better initialization of the soil moisture, the distance error and the location rainfall intensity is improving. So it's very useful for initializing the land surface for severe weather. And so one of the benefit of the seamless modeling system is same dynamical core you can use across scale. So the shortest scale is 330-meter Delhi fog model we have. It runs in winter only to predict fog, and it's used by IMD and airport authorities. And the same model dynamical core is configured at 1.5 kilometer, 4 kilometer, 12 kilometer, and the coupled model also for ensemble prediction system. One of the benefit of the seamless prediction system that the model development cycle is very fast. Anything you test in the smaller scale, experiment in the medium range or in the coupled model, and if you are satisfied, you replace everything in all the system and come out with a new cycle of model. So this is, we are at par with other centers now, even centers like NCEP, etc. They just started 2 years back implementing a seamless modeling system. The medium range part they have configured, and in collaboration with GFDL, they are going to configure the coupled model part of the seamless prediction system. So we are at par with all leading centers. And if you see the performance of our model with time, because of better data assimilation and resolution, the RMSs are continuously dropping. So that's a good thing, that because of the enhanced satellite data use and the HPC model resolutions, new models are there. And if you compare our skill with other centers, NCMW, with NCEP, Met Office, and DCMW, if you go to day 5, so you are almost there, comparable to other lead center. Marginally, maybe ECMW, they are slightly better, but it's not much. We are all comparable. This for the tropics, and we have seen for other region also. So I will just show 3 slides from the recent heavy rainfall in Kerala, which happened in October. You see day 5 in advance. This is the rainfall from the global model. It was captured well. It was giving an indication that very anomalous rainfall is going to happen even 4 days in advance. And the regional model did much better. You see the heavy rainfall is here, and the model was indicating 3 days in advance that there will be heavy rainfall. And almost similar time, you had Uttarakhand, very heavy rainfall, extreme rainfall event, which was captured very well by the model. And this is the regional model. Again, the intensity and the location was very nicely captured 3 days in advance. And this is what happened in the Rayalaseema, 19th November. You see, this is the regional model. So it captured very well 3 days in advance, if you see the observed location. And these are from the different model, our unified model, our regional model, and this is the UK Met Office. This is the IMD GFS, and this is the NCEP new GFS. So we are pretty well compared to many other centers, and it's working well for the severe weather. One new thing we have introduced in last 1 year is the lightning forecast. So the regional model, you know, nowadays the cyclone prediction, heavy rainfall prediction is good, but many deaths are happening because of the lightning prediction. So the regional models, by improving the assimilation system and the forecast model and incorporating the lightning schemes and using the observation available from IITM and Indian Air Force, we are able to compare and see that broadly the regions of lightning activities predicted very well. So one can give advance warning 2 to 3 days in advance, which are the regions where lightning is going to happen. But to pinpoint on a village level, district level, it's difficult. But we are working on some new system called rapid refresh system. So it will be possible to make lightning forecast very early, some kind of short range 6-hour forecast. So that's what we are working now on that. So we have many users. IMD is our main user, and many other government agencies. National Nuclear Power Corporation of India, they use our forecast for early warning system of emergency, nuclear emergency system. We have many users for the hydrological applications. And interesting thing is many private companies for wind energy and solar energy, we have been catering to them. And they are finding this model output very useful, and continuously they are interacting with us. And a huge number, at least more than 10 are working with us, and we are receiving feedback from them about the quality of forecast. And another thing is this center is also catering as a BIMSTEC center for weather and climate. So under BIMSTEC regional cooperation, as I showed in the beginning, that with this unique capability of modeling assimilation we have in this center, so we are extending our support to BIMSTEC countries in terms of products, training. Time to time we organize trainings, workshops, and many products also on the web we keep, and bilaterally also with individual countries on demand. We are providing output to them. We are in touch with them. Coming to ensemble forecast system, actually my next speaker, he will talk more about that. But we are very fortunate due to availability of HPC and our scientists, resources and collaboration, we could put in place very high resolution ensemble prediction system. We have 23 member ensemble prediction system, and GFS, Partha will talk about that. So this is one of the highest in the world compared to other leading centers. So that is the capability we have in terms of probability forecast and defining the uncertainty. And it's accepted by the TGI in ECMWF, so anybody can download this data from ECMWF for research purpose. And you have seen in the TV and many websites, whenever the cyclone comes, how useful is this ensemble prediction system. So it not only gives ensemble mean track intensity, but the probability, strike probability, which areas are likely to be affected in what percentage, which is useful for the disaster managers. So this is a very standard product now. Whenever there is a severe weather or deep depression or cyclone is approaching, these products we share with IMD, and we also keep all this thing in our web. Anybody can use it, including the state disaster departments. And this is the new thing we have implemented, the ocean data assimilation system. So what kind of data goes into this? So this is a global, very high resolution NEMO-based model. We use a variational data assimilation. So all the SST, so I'm showing you how much data goes. So this is the SST, satellite SST, which goes into the assimilation system. These are surface observation, including SEEP, mood buoy, drifter. These are subsurface data, XBT, and Argo, etc. And this is the sea ice information which goes into it. And these are the altimeter sea surface anomaly. And we have compared with Ramabui. The analysis system does pretty well, compares well with the in situ observation. And it is totally independent. It takes wind from our own model. Then it derives all this current. It's a full ocean model which is driven by our own forcing, and the assimilation is done with the first guess taken from this model. So it derives currents, then sea surface temperature, salinity, and everything. So based on that, the coupled model is initialized. So as I said, we have the atmosphere initial condition, the ocean initial condition coming from the NEMO bar. Sea ice also is initialized. We have a land surface assimilation system. So a complete R system model which caters to a coupled model. So one important thing is tropical cyclone heat potential we monitor. So this is a very interesting case. You see high heat potential along this coast. So the one cyclone which formed over the Andaman Seas, Phylin, it came along because of the huge heat availability. So we are monitoring the cyclone weekend or what, and we saw that it is remaining, and this tropical cyclone heat potential prediction, sorry, I said it's funny system, and you see day 15 in advance. So this is the observed tropical cyclone heat potential, and these are the different forecasts, and you can see 15 days in advance this coupled system was able to capture that such a heat will be available, and we could see that the cyclone will not weaken, it will be strengthened. Another use of this coupled model is the extended and prediction multi-week forecast. So we give this forecast to IMD, and they use both the IITM and this system to draw their inferences. So it's very skillful up to day 2 and 3 to predict the dry and wet spell. If you have a dry spell, how it's going to get into the wet spell, when the next wet spell will be over. So all this information we have seen week 2 and week 3 are very skillful. And the monsoon onset, this is an example slide I put in 2019, monsoon was delayed. We had a delayed onset which came around 8th June. And 4 weeks in advance, the model, coupled model predicted that there is a delay. See, there is no rainfall coming 17th May, 24th May, and even the rainfall belt is not moving. But in the 4th week, it started moving. So this is very useful for extended wind prediction. And we have the capability because of the coupled model, sea ice assimilation, and there is a less almost sea ice model which is coupled to this Earth system model. So we provide forecast to NCPOR.
One second. Now, how long you will take to complete?
Yeah, last 2-3 slides. Yeah.
Okay, fine.
So we have the capability of polar forecast. So we produce this forecast and share with NCPOR whenever their ships are operating in the Antarctic or Arctic, whenever it is required. It's available around the year. And so our station is in Maitri. So whenever our ship is approaching close to Maitri, this is the sea ice prediction and situation can be given from the model. Very useful for our Antarctic operations. And recently we introduced this seasonal forecast system based on the seamless model. We compared with ECMWF. The skills are comparable. 70% skill is there. And these are the correlation plots compared to ECMWF, totally comparable. So very recently, we are now configuring a regional coupled model based on the UM system. This is part of the seamless modeling system. These are some of the early results from the regional coupled model, which will be used for very severe weather forecasting. So what we need is computing power. So now we have only 2.8 petaflop of computer. So what we have projected that we need at least 100 petaflop for R&D. But moving our operations by next year or 23, we need 20 petaflop. Because ECMWF has moved to coupled NWP. In the medium range also, they are using a coupled model. So we are ready with the model. It has been tested, but we need this HPC. So we have a collaboration of unified model consortium, all these countries we collaborate. And so the state of the art is model is maintained here. So this is our future plan. Basically, we want to further work in this seamless modeling system, and coupled NWP is the main thing. We want to go as soon as the HPC, new HPC is available, and this regional HRR system for severe weather, where all the radar data will be used, is the next focusing, and developing application. A lot of resources we have put in the ensemble prediction system, but how to make use of it. So we are working with many sectors like water, energy, and defense people, agriculture, how to make use of this probabilistic forecast and estimate the uncertainty. So with that, I will stop. Thank you.
Yeah, it was an excellent talk. I think giving the broad overview of the various aspects and the recent advances of all the deterministic systems that NCMWF is working on, that encompassing ocean, atmosphere, land, sea ice, and so on. Dr. Mitra, thank you very much. So I will ask if there are anyone who has some questions or clarifications or some comments. So they are free to.
So there is a question in the chat box.
So I'm not getting it.
Yeah, I can read some question from Abhiram. I would like to know if NCMWF model forecasts are available for public use. I'm especially interested in the NCM global regional model. Yeah, we are collaborating with any institute. So you just write an email to us and what is the problem you are interested. So we are sharing the data with many users, as I told. So if you are a user, you can write to us. If you are a researcher, write to us. So you can tell what is your research problem. We'll find out a scientist who will work with you. So just send an email. Thank you.
Yeah. So Dr. Mitra, I have one small clarification regarding this. This one, you talked about the wind profile from LiDAR. How recently and how frequently you use it in your, and how many levels you get, and what is the resolution at the ground? Horizontal.
Yeah, actually, we are simulating the whole profile. It's a new data set. We made it operational only a few months back.
Okay.
And the number of observations are quite a lot, something like in lakhs. Okay. And so the exact detail, my colleague who works, I will ask him to send an email to you, the numbers, but they are coming in lakhs.
Okay.
And many layers. So we have to thin it. One plot I showed you, almost 75% thinning we are doing.
Okay.
It's a huge number of data, and the impact I showed almost 10th to 12th most important data, which is having an impact.
Okay. Okay. Thank you, Dr. Mitra. Thanks for your very enlightening talk. Yes. So let me invite Dr. Parthasarathi Mukhopadhyaya, who is our next lead speaker. Dr. Parthasarathi Mukhopadhyay is going to talk about recent developments and future prospects of numerical weather prediction in India.
Thank you, Professor Chandrasekhar. Is it my slide? Is it visible?
Yeah, it's visible, but only thing you just have to put it to full screen.
Okay. Is it full
Yeah,
screen
now it is full screen. Yes, you can start.
Okay, thank you. So thanks to Chair, thanks to our INTROMET organizing committee for kindly inviting me and giving me the opportunity for sharing some of our research. So Dr. Mitra has nicely given a very detailed overview of data assimilations and NWP, initial condition generation, etc. So I will basically mostly, talk about the physics part of the model. So you all know that any NWP model has two major components. One is being an initial value problem. It heavily depends on proper initial condition, and once it is initialized, then the model performance is heavily dependent upon how well we are representing the physical process in an NWP system. So I will mostly confine in that physical process. Okay. Now, this is the brief outline. I'll talk about the current system, its strengths and weaknesses, basis for future improvement and challenge and future roadmaps. Now, actually in IITM, we don't run operationally any model, but what we do is we develop this model and hand it over to IMD for operational use. And currently, whatever model has been given to IMD is right from top is seasonal forecasting system, which happens to be the highest resolution in the globe at 38 kilometer CFS T382. Then Dr. Sahai's group developed this extended range forecast, with 44 members. And then we have developed this recent, GEFS T1534 with, truncation 1534 with 64 level in semi-Lagrangian dynamical code. But before that, we had earlier, T574. It was in 2017 with 64 level, and even before that, we had 574, which is around 27 kilometer. Eulerian system, that was a determinist system. Before that, the system was to T254, and even before that, it was T82. But one very interesting thing you can see that even if the horizontal resolutions of the model increased from T82 to T1534, the vertical levels remain almost, constant. We have never increased the vertical resolution. You might have noted that even unified model, the vertical resolution is 70. So this is one of the drawback you can right away keep it in mind. Now, just to start with, one of the very simple metric to see a model's performance is just to plot the scatter plot of precipitation and VLR. Okay, this is the observations, and if we plot the precipitation and VLR, okay, and this actually tells us that the rainfalls are associated with what type of VLR. So the low is the VLR, it suggests the deeper is the cloud. So you can easily make out that these these are the winds of rainfall which are coming from a very deep cloud. Okay, so this is the structure of the system. Now, if I go to different model which we have so far analyzed, right from T62 to T126 to T382, you can make out yourself that none of them are actually resembling what is noted in the observation. The major problem you can see, there are very few dots below this 180 watt per meter square VLR. So it basically, so you can argue, in T382 there are few more dots, agreed, but it is nowhere close to what is seen in observation. So what does it mean? It means that the model is producing a lot of light rain from the warm cloud, okay, but very few heavier intensity rain from the deeper cloud. So the clouds in the model are not model is not producing very deep cloud. The same systematic bias we find when we plot the model rainfall and VLR, at different time of the day, okay, early morning, middle of the day, and in the afternoon. You can see that while observation clearly suggests that the cloud is deepening, okay, by afternoon and contributing heavier and red. These two model producing a similar type of rainfall. Only because higher resolutions it is producing more grids. That's all. But the distribution remains same. Another issue is, see, basically, tropics is a convectively coupled system. We know here the circulations and wind, they are convectively coupled, and you know that manifestations of weather are basically due to all these convectively coupled equatorial waves. And if you see, this was published back in 2015 by one of my students, and you can see this is the Kelvin wave from observations, AVHRR. But when we come to the model, the signal is very weak, whereas the equatorial Rossby wave, is overestimated. Again, the mixed Rossby cavity wave, which is a high frequency wave, you can see the model is very, very, almost non-existent. So this again suggests gives us an impression that the models, moist process are not in place. This is another way of looking into this, which is called Wheeler-Gladys diagram. And this also shows, basically the same thing, Kelvin, equatorial Rossby wave. And we can really can't make out which one is low resolution and which one is high resolution. But it is not only, for GFS, it also happens, GFS-CFS, it also happens in other climate model as well. I mean, you can see here, this is a CAM4, this is CAM 3.5, SNU, and so on. And this is observations. This is, of course, boreal winter. And here you can see this wave number frequency diagram. None of them are actually resembling the observations, except this model, which I will come a little later, which is super parameterized CAM. Okay, and now eventually, with all these inaccuracies in the convectively coupled equatorial waves and all other manifestations, you finally get to see these biases. These get reflected in the precipitation and also in the wind. You can see here, these are the two different models. This is 100 kilometer resolution, this is 38. But you see the precipitation bias is fairly similar. Both are raining too much over ocean and raining too little in the land. I think, but again, this is not just for CFS or GFS. This is the state-of-the-art IFS model, and you can really see this is from Athena. There's a big experiment, a numerical experiment, and you see the ECMWF IFS was run at T2047. It's a huge, resolution at 10 kilometer. And this is the trim observations, and you can see there is not much, resemblance if we go from a T159 to T2047. It's even more clear if we see the variance. So here you see none of them look actually similar to the high resolution observation. So the take-home message from all these is that while we improve the resolution, okay, that is must for resolving topography and resolving many other heterogeneity, but we have to make our physics also suitable for higher resolution. If I keep the physics which is used for T159, if I use that for T2047, then this is the results that we generally get, and we can't expect the model to do a marvel. And this is, I think, Dr. Rajivan also showed yesterday, a recent paper by Chaudhary et al. 2021, and this was the famous paper of Sparva 2013. These two were already known, they have reproduced them, but they have added this image 6. While there are some, improvement or deterioration here and there, but the broad picture looks really similar and remains same. I mean, they have only plotted over the large from 40 to 160, but if it is plotted for the whole globe, it is still, the fact is that the oceans are getting more rain and lands are getting lesser rain. The question is, what is the probable reason behind such model? So one of the reason is moist process parameterization. And here I have plotted the observations. This is a log of rainfall it means 0 means log 1 and 1 means log 10, 2 means log of 100, okay, millimeter per day. And this is the pressure and this is the relative humidity. What you can actually notice in observation that there is a gradual moistening, okay, the moisture is gradually increasing in the boundary layer when the rainfall is becoming heavier, okay. But that is not the case for model in any of the resolution. You see the relative humidity, the moisture is suddenly getting becoming very, very high, okay. And in all, I mean, and in between, you can see a very dry layer sitting here in the middle of the troposphere. So this is one of the major problems. So the model will produce a lot of popcorn type of convection, but it will not actually emulate the observations. Now this is one of the issue. This is where students must read this. Arakawa's made monograph 1993, where he very nicely explained what the basic framework of quasi-equilibrium, where it shows that the large-scale moist process will destabilize. It will pump the moisture and atmosphere will become unstable. Okay, CAPE will be generated. But then the cloud scale will consume that moist instability. And he said, I mean, that is the basis of Schubert's, and in many, almost all the semi 5, semi 6 model closure, that these two are in balance. Okay. But in Chang 2002, using atmospheric radiation measurement, southern Great Plain data, he has, convincingly showed that this is not the case. Okay, the net CAPE and the partial CAPE, they are very poorly correlated to. So this framework doesn't actually remain valid neither in mid latitude nor in tropics. But still we are using that. That is one of the major issues of these biases, which we have been hearing since yesterday. And now the question is, what are the possible ways out? Okay, one possible way out that was again suggested by Professor Arakawa. He suggested there are two routes basically. One route is you go from GCM to global cloud resolving model. That's what we are. I mean, there are many papers coming in Wade et al. And so on. And otherwise, there is a via media route where you develop a multi-scale modeling framework, okay, and then avoid this uncertainty of the convections. And how we do that? We do in this way, okay. That also we tried in CFS, that we put many 32 single column model or cloud resolving model within one grid of CFS or GFS, and then we try to reproduce, run the model. It is very expensive, but you can see this is the variance. Okay, this is the variance plotted for the super parameterized CFS. This is the CFS V2, the default one, and this is the observation from TRIM. This is for synoptic variance. This is for ISO variance. Okay, 2 to 10 day and 10 to 90 day. And you can see a very good resemblance with the super parameter. But the point is, the advantage is it definitely improves the mean state and variability, resolving the cloud process. But the disadvantage is it can't be applied for operational forecast. We can't run an ensemble of super parameterized model because it is very, very expensive to run. Then you may ask the question, what is the what is the advantage? What is the need? I will come to that later. Arakawa also suggested that we need to improve this representation of different ingredients processes of the cloud, like rain, propel, cloud, and water vapor. We tried that, and we added from a WRF like a test bed. We use it in GFS and CFS. So 6 class of like this WSM. And this is an observation-based study by Jiang et al., where he showed when the rainfall propagates northward, okay, the cloud hydrometeors, it is integrated ice water content, that also propagates northward. So observations. We tried to see whether this really happens in case of model. And when we saw that when we added a physically based a microphysics, okay, in the model, that actually happened. You can see here the rainfall is propagating northward, and the cloud water and cloud ice that also propagates northward, which is consistent, which is not happening here, which is the default physics thing. And this is a recent paper by Dr. Surya Chandra Rao and many of us, where we can see that this model with improved physics actually performed almost equivalent to the high resolution CFS T382. So So this again shows one example that if we improve the physics, even a moderate resolution model can compete with a high resolution model. Okay, so now question is, this is a very, very important paper. Students must read it, Ongoing Breakthroughs in Convective Parameterization, April 29 by Catherine Rio. And she said that it is often stated that a good climate model should be a good weather model. And indeed, short-term error growth on weather timescale can reveal important parameterization deficiencies that lead to mean state biases. So what she is actually indicating that we should use a GCM, AGCM as a test bed, okay, and then go to the climate model. We did actually other way around. We started from climate model, ended up in GCM. But anyway, so this is the GCM which were required by IMD, by society, by everyone, that was installed and that we implemented. This is 12 kilometer. And this model, which we have now, a very advanced convection, which is scale aware. Okay, this is very much required. And you see with this model, this is the diagonal plot of day 1, day 2, day 5. You can see there is it fairly looks reasonable with that of observations. Even the amplitude with the GPM, you can see up to day 5, the amplitude of diurnal rain looks very reasonable. Whereas if you see this where we have not used this convection, you see both the model looks like a hockey stick. Okay, and this is the the GFS performance for last say 8 or 9 years, and you can see there is a gradual improvement of the skill, and bias also is not increasing. So model is performing really reasonable, and this I think already Dr. Mitra has shown. But this is actually at par with other centers of what he was showing. That is really an encouraging part. And T1534, this is a very interesting plot. You see the black line, which is the day 5 skill by 12 kilometer model, which actually coinciding with the day 3 skill of T574 model. What does it mean? It means that actually we have gained 2 days. Okay. By increasing the resolution. If you see the ECMWF standard, they say their target is 2 days improvement in a decade. So anyway, we have done it in just 2-3 years. But everything is not so rosy. Okay, we've seen a benchmark rainfall case in Kerala. We have published a paper in weather forecasting at BAM, and you can see here we have plotted all the 3 models. Okay, GFS, ECM, and CUM, and you can see while this is for 2018. You can see on the first day, the models are quite good, but the same magnitude is not captured in other lead times. Okay, so this is the limitations of a deterministic model. So that's why we remember Ed Lawrence and we follow his methodology, and based on that, we come to GEFS. It's a gigantic engine. It's a 21 member, 12 kilometer model, daily run twice. Okay. It's a huge data. Now the data is online available in ECMWF TG archive. Any student, anyone just can go and download and utilize the data. A very, very important and this data. Now you see what is the advantage of this GEFS or ensemble system. If we would not have that system, see this is a deterministic forecast of cyclone Amphan, and you see this deterministic forecast is suggesting that the cyclone may go towards Odisha. Okay, whereas because we had this ensemble, we could see that the cyclone actually went towards West Bengal, and you see this is the observation. So this is the advantage. You see here there are 21 members are suggesting one side, the deterministic suggests the other side. So this is why one realization of any model not to be believed. That is the essence of the day. Now you have seen the deterministic efficiency. Now if you see the same 3 models, this is GFS, this is IFS, and this is NCUM, but this is forecast probability plot for this rainfall. You see for Kerala event 2018, this is the probability, okay? And this is the rainfall plus 1 standard deviation, climatology rainfall plus 1 standard deviation. This is climatology plus 2, this is climatology plus 3. And you see for ECM and NCUM, even climatology plus 2 standard deviation, it shows around 70% probability 6 days in advance. This is a huge, even 1 standard deviation, all 3 models are doing very well. So this is the merit of ensemble forecast. It is equally same for 2019 case. You see here, okay, on this case, all these models, okay, 1 standard deviation, 2 standard, even 3 standard deviation. 3 standard deviation means actually it is 99%. Okay, and you can see the 70% probability and 5 days in advance. So we have to utilize this information from ensemble, okay, which is still we are not, we are not able to get it. Now this event was not even captured by ECMW extended range. That needs to be. And I was hearing yesterday somebody was talking, the clouds were actually very shallow. This event, now the question is, why did it happen? So we tried to give some explanation. This is one explanation we have given in that paper, that tendency of precipitable water vapor is governed by source of moisture convergence, and sink is the precipitation. What we found is that this integrated precipitable water vapor is very, very low, okay, during all the days. So it essentially means that the integrated moisture convergence is almost converted into precipitation. Now question is, if my model has not produced the rainfall equivalent to what is observed, then it would mean that the efficiency of converting this moisture convergence into the rainfall is lacking in the model, what actually is the case. Now this is the recent case, in the October 21, you can see here also we find strong moisture convergence. And you see these integrated precipitable water vapor is very, very small. It means it is balanced by the sink, which is precipitation. And look at this probabilistic forecast. It again gives high probability with 5 days lead. But deterministic, no, it is very, very less. Okay, so this is the essence. Now, what are the challenges? Challenges is, you see,
Dr. Mukhopadhyay, yeah. I think you need to.
Yeah, I will finish in 2-3 minutes.
Okay, fine.
Yeah. So this is the, even if we plot this ensemble forecast, okay, we find that the models are still struggling. Okay, and we have also seen that the spread is lesser than RMSE, which basically means that the ensemble forecast is under dispersive, means overconfident. So we have to improve that. And how do we do that? There are many ways. One way is that we have to increase the resolution, horizontal and vertical. We have to introduce this more and more stochastic processes, and we have to build a coupled GFS that is already in process. Just for example, you see when we have increased the resolution from 64 to 128, see the improvement in the rainfall for the case of 2018. You see the same thing for recent October case, okay, when we increase the vertical resolution. Now, I think this was mentioned by Dr. Rajivan yesterday. This we are now working on this. We are using this, TCO grids, a cubic octahedral grid that is used in ECMWF. And here is the latitude versus length scale. We are planning to use this TCO to 1534 so that we can run the, we can get a model around 6 kilometers. And this is another way I was asking that what do we do with the superparameterization? The superparameterization model can be used in AIML. We use this CRM's tendency, okay, to drive my tendency, okay, and we completely, that is still we are working on that, okay. And another way we are thinking to improve is our stochastic processes by using the radar across the globe, not just 1 point data over India and so on. Anyway, so the summary is like this: that significant improvement is achieved in the system. High resolution ensemble forecaster found really useful for various high impact weather phenomena with longer lead time over Indian region as compared to deterministic. But there is a need to introduce stochastic perturbations to improve basically the spread and RMSE relations in the ensemble, and also needs to improve the individual member of the model. Possible break in parameterization deadlock may come from the data-driven AI/ML approach. That is my personal belief. And this, I already shared this slide with Dr. Vilas. Any student can take it. This is the link which Dr. Mitra also was telling. One can go and take the GFS data and utilize it. Before ending, I would read from Professor Kerry Emanuel's one recent paper, where he says very strongly, it's mostly for students. Okay, as it becomes easier to undertake complex computer simulations of climate and weather, as large volumes of satellite data become more and more available, it is tempting to use computers to simulate rather than understand nature. And so the suggestion is that without understanding, we should not run the model. That will actually hamper scientific progress and may impede the development of better models. And this is just, I plotted, the snapshot of GFS 12-kilometer cloud with actual, global satellite cloud. You can see the whole equatorial ITCZ is very well captured, but you can easily make out like this picture might have been taken with a lower pixel camera where these finer details are, lacking. So that's why we require a high resolution model. Anyway, I stop here, Professor Chandrasekhar, and thank you so much.
Yeah. It was an excellent and enlightening talk by Dr. Mukhopadhyay on the recent developments and future prospects of numerical weather prediction in India. So, Dr. Mukhopadhyay, there is a question in here. So, can I ask both Dr. Mitra and Dr. Mukhopadhyay, if you had to prioritize one new data type or region for expansion of observations for data simulation for forecasting, what would that be? And what is the model development priority for better NWP and ER forecasting?
So you are asking Dr. Mitra first?
No, I think you can also answer. No issues.
Okay, if you ask me,
no, this is the question and answer. I think, can you read it? There's someone called Andy Turner who has put this question.
Can I ask if you had to prioritize one new data type and region of observation for DA? So this, I think Dr. Mitra can say what new observations he feels. And I can say about the development priority.
Yeah, please.
Yeah, so see, as I showed in my talk, so first priority will be land surface assimilation, because currently we are having only soil moisture from ASCAT, but there is huge scope in assimilating other land surface parameter, like we have experimented with the insert land surface temperature, but many other things related to land surface. That's what ECMWF has shown, that if you properly assimilate, initialize the land part, there is a huge improvement even in the subseasonal to seasonal forecast and the medium range. So all land surface parameter in the land data assimilation system that we want to prioritize, that is number one. And the satellite data, see, as and when nowadays the new trend is private data producers are coming out with many type of data. So we are in touch with the private data producers also, and so like this micro REN, this GPM type REN radars are coming. So and that also we would like to assimilate the rainfall, vertical heating profile, all those information which is useful for the tropics. Thank you.
Okay.
Yeah, that other thing what he's asking about the priority in NWP. So I would say there are two priorities. Andy, one is that our resolution has to improve because the models are still struggling in getting the orographic rain of Western Ghat. And the second thing, I think Dr. Mitra also will agree, we have to introduce more and more stochastic process. This deterministic closure, is not going to help us in any way. We can't represent the PDF of rainfall over tropics by just setting a hard condition that if it will rain if the cape is greater than this and not rain if the cape is less than this. So we have to have a stochastic PDF based scale aware approach, and that of course both the centers are working.
Yeah, another thing is since ECMWF has moved to coupled medium range forecast, so that's also a priority now in India, that we have to go to coupled
Absolutely.
NWP in the medium range and ensemble. See, we are stuck with 20 ensemble each model. At least we have to use 50 ensemble, and what Partha also told, how we generate to have a balance between error and spread. So that's a trick. The ensemble technique to a proper representation of the probabilistic forecast is also, we have to do a lot of research on that. So coupled NWP and ensemble members, how we create that. That's a priority. Thank you.
Okay, thanks to Dr. Mukhopadhyay for a very enlightening and interesting talk. So we go to the next speaker, invited talk by Dr. Govindan Kutty. He's going to talk on assessment of predictability of tropical cyclones over Bay of Bengal using ensemble-based methods.
Am I audible?
Yeah.
Thank you, Professor Chandrasekhar. At the outset, let me thank the organizers of this meeting, INTROMET, for providing me an opportunity to present my talk. Let me share the presentation. I hope my screen is visible.
Yeah, it's visible, but now it's fine.
Okay. So today I'll be talking about predictability assessment of tropical cyclones over the Bay of Bengal using ensemble-based methods. And I'm Dr. Govindan Kutty along with Rima Matthew from Indian Institute of Space Science and Technology, Vallimala. So Dr. Partha has given very nice explanations about the importance of ensemble-based forecasting. So just as an introductory part, I'm just introducing this as a for ensemble forecasting. Uncertainty is a part of every weather forecast, and no forecast is complete without the descriptions of uncertainty. So ensemble forecasting can be used as a method to quantify these uncertainties of chaotic atmosphere. So these uncertainties which we get from the ensemble-based forecastings can be used to understand the predictability. If you can, the larger the uncertainties means the larger or the lower will be the predictability. So this information is useful in predictability studies. So in this study today, I'm going to present I've used the ensemble-based systems to understand the predictability, with an understanding that for a well-calibrated ensemble system, ensemble spread serves as a proxy for predictability. So you can see in this equation, which is given here, the left-hand side shows the mean squared error and the right-hand side shows the variance. So when the number of ensemble members are higher, the variance will tend to be equal to that of the mean squared error, which means the variance or the ensemble spread, this is the square root of it, can be used as an indication of the forecast error here, and hence it can be used to understand the uncertainties in the atmosphere. So higher ensemble spread indicate lower predictability. That is the assumption with which this work has been done. Two objectives mainly. One, we have to find out whether any common predictability characteristics are there during the genesis, deepening, and landfall phase of tropical cyclones over the Bay of Bengal. If any common predictability characteristics are there, what contributes for higher or lower predictability of tropical cyclones over Bay of Bengal? Is the intrinsic predictability, which is actually defined as the potential for dynamical error growth within the initial conditions, or is it due to the initial time and uncertainties within the analysis? So these are the two things which has been explored. So predictability in this study has to be properly defined. We are not talking about extended range predictability of tropical cyclones. We are talking about the predictability as an ensemble spread of response function. In this case, it is a cyclone central pressure at the final forecast time, which is actually 24 hours. We are not extending our forecast beyond 24 hours. So the forecast is limited to 24 hours, and we try to understand the predictabilities within that. And we define the predictability as based on the ensemble spread. So naturally, a question will come that how do you understand the potential for dynamical error growth in the initial conditions? For this, we have used a method which is called as ensemble sensitivity analysis. So ensemble sensitivity analysis tells us that if an initial condition at a given region is perturbed, how much it would alter the response function. if you make a small perturbations over one region or in initial conditions, and if the response function responds very largely, then that means that it is highly sensitive to initial conditions, and which can indicates that the intrinsic predictability is lower. So ensemble sensitivity can be used as a tool to define the potential of for error growth. So this in an ensemble framework, you can see JE here is the forecast metric, which is actually a vector, which is represented as a vector, which is having a size of k cross 1. K is basically the sample size or the number of ensemble members in this case, and X is the variables in the analysis, which is actually P cross P matrix, which is an off diagonal in which off diagonal elements are assumed to be 0. So only it's a diagonal matrix, and so we are using univariate ensemble sensitivity here, and ensemble sensitivity is calculated as a gradient of forecast metric to the variables in the initial conditions, which is actually expressed in terms of ensemble statistics as covariance of and divided by the variance from the that statistics is actually estimated from the ensemble members. So higher ensemble sensitivity indicates that there is a higher potential of error growth in the initial conditions. That is the assumption here. And using this, we conducted our study, and for this, the ensembles which is required for this current study, we have taken from ECMWF data, which is the TIGI global ensemble forecast data. 51 ensemble members are available at a resolution of 0.5 degree and 0.5 degree, and a total of 24 tropical cyclone has been considered, which occurred during a period of during 2010 to 2019 are identified. You can see the track of the cyclones which has been considered in the study, and that falls in different categories of cyclones. We didn't separate in terms of categories. And based on this, we conducted this study. In this is something which gives you the spatial distribution of or spatial plot, which gives 3 different figures you can see. One is the analysis spread, the second one is the ensemble sensitivity, and the third one is the forecast spread. Forecast spread is the indication of the predictability in the forecast. And the analysis spread will give you the information about how much uncertainties, initial condition uncertainties are there. We treat the analysis variance as the as an indications of the analysis error. Here again, that's an assumption. It may not be always be true. And the middle one gives you the ensemble sensitivity, which tells us that how much is the the potential for error growth in this for a given in a given initial conditions. So this figure is given just as a representative figure, and it is plotted for cyclone Phylline. Now, what we did was we calculate the deepening rate of tropical cyclones, and that is plotted against the this forecast spread, and which is given in the left hand side of this figure, which gives you as a positive slope. And we also calculated the statistical significance. It passed the statistical significant test at a confidence interval of 95%. And we found that the positive slope indicates that as the deepening rate increases for those cyclones which is having deepening rate is higher, the predictability of tropical cyclones become lower. Cyclones with higher deepening rate exhibits lower forecast predictability. That is what it indicates. And on the right hand side, you can see the sensitivity, ensemble sensitivity, maximum absolute ensemble sensitivity is plotted against the forecast spread. And again, it gives us a positive slope, which indicates that the cases which is having higher initial condition sensitivity exhibit lower forecast predictability. And we again classified the cyclones into 2 categories, 2 bins. So based on their deepening rate, one is the based on the rapid deepening. We classified as rapid deepening. This is a very subjective classification, not based on any criteria which we have used. We simply plotted the distribution. Based on the distribution, we did the classifications. Rapid deepening is the cyclone which actually deepens at a rate of 20 hectopascal per 24 hours. That we got 8 cyclones in that basket. And slow deepening is which is less than 12 hectopascal per 24 hours. So we got 9 cyclones in that basket. And when we have plotted the forecast spread, the sensitivity, and calculated the forecast spread of sensitivity and the initial spread, and the middle one gives you the forecast spread, or which is actually the proxy for predictability. You can see that the light pink color bar is a higher value than that of the dark pink color, the pink bar, which indicates that the forecast, the rapid deepening storm exhibit higher forecast spread, which means the lower predictability, and also you can see look at the sensitivity. Sensitivity is higher for those cyclones which rapidly intensifies, which means it is highly sensitive to its initial conditions, and the chances of error growth is higher in that case. Whereas in the case of initial spread, even though rapid deepening storms are having higher values, the error bars are very high, so no conclusive results can be gained from that. And again, we we computed the sensitivity with respect to various variables like initial sea level pressure, field, the specific humidity, the vorticity, vertical wind shear of the forecast with respect to the initial conditions. And we found that in all cases, a rapid deepening storm exhibit significantly higher sensitivity for all the variables in the initial conditions. Now, the next thing which we did was we classified the cyclones into two categories again, the north falling cyclone and south falling cyclone. Again, we made a subjective classification on the cyclones which make a landfall, which at a latitude which is greater than 17° north and which is less than 17° north. We got 12 and 11 cyclones. And again, if you look at the figures, interestingly, you can see that the cyclones which is having a north falling cyclones having a lower predictability or higher spread. The center figure represents that, and the cyclones which is actually having a south landfall shows a lower spread. So which indicates that the north landfalling cyclone have higher sensitivity and forecast spread than the south landfalling ones. So we did the same thing for based on the forecast. The landfalling locations with respect to its initial conditions, and again we found that north landfalling cyclone exhibit remarkably high sensitivity to its initial condition for all the variables which were considered in its initial conditions. Again, we did the same experiments with different seasons, cyclones in different seasons, pre-monsoon and post-monsoon, by the assumption that the flow conditions are different, so the predictability will change with respect to seasons, and we found we didn't get much good results from this. Predictability during the landfall doesn't vary with seasons. That's results which we got from this. And one more thing which we did was we based on the genesis locations, we classified the cyclones into two categories, B1 and B2, as you can see. One, the cyclones which makes its genesis at the central Bay of Bengal, and which is having its genesis at the southeast of this, and we again did the predictability experiment as we conducted. The error bars are pretty large, but the one results which we can see is that the central Bay of Bengal cyclone exhibit lower forecast spread than the cyclones which form over the south, and the sensitivity is also higher for those cyclones. So in conclusion, rapid deepening storms exhibit low predictability than slow deepening storms. North landfalling cyclones have low predictability than south landfalling cyclones. Cyclones with genesis location towards the central Bay of Bengal exhibit higher predictability than the cyclones that form over south of Bay of Bengal. And despite the flow conditions being different, no significant differences in predictability seen between pre-monsoon and post-monsoon. That's all. Thank you.
Yeah, thank you, Dr. Govindankutti. It was a very, very enlightening and very interesting talk. So there is just one question. So the question is, sir, any opinion on machine learning output explanation on basis of physics?
I think this question is not for me. It's for Dr. Partho, I guess.
Okay.
He's talking about the physics, right?
So any comment or any questions or clarifications from anyone? So Dr. Govindankutti, I just have one small clarification.
Yes.
So you showed in one of your slides that when you actually took pre-monsoon and post-monsoon, the spread was not very different. It was more or less the same.
Yes.
Yeah. So
yes.
This was very different from the other, above 17 north, below 17 north. You have different regions over the Bay of Bengal.
Yes.
But if you look at pre-monsoon, post-monsoon, the number of cyclones in post-monsoon is much higher, right?
Yes. Yes.
So when you actually take the cases, did you ensure that the number of such cyclone cases that you consider?
Yeah.
They're also equal, or?
That we try to make it equal, but that's one reason why the number of cyclones have reduced, because we have a lot of cyclones in post-monsoon. So the number of cyclones in pre-monsoon basket is different from that of the post-monsoon thing. So we have to reduce the number of cyclones to make it equal, or something comparable, and that may be the reason why we are not getting the results. We are exploring this further to understand it further. So I think it is maybe because of the reduced number of cyclones we are getting results which we were not expecting.
But you have ensured that the
we have ensured that the cyclones, number of cyclones are comparable in both baskets.
So are there any questions? And if there are not, let us thank Dr. Govindan Kutty for his excellent talk. Thank you, Dr. Govindan Kutty.
Thank you.
So, so now we have completed the 2 lead talks and the invited talk. Now we go to the presentation. The first presentation is by Dr. T. Banik from India Meteorological Department. So this is going to be, the topic is explicit lightning forecasting over northeastern India, preliminary results, explicit lightning forecasting over northeastern India, preliminary results. I'm sorry, it is repeated twice. So Dr. Banik, you have now the podium.
Yes, sir. Just a minute. I'm sharing my screen. Click this.
So you have 9 minutes and 1 minute for discussion.
Yes, sir. My screen is visible?
Yeah, your screen is visible, but make it full screen. Huh?
Yeah, okay, just a minute. Is it now okay, sir?
Just
is it okay, sir?
Yeah, just waiting for it. Yeah. So meanwhile, you can just start, I guess. Yeah. So
I already full screen the PPT, sir. Is it visible now?
Right now, not yet, I guess. Yeah.
Okay.
So you can start here this thing. I think it will take some time, maybe. So fully it should be fine. Yeah.
Or shall I reshare my screen, sir? After stopping it.
Yeah. Okay.
Okay. Just a minute, sir. No, I understand. This is bigger. Yeah, sir, it's working now.
Yeah, now it's fine. Yeah. Now it's
okay.
fine. Yeah.
Good afternoon, all of you. This is Trishanu Banik. I'm from India Meteorological Department. I'm presenting the topic which is related to the lightning. The presentation topic is explicit lightning forecasting over northeastern India, some preliminary result. So this is the objective. The initial objective was to develop a numerical weather prediction model based on lightning forecast system over the Northeast India, and also we are planning to implement the same over the Pan India. And the second one is to utilize the ground-based lightning detection sensors data into the model for assimilation purpose. And third purpose is to check the performance, how it is performing with respect to the observation lightning data. So presently there are two popular way of lightning forecasting system is available. One can forecast the lightning using the explicit electrification physics inside the model. And another way is to diagnose via combination of kinematic or microphysical proxy variable, which are basically well correlated with the lightning occurrence. In my case, I have utilized the first one, that is using the electrification physics mechanism. So the model that I have implemented is called EWRF. In the model, it has two different sections. One is for the charging, another one is for the discharging section. In the charging section, there are two ways. One is the inductive charging, another one is the non-inductive charging. Both the charging mechanism has been implemented in the model. And in the discharging mechanism, we are considering some charging threshold as well as the electric field threshold. Once in any of the grid point, if that electric field threshold or charging density threshold is crossed, we consider it as a lightning discharge. So the charging scheme that we have implemented, this is the equation that we have utilized in the model. And also the assimilation system is also there in the model, where the observed graded lightning has been converted to the model water vapor. And based on the observed lightning, what we are ingested in the model, the water vapor in the mixed phase region of the model changed. So this is the picture. Next one, this is the study domain that we have implemented. Complete Northeast India, 3 domain configuration was there. Domain 1, Domain 2, and Domain 3. Domain 3 encompasses the whole Northeast India. And the physics and other parameter name list option that we have implemented or utilized is given here. You can clearly see those things. The resolution we have used is the 3 kilometer for the innermost domain. And we have also turned on the lightning only inside, only on the 3rd domain. So what are the results? So if you look at the picture, you can see I have considered one day, which is during 2017, when there was a thunderstorm or lightning incident over the Northeast India. And you can clearly see that. This is the scenario. And this is the observed lightning. This is the Earth network generated lightning during the 3rd April 2017 on 7 UT. When we run the EWRF model in control run scenario, we can see model are not able to capture the observed lightning very well. But after that, we have assimilated the lightning and start generating the forecast after 1 hour, 2 hours, 3 hours, like that. Then we noticed the forecasted result changes very drastically. And you can see the model are well captured the observed lightning condition. And if you go to the 2 hours after the assimilation, you can also see the model is capturing very well. We have tested the same thing for the 3 hour, 6 up to the 6 hours. We noticed if you go beyond the 6 hours, the model performance start deteriorating. So we can, for any kind of nowcasting purpose, we can very this is the model that we can we can utilize this model for the any kind of nowcasting purpose, because after the 6 hour from after the assimilation, this model performance is very good. And these are the some other cases where you can see this 3 color, we have represented the simulated lightning, severe, high, and moderate. And this is the observed lightning represented by the red dots. You can see the observed lightning and simulated lightning are matching very well after the 3 hours lead time of after the assimilation. This is the 1 hour, this is the 2 hour after the assimilation, this is the 3rd hour. So these are the different date cases. You can different day related cases you can see that we have run over the northeastern part of India. And these are the other case studies where model perform very well. This is the cases, you can clearly see those cases as well. And third thing is the validation. So based on the different days, actually over the Northeast India, we have run the model during 2019. We have around 48 days. So we run the model, we gathered all the data, we plotted those, and after that we generated the validation study based on the different statistical score of contingency table. So first figure at the topmost corner is basically the observed lightning during the pre-monsoon 2019. You can see the the western part of the Northeast India is very much lightning prone. And this is the Earth network generated lightning. And this is our model generated lightning, which is the second figure. This is the EWRF simulated figure. You can see how beautifully the EWRF captured the observed lightning. This is also true that EWRF lightning density is showing more compared to the observed lightning. But if you look at the spatial distribution and also the temporal distribution we have checked, in terms of the spatial distribution, the model captured the observed lightning very well. Further, we have plotted how the POD, ETS, accuracy, FAR, correlation coefficient, and bias score changes day by day in different grid points. You can clearly see those things. And you can see for the POD or ETS or different other statistical score, the region where the higher lighting activities is what the region which is very much prone to the lightning. Those regions or over those places, our model performance is very well. But the region surrounding to the places where the model performance is good also shows some higher FAR value. We can clearly show those places like this. So in terms of the spread, we can say that our model of simulated model output representing the observed lighting well, but at the same time, the spread is also showing some kind of high FAR value. So we have to look into this issue also, how we can minimize this kind of false alarm ratio. And also we have plotted the correlation coefficient. You can see the color bar is there. Most of the places you can see the correlation coefficient is very good. And some places are also there where the correlation coefficient downs up to the 0.5. And also if you look at the bias score, you can see the places where the high lighting activity is observed is showing the good correlation, and the area which shows the high FAR value, those shows the over forecasting by the model.
So Dr. Banik, I think you have 1 minute, one more minute to wind up.
Yes, sir. And also further, we have generated the statistical scores after averaging all the grid point and all the analyzed day for different co-location radius for different threshold. You can see how the model perform for those dates. And this is sometimes what happened. Even if you see when we take the average, the ETS value come down. For that reason, what we have done, we have considered individual day and plotted how ETS performs when we consider the mean ETS with respect to the all grid point. You can see in some days ETS value goes up to 0.55 or around 6. And also I have plotted few dates when the model performance was very good and few dates when model performed very average and some worst case scenario as well. So this is the case when model performed very well, and this is the case when model averagely performed, and this is the case when model failed to capture the observed lighting. So what we notice that if there is a huge amount of lighting activity or good amount of lighting activity, then model capture very well. But if some isolated or some small lighting incident is there, sometimes model fail to capture those parts. So in future scope, we have planned to implement the same over the pan India. Even we have tested few cases also, but before implementing for the whole India, we are we need to validate the model, how it is performing with respect to the observation data. And we also have a target to testing the EWRF with sub-kilometer scale resolution. And different improvement scope is also open, and more sophisticated assimilation technique also we can test for this modeling system. Thank you.
So thank you, Dr. Banik. It was a very interesting topic. So there are a couple of questions asked in the chat box. So the first question is, which model variable are you using to assimilate your lightning observation? And second is, can you explain the observation operator for your lightning assimilation?
Yeah, so this is the mixed phase water vapor. We modify the mixed phase water vapor with respect to the observed lightning. So that relation I have already showed in the methodology section, where you can clearly see that model water vapor content has been modified with respect to the observed lightning incident.
Second question is about observational operator for this lightning assimilation.
Yeah, group L mixing ratio we have used, sir.
No, it's about the operator, basically observational operator, not the variable, not the model variable.
Yeah, this is the gridded flash sheet, sir. And
okay.
Also, yes.
Thank you, Dr. Banik. Yeah, thank you very much. So the next speaker for today's session is Imran Ali M. Momim from INSEAMA WF, who will talk on evaluation of global NEMO-based ocean analysis in the tropical Indian Ocean. Welcome, M. Momim. So you have 9 minutes to present. Yeah.
Can you see my slides, sir?
I can see your slides, but it's not full screen yet.
Now it's full screen?
Yeah, now it's full screen. Please go ahead.
Yeah, good afternoon. First, I would like to thank organizer Intromet and chair for this session, Professor Chandrasekhar, for providing me an opportunity to present my work here. My title is Evolution of Global Nemo-based Ocean Analysis in the Tropical Indian Ocean. And my so next, for any global ocean analysis, we require the dynamical model. So here we use the global NEMO ocean model as a dynamical model. And this is a state-of-the-art model used for ocean forecasting, research activity, and climate study. And in NCRWF, this model is used for studying the ocean dynamics and thermodynamics, and also initializing our global couple model for studying the weather and climate. Left-hand side is shows the bathymetry of the curvilinear grid NEMO ocean model grid resolution, and right-hand side is our couple model that is already described by Dr. here in NCRW, Dr. Ashish Mitra. Data assimilation, that is the mathematical process to combine the observation and model to produce the global ocean analysis or analysis. And the basic input to the assimilation is the difference between the observation and model prediction. So that is called the innovation. And output of any assimilation is the residual. That is nothing but the difference between analysis and observation. So we require the two kind of information. One is observation and second one is background. Here are the some of the advantages and disadvantages. Observation are different types of observation, and these are the noisy and insufficient, and they are mostly scattered and non-uniform observation. Whereas the background is either from the climatology or dynamical model, and it is a filter out the noises, filter out, and it is complete coverage. So in observation, the error is mostly coming from the representation error and instrument error, and in the background error is due to the initial condition and imperfect model circulation. So these are the error in the observation and background. So now coming to this assimilation. So assimilation here is used the NEMO variational data assimilation. This is the model is NEMO 3.4. Resolution is 0.25 by 0.25, 75 levels. And assimilation technique is the 3D bar, first guess at appropriate time. Assimilation window is 24 hours. And for driving the model, we use the NCMRWF unified model as a forcing. And these are the various observations are assimilated: SST, temperature, salinity, sea level anomaly, and CS concentration. So below part is the frequency of the forcing, that is 1 hour for wind, and for radiation force, it is 3 hours. So right hand side, if you see the assimilation technique, that is the 3D bar, they have two components. One is the background term, and second one is observational term. So in this cost function, so important thing is B and R. B is the background error covariance and R is observational error covariance. So this is the main error, background and observational errors are main to decide how your analysis is going. So in the below part, I am just putting one image. This just give you an just show you, if your weightage is more to the forecast model, your analysis is towards the background. And if you have more weightage to the observational error, so your analysis is towards the observation side. So coming to this assimilation cycle, here we require the two information as we discussed above. One is observation, and second one is from the short forecast. So here both the information are fed up in the data assimilation system, and that generate the increments, and that increments are run along with numerical model to generate the analysis and the forecast. So right hand side shows the linear balance relationship. So after the assimilation of observation, we have to follow some kind of physics For example, any change in a temperature, that will also change your sea surface salinity. And the change in temperature and salinity, that again change your density. So this physics must be followed. Your hydrostatic balance, that is change in a sea surface height, and your surface current, U and V, that is follow the geostrophic balance. So any data assimilation, this balance relationship must be followed. So lower part is showing the observation, the various observation which are assimilated into the system, the GHR SST, in situ SST, temperature salinity profile, and altimeter. And right hand side is after the assimilation, the models generate the increments, data assimilations generate the increment file. So this is the sea surface temperature increment, sea surface salinity increments, sea surface height, and sea ice increment. Coming to the assessment part, here we use here the 2 years of analysis, 2016 to 2018, and the parameter used is temperature and salinity profile and surface current. And the observation used for the validation for assessment is Ramabuoy and Argo observation. And quantitative assessments are carried out mean, RMSE, standard deviation, and correlation. And right hand side is shows the location of the Ramabuoy observation during the 2016 to 2018 year. The below part is the surface profile. So only 3 Ramabuoy observation, we have continuous observations. So we only use the 3 Ramabuoy for the temperature salinity bias assessment. And here we found that the surface are well for the temperature case. The bias is very less, is less than 0.5, less than 0.5. But if we come to this right hand side, the salinity part, we find that there is a large error in the surface as well as the subsurface. And mostly error is over the northern Bay of Bengal region. It is 12 degree north, 12 degree north and 15 degree north. So coming
Hello.
and if we come to this lower part, that is the variability. The variability is well.
So you have just 2 minutes, huh? You have to wind up. Yeah. You have 2 minutes to complete. Please.
Yes. So this lower part is a standard.
Share the screen.
Yeah, please put it, take the full screen. Make it full screen.
Now it's
now it's
full screen.
Yeah, yes. Yeah, please, please complete. You just have 1 minute.
Yes, I am completing this. So lower part is the variability part. If you see, the variability is also well simulated, but mostly variability is high at the subsurface thermocline depth. That variability is more. Now coming to this Argo part, here we see the SST part, the variability is more, this circle represents the variability is more over the region where the RMS is more over the region where the variability is high. Similarly, if we come to the sea surface salinity, the RMSE is more in the region where the high variability, and this is the Bay of Bengal region. So coming to this profile part, the temperature and salinity profile, if you see here, the bias is a negative bias in both the temperature and salinity case, and the negative bias indicate the NEMO is underestimating the variability. And if we come to this right hand side is the sea surface salinity, and maximum impact is in the Bay of Bengal where the RMS is high and bias is also high. So coming to this surface salinity.
So your time is up. So I think you need to wrap up. Yeah.
We also from the new analysis.
Yeah.
Yes, I'm just this is slide.
Highlight only the pertinent points and then conclude. Hello. Yeah, please share your screen and just conclude. Huh? Yeah, I think your time is up already. Yeah.
So this is my final. Can you see my slide?
Yeah. Please go ahead. Yeah, we can all see. Yes.
Yeah, this is my final conclusion here. The 2 years of reanalysis of the data we evaluated against the Ramabuyan observation. And here we found that the RMS is high in the northern Bay of Bengal region with respect to the Ramabui. And with a comparison with the Argo, found that the high SST RMS in northern Arabian Sea and high SST RMS in northern Bay of Bengal region. And finally, the surface current has a larger RMSE and more variability in the equatorial Indian Ocean region.
Yeah, thank you, Mr. Imran Ali. Yeah, any quick questions or comments are welcome. So there are no questions in question and answer. Thank you, Mr. Imran Ali. Okay, the next speaker is Dr. George from Ministry of Earth System, Ministry of Earth Science, MOES. Mr. Gilby.
Sorry, my affiliation is NCMRWF.
I'm sorry. I think institute is written as Ministry of Earth Science. Anyway, it doesn't matter. NCMRWF comes under that. So please start sharing your presentation.
Okay.
You have 9 minutes of presentation time.
My screen is visible?
Yeah, it's visible. Full screen is visible. Please go ahead. Yeah.
So I'm going to present the use of hairless horizontal line of sight wind observation on NCMRWF Unified Modeling Data Simulation System. So here is the outline of my presentation, and this is the famous schematic representation of all types of observation which are used in the almost all the data simulation system. And the AOLS satellite is one of the new addition. So the satellite is having a inclined polar orbit, and we are using the L2B data set. So level 2B data set, and it is a bin average product. The bin dimension is mentioned here, 500 meter vertical and 86.4 kilometer horizontal, and the average data is representing the center of gravity of the bin volume. And these are the various data set which we are used in the NCM Global Data Assimilation System, and HLOS wind is a new addition. And this is the global coverage of the observation, and the lower panel is showing the data used, and the time series also showing the statistics of the count. And the table has shown the details of the data quality control, and we are using 80 kilometer horizontal and 1000 Pascal vertical interval for the thinning to avoid the spatially correlated observation error. And this is the details of observation operator. We are having the observation at the center of gravity. So the model variable is also taken to the center of gravity, and it is converted to the horizontal line of sight using the relationship at the bottom. And this is the triple collocated verification of the observation. In the first first set of figures, we are comparing the ALS observation with the Sonde and NCMRWF unified model background. So this is triple collocated. The 6 figures on the left hand side, and on the right hand side we are comparing ALS observation with the atmospheric motion vector and NCM background in another triple collocation. And the statistics are given. I am not going into much details. This is the model details. We are having first 50 iterations with N144, that is almost 90 kilometer resolution, and from 51 onwards we are having 40 kilometer resolution, and the forecast model is of 12 kilometer resolution. Number of vertical level is 70, model top is at 80 kilometer, and time step is 5 minutes, and assimilation cycle is 6 hours, and the background is written in 1 hourly interval. And here we have the hybrid 4D system with a weight of 0.3 for the flow dependent error covariance coming from the ensemble system. And the left hand side, we can have the impact of various observation types. So as an volume per day, the impact per day, we have ATOS observation is having the top impact 17.5%, and which is followed by IRC 15.1%, and so on. And HLOS wind is having the 9th position in impact per day, which is almost 3.6% of the total impact. And in impact per observation, the HLOS observation is having an outstanding position. That means it is comparable with the aircraft observation is having the maximum impact per observation, and HLOS as well as the atmospheric motion vector is having almost comparable impact per observation. And from the assimilation analysis increment difference, we can see that zonal wind over higher altitude is having a large impact. And from impact on background fit, we can see there also the Sonde 500, Sonde 250 hectopascal level, satellite wind, zonal wind from the satellite AMV, and the aircraft observation is are having more positive impact. This is one of the case study of the previous monsoon onset, and which is followed by Nisarga severe cyclonic storm. So on the date of onset, we have a very good strong convection over the Kerala coast region. So we have declared the onset, but it is followed by a severe cyclonic storm Nisarga, which is one of the rare case. As we know that during the active phase of monsoon, we don't usually we don't have any cyclonic storm. And here some details which we have got by assimilating the Aeolus observation. So the first figure is from the control experiment, and the second one is the same plot for the assimilation with Aeolus, and the third one is the difference between the experiment and control. In the second row, we can see that in the difference, we can see the shading is indicating the zonal wind speed, and the vector is showing meridional vertical wind vector. The shading in the difference, we can see that there is a zonal, there is an easterly in the difference, not in the mean. So which is an indication of weakening of vertical shear of zonal wind. So the vertical shear of the zonal wind is the main factor which suppresses the intensification of cyclonic storm.
Dr. George, you have one more minute. Yeah.
Okay.
So you have one more minute to complete.
The first six figure on the left hand side is representing the 24-hour forecast, and right hand side is the 5-day mean forecast. Here also we can see that zonal easterly component along the equator, and on the Walker also we can see that same factor, which may be one of the reason for the formation of Nisarga severe cyclonic storm because of the weaker vertical shear of zonal wind. So this is the details from the operational assimilation this year, and this table compare the impact per day. So we have seen that Atos is having the maximum impact per day, 17.5 on the pre-operational experiment, but in the operational use, the impact is increased to 19.2, which may be due to the METOP C observation newly added to the data set for the operational
Dr. George, your time is up.
IRC also
Please
have
conclude.
increased its impact, and the Aeolus wind, in the pre-operational experiment, it has having 3.6%, and it is slightly reduced to 2.8, which is mainly because the pre-operational experiment is done in a lag mode, so all the data set in the time window will be going. So in the operational case, it is in the real time, and the input data volume will be slightly reduced. So that
Dr.
is the reason
George,
for
your
the
time is up.
reduction.
Please
So,
conclude. Yeah, please conclude. Your time is up.
Going to conclusion. So this is the time series. The top one is the impact, and so top one is the observation volume, and bottom one is the impact. So we can see that it is having the beneficial impact throughout the period, and it is never it is having any deteriorating impact. And this time series is made for the IMDA domain. So it is 30 degrees to 120 degrees, and 15 degrees south to 45 degree north. And the main conclusion is that on real-time use, the data volume and the impact per day is slightly reduced compared to the pre-operational experiment, but still it is beneficial.
Thank you, Dr. George. So
this is one of the previous paper on the pre-operational experiment. And thank you.
So your time step, you mentioned it is 5 minutes. I think it is 0.5 minutes.
That is model time step. Assimilation window is 6 hours.
No. So you have written your horizontal resolution is 12 kilometer and time step for forecast is 5 minutes. I think it should be 0.5 minutes. You cannot have 5-minute time step for 12 kilometer resolution.
I'll check it.
So it should be 0.5. It should be 30 seconds. Are there any more questions? I think it's a typo. Yeah. So are there any questions? If not, let us thank Dr. George. Thank you very much for a very, very interesting topic on use of LO's horizontal line of sight observation in the global NWP system. The last speaker of the session is Dr. Prashant Kumar from Space Application Center, Ahmedabad. And he will be talking on fostering the need of L-band radiometer for extreme oceanic wind research. So I invite Dr. Prashant Kumar. So you have 9 minutes to give your presentation and 1 minute for discussions.
Thank you, sir.
Your screen is already full screen mode. You can start.
Okay, thank you, sir. First of all, I am thankful to INTROMET. My title of presentation is Fostering the Need of L-band Radiometer for Extreme Oceanic Wind Research. So the background of the topic is that ocean surface retrieved scalar and vector winds from space-borne radiometer and spectrometer are very crucial input for the NWP models. So mostly C-band and Ku-band spectrometer are used for the wind vectors, and these vectors are used widely in the operational NWP models. The issue with this wind vectors project as well as wind form radiometer is that whenever the wind conditions are more than 30 meters per second, something with a high wind speed, these microwave sensors are strongly affected by the precipitations as well as convective clouds. And over those regions, the retrieval from these satellites are not very good. So the objective of this study is that first I want to compare the various instruments like ASCAT, which is a C-band spectrometer, SCATSAT-1, which is a Ku-band spectrometer from India, a analysis, analysis, and a reanalysis ERA5 with respect to the SMAP, which is an L-band radiometer, as well as with the JTWC dataset for 2-year period over the globe. And after that, we try to modify that how the spectrometer wind can be realistically reproduced over the cyclone region where the actual retrieval are not available, and then if we will assimilate these modified winds in the numerical model, what kind of improvement can be possible? So these are the two objectives of this study. So for this purpose, we use the two different spectrometer, ASCAT as well as SCATSAT-1, SMAP wind speed, which is an L-band radiometer, then one analysis and one reanalysis, both are at 0.25 degree resolution, as well as JTWC bed stack data over globe for 2-year period. So this is just a brief discussion. When we take the mean wind speed over the globe for a period of different years, what we find out that most of the wind vectors are available within the range of 0 to 16 meter per second. Means almost 92-94% data are available in this region, which very precisely explain the mean wind condition over the globe. Whereas when we talk about that in the different wind ranges, that what kind of winds are available from these instruments, what we find out that above the 40 meter per second, when some extreme condition occur where the wind speed is more than 40 meter per second, only SMAP, SCATSAT, and NSAP final analysis are able to capture these events. Whereas if a very high extreme wind conditions are available, like more than 56 meter per second, only SMAP is able to capture these kind of events. So existing instruments, except the L-band radiometers, are not able to capture these high wind conditions. So now after that, we also compare these different wind speed with the SMAP data set, and what we find out that means all the product like ASCAT, SCATSAT, NSAP, as well as ERA5 are in well combination with the SMAP data set, because mostly these data are represented for the low wind speed. Whereas when we compare the same data set with the JTWC maximum sustained wind speed, what we find out that these things are very important here, that the maximum wind speed measured from the JTWC PESTEC data set goes up to 70 to 75 meter per second. Whereas SMAP is able to capture this thing, as well as ANSEP is also able to capture these high wind conditions. Whereas both the scatterometer, which we selected here, ASCAT as well as SCATSAT, and ERA5 also, reanalysis also are not able to capture these high wind conditions. And in the lower plot, you can see that very large errors are found in both the scatterometer as well as in the ERA5 reanalysis for high wind conditions. So this is one of the major area where we need to correct the satellite retrieve product. So this is the one of the objective also. So what we did here for the high wind condition, when scatterometer winds are flagged due to precipitation. So what we did, we performed a histogram matching with the SMAP data set for a 2-year period. And wherever the rain flag is available over the scatterometer pass, and the conditions of high winds are available from the JTWC, we prepared a histogram matching. And what we find out that this is just a plot, a default plot, which is available from scatterometer for a cyclone. And then after correction, what we find out that the values over the near the eye of the cyclone, the tropical cyclone, are able to capture roughly the JTWC observed wind speed are around 60 meter per second. And after this correction, we are able to correct the scatterometer wind up to 50 meter per second. So these corrections are implemented for the scatterometer winds conditions. And then we try to assimilate in the weather model. So again, when we assimilated these winds, high winds, because generally models are not having these high winds in the background. So we need to prepare a dynamic observational error for the high wind as well as low wind conditions. And then we try to assimilate these observation for the for a very high severe type tropical cyclone. Marcus is the strongest tropical cyclone to affect the city of Darwin, Australia. And what we find out that means this modified scatterometer wind, which we defined as a SCAT-M as a green color, are able to capture the track with less error as compared to the normal scatterometer conditions. With this, we also find out that the reduction in the intensity is very high when we assimilated this modified scatterometer wind conditions. So the conclusion of this study is that except SMAP retrieve wind, which is a L-wind radiometer, no other selected data are able to capture wind speed more than 56 meter per second. It is also observed that only SMAP and ANSEP analysis are closer to JTWC within this study, and results suggested that most of the high winds near storm from ASCAT and SCATSAT are flagged as rainy pixels, and this is the concern because of that ERA5 data also have not very high wind conditions. Furthermore, we also performed the modified scatterometer wind, and we assimilated in the WRF model using variational method, and what we find out that these assimilations improve the track and intensity predictions. So more detail about this study are available in given references. Thank you.
Any questions, clarifications, comments? Yeah. So Dr. Prashant, I just have one small clarifications. You said that very high wind speeds, like 56 kilometers, 56, I mean, whatever, meters per second and all, you're using.
Meters per second.
Yeah. So basically you're using these L-band radiometers, right? From, and then you said that you took this tropical cyclone case of Australian coast, and then you showed that a big impact is there. So instead of just only modifying only those regions which were like high wind, which the other scatterometers could not like sort of reproduce. So why don't you use the entire thing from this element? So,
yes, sir. Definitely, one very good point that SMAP element itself can be used as a complete, but the concern with radiometer is that they are only providing the scalar winds, means only wind speed, but direction is not available from the radiometer. So, and after this correction, what we find out that from the spectrometer, we are able to get the high wind as well as wind direction also.
okay. So both will serve the purpose. So
yes, sir.
So it's a very interesting topic. Yeah. So if there are no questions, let us thank Dr. Prashant Kumar of Space Application Center, Ahmedabad. And I also wish to thank all the people, all the members who gave the lead talks as well as the invited talks, as well as those who make presentations. So I thank all of them for maintaining the time, and we could complete the entire session. We did extend by about 10 minutes, which is, I think, fine. So thank you. I also thank the organizers of INTROMET 2021 for giving me an opportunity to chair this session. Thank you.
Thank you, Professor Chandrasekhar, for chairing this session. So the next session will start at 4:20. So we will reassemble at 4:20. Thank you.
Thank you. Thank you.
Hi, welcome all to the technical session TS4A of INTROMET 2021. So this session is for early career research session on our changing climate. So in this session, we have Sri Anand K. Sharma to chair the session. And we have one lead talk and one invited talk, followed by 5 oral talks, I think. So Anand Sharma is working as Additional Director General, Scientist G, Head at Regional Meteorological Center, Indian Meteorological Department, New Delhi. He was a Deputy Director of General of Meteorology in the Regional Meteorological Center, New Delhi. He was the founder director of Meteorological Center, Dehradun, 2002 to 2015. So the lead talk is by Dr. Ajay Mohan. Ajay Mohan is a senior scientist at Center for Prototype Climate Modeling, New York University at Abu Dhabi. He's a climate scientist with interest in climate variability, climate modeling, and data analysis, specializing in tropical convection and monsoon variability. After that, we have an invited talk by Dr. MCR Kalapureddy. He's a scientist E at Indian Institute of Tropical Meteorology, Pune. His research mainly focuses on remote sensing in the atmosphere, clouds, and precipitation studies.
Yes,
With this, may I invite the chair, Anand K. Sharma, to take over the session. Thank you.
Thank you very much. Good afternoon and to everyone. And before I think we invite the lead talk, again, I want to congratulate Cochin University, especially the Center for Atmospheric Science, for taking this lead and organizing this Intromet in an excellent manner. And I wish them all the best for this, and I'm also thankful to them for giving me this opportunity. So without wasting time, I think I will invite Dr. Ajay Mohan, who is a lead talk speaker. He's from NYU Abu Dhabi, and he's going to talk about how climate models got so accurate that they earned a Nobel Prize. Over to Dr. Ajay Mohan.
Okay, thank you, Dr. Sharma. And let me first thank the organizers for inviting me for this talk. This is probably a good lead talk to start a session for early career scientists. And also, let me thank the organizers for the excellent arrangements. I've been listening few sessions in the morning. It was very audible from here in Abu Dhabi. So let me go straight into the topic. The 2021.
Sir, full screen mode. Slide.
Oh, okay. Yeah. Okay. 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 The 2021 the Nobel Prize has been awarded to groundbreaking contributions to our understanding of complex physical systems. And this is quite exciting for most of us who have been working in the field for more than almost 20 years or even more than that. So, it's quite certain that we all got excited with this news. And this has been awarded to 3 scientists. The half of the prize has been given to Giorgio Parisi for the discovery of the interplay of disorder and fluctuations in physical systems from the atomic to planetary scales. So this is a citation from the Nobel Committee. And the 50% of the prize has been given to Shikuro Manabe and Klaus Hasselmann for the physical modeling of the Earth's climate, quantifying variability and reliably predicting global warming. So this talk will outline only the contributions of Manabe and Hasselman, and that is actually relevant for the entrapment. So I will go through some of the developments which has happened and why this is important. And of course, these two scientists are legends in our field. So it is almost impossible to summarize their contribution in 20 minutes. But I will try to do quickly go through and give a reasonably good idea. So Manabe, Manabe showed us how and why increasing carbon dioxide level leads to global warming, while Hasselman showed that it is actually happening. So that is the statement from John Stevens. Of course, this is work by these two scientists, and I would like to acknowledge several online material, published papers, documents provided by the Nobel Committee, so on and so forth. I have tried to acknowledge it in most of the slides. If I have omitted something, please do excuse me. The outline of the talk is based on some of the most common headlines, which are so-called, which are seen in the media after the award has been done. So the climate predictions were treated with heavy skepticism just 30 years ago, but they have become our main window into how global warming works, and that's true. I mean, like if you look into the talks in the earlier session, also where they were been showing the developments in the past 10-15 years, and we see huge improvements. So this is more so when you go back to 1960s onwards. So why climate modelers deserve the physics award? They have proved right again and again, and obviously the pioneering role played by these two scientists in developing the in laying the foundation for the development of the system models. So before going, so this is the first time probably the Nobel Prize is awarded for research on complex systems. So it is very difficult to define even a complex system. Okay, so in such a scenario, understanding the nature of disorder of complex system presents an enormous scientific challenge. In that context, the first time award of Nobel to research in complex systems assumes significance. This is coming from Goran Hansson, Secretary General of Royal Swedish Academy of Science. Many of you might believe that physics is only about simple and orderly phenomena, but physics is much more than this, because it uses basic theories to explain the world's vast complexities. And these studies, this is the key point, these studies require deep intuition into what structures and progressions are essential. Okay, and the things at which this year's laureates are true masters. This is very important because the limitations of in the 1960s, both in computational and the development of the climate model was huge. At that time, to think about and to about the climate models, you need to have some deep intuition. Okay, so that is one of the reasons why this one of the prime qualities of these two scientists. So without soberly probing into the origins of variability, we cannot understand the behavior of any system. Okay, therefore, only after having considered these origins do we understand that global warming is real and attributable to our own activities. The primarily these two people primarily answered, and many, I mean, only two people got the award, but there are many who have been working on this field for several years. So is the primary questions the committee considers is yes, heating up? Yes. Is the cause of the increased amount of is the cause of heating up is due to the increased amount of greenhouse gases? Yes. Can this be explained solely by natural forces? No. Are the humanities emission for reasoning for increasing temperature? Yes. And all these questions have been answered by this state-of-the-art climate models. So that's why the climate models deserve the Nobel Prize. So above all, physics applied to greatest benefits of humanity is fundamental. So now Before that, some awards has been given, like in chemistry, the ozone depletion, finding of ozone depletion got award. And obviously 2007, the IPCC Peace Prize has been given to the Peace Prize, the Nobel Peace Prize has been given to IPCC and Al Gore. And 2018 Economic Prize has been given to William Nordhaus for his work in interaction between society and climate change. This is a statement from Gavin Schmidt, who's the director of NASA Goddard Space Center. So he thought that this, that the climate scientists will never get an award. The reason is this field is widely multidisciplinary. It's this encompasses biology, chemistry, history, paleoclimatic, fluid dynamics, applied maths, and so on and so forth. So because of that multidisciplinarity, I had always assumed that climate science would never attract the attention of disciplinary prize candidates. So that is his thought. And it is largely true. So in any prize, more than several people are deserving, only few will get it. But climate sciences, there are several people who are been working because it's largely multidisciplinary. Okay. So now I will not go through the history of this thing, but at least give you a few idea of how it has been evolved. In 1820, almost 250 years ago, Joseph Fourier actually gave an idea about the greenhouse gas effect. He found that atmosphere acts as an insulator, and this is the first time that we see that this greenhouse gas. Although the greenhouse gas name came later, this is the first time that has been identified. And then, John Tyndall in 1861, he's a pioneer in this field. He did a lot of experiments. So one of the prime thing, like oxygen and nitrogen, which contributes almost 99% of the atmosphere, almost to have a very little effect on maintaining the surface temperature of the Earth. So that came from John Tyndall. And then obviously Arrhenius, who he's also a Nobel laureate. He actually is the first one who did this climate sensitivity study, which is found, although his estimate was around 6 degrees centigrade, which is largely above what we see, but with the doubling of CO2. But it comes in 1896. So the understanding of electromagnetic spectrum and the properties of gases were limited at that time. So but later, there were several studies, and of that, the important study is from Callender, who found the pioneering the dominant role of ocean in taking the carbon sink. And then, of course, in 1916, Keeling came with this Keeling curve, which started measurement of CO2 levels, and the currently CO2 level is around 414 ppm. So this is which is 800,000 years ago, the CO2 has not been higher than 300 ppm. So that understanding is what comes from these continuous measurements from 1960s onwards. And then came Manabe and Butherland in 1960s. They actually did the first climate model, development of the first climate model. So I'll come into the details of that particular study. So before that, a few personal things about Manabe and Hasselmann. Manabe was born in 1931 in Japan, and then he moved to US Weather Bureau, which later became the GFDL lab. And Klaus Hasselmann was also born in 1931. He's also the founding director of MPI Hamburg. Okay, now to the development of atmospheric models. In 1950s, we know that Jules Charny and John Newman came with this development of the first atmospheric model, and it took almost 24 hours to predict 24-hour forecast. See, the whole idea that you can take something so complex as a climate system and code the equations and that govern it and put them in a computer actually was started by these pioneers who thought that this is actually possible, and that's how this whole development happened. Okay, this is again a statement from Manabe, who was actually invited by Joseph Manossi, who was the instrumental in developing the GFDL lab. So he moved to US from Japan and started working on numerical modeling. This group at that time itself has an idea of developing an Earth system model. This is the early 1960s. So this is the important paper which the Nobel Committee cites about Manabe's work. Obviously, he has several other works, and he has been working for the past 60 years. Both the scientists are in their 90s and they are still active. For the almost 60 years of their hard work has been recognized now. This particular paper actually has been cited as one of the most influential paper in the climate science. Actually, it is voted by climate scientists in a survey conducted by the site Carbon Brief. So what is so important about this paper is that it predicted the right amount of warming at the surface. This is in 1967 paper, around 2.4 degrees centigrade. And more than that, it also predicted that apart from stratospheric warming, the troposphere would cool. I'll come into the details of that. Actually, that particular aspect has been taken as a fingerprint later by Hasselmann to understand the human influence of climate. So what is a big deal in this paper? Okay, that part is very, very important, because even the best computers in the world at that time is less than power for any of your mobiles today. So what is important is that one need to have a very simple model. Okay, you need to make the physics very simple. Okay, that is the beauty of that model. The physics employed is very simple. And many of the things are unknown. The number of vertical levels used in the model, what kind of greenhouse gas, because apart from carbon dioxide, methane, water vapor, everything is there. So what all the gases has to be used, what has to be varied, and all that. So not much idea. So a lot of intuition and thinking has gone into that paper. It predicted a warming of something like 2.36 degrees Celsius with the doubling of CO2. Today's best estimate is 0.3 degrees Celsius. Above all, what do you call this radiative convective adjustment has been actually done, because when you have carbon dioxide, more carbon dioxide, the atmosphere will warm. When you have more warming, you will have more water vapor in the atmosphere, you will have more moisture in the atmosphere. So moisture again is another powerful greenhouse gas that will again increase the warming. So it's a positive feedback mechanism. So you need to have that radiative convective equilibrium. So because the vertical structure of moisture has to be incorporated. So that is something which those studies, the previous studies before this paper was struggling to do. So that is something which Manabe were able to do. This is from Manabe's word. You cannot compete with the complexity of nature. So there is so much physics involved in every raindrop that would never be possible to compute absolutely everything. Okay, so this is the paper in that paper. So the Nobel Committee has beautified that paper. So the three levels of CPM, CO2, 150, 300, and 600, and the carbon dioxide, and they find that 2.360 degree increase with increase a doubling of CO2, and 2.28 decrease with the halving of CO2. So what is important is that Suki incorporated this effect to a simple algorithm called convective adjustment. So that radiative convective adjustment is been incorporated. Apart from that, this stratospheric cooling, okay, so that has been finally, so with the increase in tropospheric warming, the stratospheric cooling also will happen. So that is actually the prime finding of this paper. So these are the two papers which actually led to this 1967 paper, which they actually talk about radiative equilibrium. So I will not go through these slides because I want to cover Hasselmann's contribution also, but there are several other studies. I mean, there are few slides needed to list Manabe's studies. Okay, and I have already told these points. The legacy of this work is that they were a champion of simple atmospheric modeling. So although the models has become complex from simple radiative transfer model to a Earth system model, you actually need that kind of simple modelings to understand the the basic physics. So that is something which came from Manabe. So this is a book from Manabe. You can read more about him. So now to underpin this contribution of Hasselmann, actually, if you look into the IPCC reports from 1995 to 2021, earlier we were like a balance of, we were like thinking that this will happen. The balance of evidence suggests that a discernible human effect. It is extremely likely that human, but with 2021, we say for sure that it is unequivocal that human influence has warmed the atmosphere. How does that understanding has changed? So that is where Hasselmann's contribution comes. So I'll quickly go through it. Okay, this is Lawrence study of sensitivity to initial conditions. This has been referred in the earlier talks as well. So in practice, this means that it's impossible to produce long-term weather forecasts. That was the understandings in the 60s. But then Hasselmann came with 1976 seminal work, which involved the creation of a stochastic climate model that shows how weather disturbance could be integrated into a larger, more stable atmospheric and ocean circulation patterns to produce changes in climate. So this is the first study where how this, you need to actually consider the chaotic weather also, and how to include those chaotic weather into the to treating a long-term climate prediction. So that understanding came from him, and then he went on using that same thing. He went on to look into the signal to noise noise ratio. So that actually became a statistical roadmap for detection and attribution studies. So detection and attribution studies are studies where there is a warming happening or there is an event happening. How is that being? Is it due to a human influence? Is it due to warming? So that human fingerprinting technique has been actually comes from these basic studies of Klaus Hasselmann. So in 1970, there was an understanding that there is both signal and noise. So the signal was a climate response to the external pattern, whereas the noise arose from internal climate variability. So that understanding came into with these studies. So instead of looking for a needle in a tiny corner of a large haystack, because of the grid point statistics, Hasselmann advocated for a more efficient strategy, searching the entire haystacks simultaneously. So for example, changes in solar irradiance, volcanic aerosols, greenhouse gases produce signals with different patterns, amplitudes and frequencies. So with that differences in changes, you can actually identify fingerprints. So that's how we that's how that understanding of optimal fingerprinting came in. So later, this has been modified a lot. So this is a study from Hegel and Swayze, where the surface temperature has been looked into until 2010. So the black line shows observation, the blue lines shows only natural forcing, and red line shows the effect of both natural and so you actually need both natural and anthropogenic forcing to explain the actual change in surface temperature. Okay, so this. So I will not go into details of this, but optimal finger technique is exactly a technique. Excuse
me, Dr. Ajay Modi, I think 20 minutes are over. You are left with only 5 minutes, and we need to have
I'm winding up. I'm winding up.
So please.
Okay. Yeah. Okay, it's a multivariate regression technique, and through years of refinement, this has been happened. I will just go and take one toy example just for you to understand this thing. So in all climate models, this is like what we see, all factors. In all climates, and when we are, you have tropospheric warming and stratospheric cooling. When you have sulfate aerosols around, which has sulfate aerosols actually scatters the solar rays, so you will have tropospheric cooling. When you have stratospheric and tropospheric ones, like in CFCs in the atmosphere, you will have more stratospheric cooling and which will more tropospheric warming. When you have sun alone, the entire vertical column is heated, okay, which is not the case. Actually, as Manabe has shown, we should have tropospheric warming and tropospheric cooling. But so from this is inconsistent with what our observations are. So which means that that is a fingerprint. That sun is the sun is not the one which is causing. Similarly, for tropopause height, or all these things. Okay, this technique has been developed very much. We can understand that the change is happening due to human influence. So now, just to discuss the last point, these studies came at a time when your computational limit is very limited. It's a 0.5 milli per RAM was been used for the 1975 Manabe and Netherlands study, whereas it's almost increased by 10 raised to 10 or even more. So this the top number is something like 0.1 petaflop. India has now think of like 6.3 petaflop of computing power. So with that, the progression of the models has improved. So many things has we have now this is complexity of the model versus complex. So ESMs are having highly complex, but at the same time it is comprehensive as well. So the largest uncertainty actually comes from scenarios. We don't know what actually is how to define the scenarios, but the scientific uncertainty has reduced. This is from a paper from Hawkins and Sutton. So all these news about the COP26 and all. I will just wind up the talk with the last thing. For the future generation, we have to act now in a very fast way. So as if the Nobel Committee was sending a message to this, the award came before the Nobel Committee, before the COP26, to the world. Then what Göran Hansson has said, what we are saying is the modeling climate is solidly based in physical theory and solid physics. He added that global warming is resting in solid science, and that is the message. So that's a very powerful message that the climate models are actually giving a is resting on solid science. Okay, and I will stop here and take questions. Thank you.
Hello.
Yeah.
Am I audible? Okay.
Yes. Yes.
I'm just checking. Next presenter. Can I share my screen?
Oh, okay. I need to stop sharing, right?
Sir, kindly unmute your things.
Yes.
शर्मा सर, आपका माइक्रोफोन ऑफ में है, माइक्रोफोन ऑन करना है.
Sorry. Thank you very much, Dr. Ajay Mohanji, for an excellent, simple talk, explaining very nicely the groundbreaking contributions to our understanding of complex physical systems by Mene, Hazelman, Parisi, who got the Nobel Prize, and it's an honor for all the atmospheric community. Especially Mene used the state-of-the-art climate models, and they simplified the modeling approaches, which could provide more understanding about our atmosphere. And you have rightly traced the history of atmospheric science, and very well said at the end that there's a simple message: global warming is not just it's a fluke kind of thing. It's based on solid science. So rightly, these researchers have been given Nobel Prize, and it will, augur good for the atmospheric community in totality, and will definitely, it will motivate many young researchers to take this field and make more and more contributions. So thank you, Ajay Mohanji, for an excellent talk. Now I invite our next speaker, Dr. M.C.R. Kalapureddy, who is going to deliver an invited talk on cloud radar technique, inferred cloud vertical structure, perspective on early identification of ISM vigor, and he's from Indian Institute of Tropical Meteorology, Pune. Over to Dr. M.C.R. Kalapureddy.
Very good afternoon, sir. Sharma sir, am I audible?
Yes.
Could you see my screen? Is it full screen?
No, it's not visible right now.
Not visible?
now we can see your name, but your screen is not coming.
So
just check at your end. Yeah, now it's there. Yes.
There?
It's there.
It's full screen, right?
Yes.
Very good evening to all of you. So welcome to the topic. And first of all, I would like to thanks to INTROMET organizers for selecting me as a lead author. Lead presentation, for inviting me to this presentation. Here I would like to present a cloud radar technique, a ground-based cloud radar technique in further cloud vertical structure or vertical structure of a cloud is prospective on early identification of Indian summer monsoon. Most of the Indian summer monsoon research has evolved and better understood with the surface rainfall observations with a simple rain gauge and networking or gridding of the data, and better further the remote sensing satellites and maybe active remote sensing, passive remote sensing will allow the larger aerial observations of the precipitating cloud systems and non-precipitating cloud systems. However, here I am going to present a ground-based cloud radar because the satellites having a problem of time limitation. They cannot able to give high time resolution, whereas aerial observations are very good. So the ground-based observations can give a scanning radar can able to give a much better understanding of this one for the further betterment of the Indian summer monsoon understanding and maybe the climate predictions. So this is Madhu, and with my team, and Govind Panditra is our lead of this program. So my slides are moving, right, sir? Yeah. So my backdrop is that so the Indian summer monsoon rainfall observation and its anomaly during a active and break spells are clearly shows there's a central India and west coast is very dry during the monsoon dry phase. There's active phase. There is a very wet. That means more amount of rain. So the red line is the climatological mean rainfall, whereas the bars are the real daily rainfall, and which is if it is much below the 1 sigma level, below the red curve, they are called the break at the central Indian region, and much above this red line is called the wet spells. So these active and break spells will come in a couple of days to a week time. So during that time, so the star region is the place where we have the ground-based cloud radar. So which I'm going to explain. So that cloud radar observations during the active and break spells for the central India has been taken with the Rajiv in 2010 things, and those the basic understanding is that the rain over the surface rain observations is given a phenomenal understanding of Indian summer monsoon. For better understanding in the future and deep understanding, we need to understand the rain giving clouds. That means the clouds, we have to understand the complete about the clouds which is precipitating and non-precipitating. And over the tropics, there are the three types of clouds. One is a shallow clouds whose tops will not extend more than 0 degree isotherm. So we have considered that below 0 degree isotherm, that is less than 5. So whatever we are having a radius on the observation for over the Mandar Devi. So with that, wherever the 0 degree isotherm things, we find that it's 5.3 kilometers from the mean sea level, and whatever the clouds is coming below is called the low level cloud in a macrophysical point of view, warm clouds in a microphysical point of view. And when the temperatures are much less than minus 38 degrees centigrade, so water cannot exist into a liquid anymore, and it's completely solidified. That is called the high level cloud or the mixed phase cloud, that comes around 10.8 kilometers and above. So by this distinction, low cloud and the region below minus 40 degrees centigrade and 0 degrees centigrade, so it's called the mid-level clouds, that is 5.3 to 10.8, are the cumulus congestion in macrophysical point of view, and a microphysical point of view is the mixed phase clouds. So a cloud vertical structure is one which can able to understand the coupling between these three levels, macrophysically and microphysically. So it is required to understand the cloud vertical structure or a vertical structure of the cloud, how it can, and one of the observations of Krishnamurti and Bhamle has indirectly told that a cloud vertical structure, out of their 9 important elements of the monsoon clouds, cloud vertical structure inherently or indirectly they are inferred. So that's what we are tapping. In order to tap this one, what we have used is the weather radar. So weather radars is having it sends its own power to the cloud system, and the echo, that is the return signal, what it comes. So it called the return power or the reflectivity or the radar reflectivity factor, which is directly proportional to the drops in a millimeter to the power of 6. So sixth power of a drops distribution, whereas the third moment will tell the cloud water content, and the radar reflectivity is because of finite pulse width and beam width. It can be a volume observation to the power of d power 6. So that is called the radar reflectivity factor, and it is the cloud water content. If it is multiplied with the fall velocity, it can give a rain rate. So radar reflectivity Z is a proxy for the hydrometeor concentrations and also rain rate. So with this backdrop, I want to show you that this is a cloud radar, ground-based cloud radar at Mandar Devi near Mahabaleshwar we kept, and very side by. So we are having a centimeter wavelength radar. It's a X-band radar, which is 3.14 centimeter wavelength radar, which is usually a precipitating centimeter wavelength precipitation sensitive radar, whereas the millimeter wavelength radar 8.5 mm. So which is like lambda by 6 or 10. So which is the Rayleigh scattering regions where the linearity will works. So that is the difference between the precipitation radar and cloud sensitive radar. So it is having a sensitivity of minus 45 dBg at 5 kilometers, whereas this is having close to a 0 dBg at 5 kilometers, the precipitating radars. So these two radars in the Western Ghats region, where the Western Ghats, you can see Arabian Sea, mean sea level 0, and it is about 1.4 kilometers from the Earth's surface. So where we are having a high altitude cloud physics laboratory, from there 26 kilometers away of the near same height, we kept the radar in Mandar Devi and used to understand the monsoon westerly winds brought a lot of humidity and they condense to form a clouds and give the first pure amount of rains over the summit. So these cloud vertical structures we need to understand. So for that, this radar in the vertical cloud radar in the vertical looking mode, observations in a day. So just before a monsoon, just before starting, you can see a cloud reflectivities within the range of minus 50 to 30 dBg values. You can see the cloud tops are around 7 kilometers, and there is a convective cloud, and a cirrus cloud can be seen. Very weak cirrus cloud on the top. However, the top portion of the things is the raw, just reflectivity direct measurements. However, it required to screen out for the background noise and the insects and insect secretions or the biological things which exist in within the boundary layer. So that need to be filtered out. The thing is receiver noise and the biota things. If you filter out, you will get pure or a genuine cloud systems. So which can be used for the understanding the radar melting layer regions, that is called bright band, and another one is the convective clouds and cirrus clouds, that is the ice clouds. So this technique is indigenously developed to understand, to remove the biases coming because of the non-filtering of the radar reflectivity. Once you filter, you can see the black part is the genuine cloud reflectivities, whereas the gray is the having the contributions from the noise and the biota. So that if you separate, and you will end up with a genuine cloud information. From that, you can able to understand in the warm phase regions, collision coalescence process and breakup and evaporation process in the 0 degree system, whereas in the higher regions, ice process like halide mosses process or the background filtration process according to the temperature at the head height. So using the vertical observations during the active and dry spells, we can able to see the radar reflectivity is much more than minus 30 dBg and above. You can see that during the wet spells, that is the active phase, you can see the reflectivity is much above 20 dBg, minus 20 dBg below up to 20 dBg, whereas in the dry spell time, the vertical profile of reflectivity can confine much below minus 30 dBg. This is only for reflectivity. If you see the Doppler component in the vertical looking, you can able to find out the fall velocities when it is raining, or otherwise simply updrafts. So you can see during a dry spell, they are much above minus 3 meters per second. Or close to a 0, whereas the spectral width, which can able to tell the turbulence within the cloud or otherwise the drop side distribution, you can see that during a dry time they are much below 1 meter per second square, whereas During a wet spell, they are much more above. So that indicates that they are raining clouds and they are having a dropside distribution. Such observations of every 1 minute, less than a minute observations, we are averaged to hourly and plotted for the 2 continuous months during the active monsoon of July and August 2015. And you can see the shallow cloud tops of only about up to a 4 kilometers cloud tops we can see in the initial phase of the July and for 2 weeks, and after that this cumulus congestus, that means the mixed phase region, that means mid-level regions are much drier, and it becomes prerequisite to form a cumulus congestus, that is the cloud tops up to a 6 to 7 kilometers they are rising, and sometimes we can see a cirrus clouds, huge cirrus clouds of higher reflectivity of minus 20 dBg. They are descending down below the minus 40 things and entering into the mixed phase regions. So this is the one of the region to develop a cumulus congestus to become a deep convection cloud of a cloud top almost reaching to a tropopause height. So we can able to see all 3 types of convection, shallow cloud and cumulus congestus and deep convection in a 40 days period. So, and it is also corroborated with the surface rainfall observations. So that means our cloud vertical structure, more the continuous cloud verticals, more will be the rain at the surfaces. So this is what can be the observations can be seen in Sukanya and Kalpredi in the climate dynamics.
Wrap up the next 3 minutes.
Yes, sir. The descending cirrus clouds, what I say is the cirrus cloud of only thickness of around 1 kilometer, it's becoming almost like a more than 10 kilometers thickness. However, the base of the clouds is having a reflectivity is 50 orders high, and that is indicating that the drop size is increasing because you can see the velocities are much fall velocities are in the order of minus 6 meters per second and above. That indicates that the bigger ice particles are forming at the base and they are releasing out of the things called the sedimentation of the ice particles releasing out of the cloud base. So this is called the descending cirrus cloud. You can see the reflectivity cloud vertical structure. They are from the ice phase, they are very nicely interacting with the mixed phase with the increasing bigger sizes, and the velocities also at that region you can see initially the velocities are minus 2 meters per second and it becomes like a minus 4 meters per second. So whereas during the non-descending cirrus cloud usually seen in the break monsoon time, at that time the cloud reflectivity values are much less than minus 10 dBg. So at that time the clouds are not descending much. However, the wavy oscillation is due to the background winds. So this is what is the important point, and we found that the cirrus clouds is a predominant contribution, the ice water content during the ice and breaks. However, it's a primary contribution can be seen in the active monsoon periods. Same thing is the liquid water contents, and the main thing is the mixed phase regions at the mid levels are playing an important role for the ISM phase to find out. So this is one of the example. The way forward, we are using the scanning observations to understand how these descending cirrus clouds and the rapid secondary ice production like mass-Talus process, how it can be explained. So this is what is the current research is going. So this is the RHI, range height intensity clouds distribution over that HSCPL region. So the main conclusion is that radar input cloud vertical structure shows a much promise in investigating the cloud systems, both macrophysically and microphysically and dynamically, because the diurnal evolutions, which is every 5 minutes observation, can able to understand the convection and PBL dynamics, how the internal dynamics of the monsoon can be understood with this one, and CFED analysis of the cloud radar movements can able to, it gives the contrasting cloud vertical structure pattern to Indian summer monsoon phases, especially the day, on the day when we are observing, we can able to tell whether it's a local active or break condition, and turbulence role in a warm rain initiation process, which is the last point which I have not explained, and tomorrow Sukanya is going to explain this talk. So these are the promises from the ground-based cloud radar technique to understand, especially through a cloud vertical structure understanding. Thank you.
Thank you very much, Kalapuredi ji, for nicely explaining the role of radar in, differentiating various kind of clouds, as you said, low clouds, medium clouds, and high clouds. and you have used two kinds of radars, K-band and X-band radars, and to understand especially the vertical structure of the different clouds, and then thereby understanding the dry and active, or I should say active and break spells in the Indian summer monsoon. And it's a very excellent piece of research. Definitely it will add to our understanding and will be a great tool in the hands of operational weather forecasters in IMD. So with this, I will allow one or two questions if there are from the audience, please. No questions. Very strange. Nobody's asking questions. Excellent piece of research. Yeah, there are no questions. I will. Is there any question? Okay, I have a question.
Yes,
I think
sir.
I would request you to, provide some thumb rules or some thresholds, like you have mentioned. That kind of thresholds and thumb rules will definitely help the operational weather forecasters.
Yes, sir. Definitely, I agree with you. So that is the reason the vertical structure of the temperature I am used here for making, so that you no need of this one, but you require that what could be the reflectivity values is enough.
Yes, yes.
So that is what is the thing. So yes, I am agreeing that for modelers we have to make some thumb rules to utilize this research for the better prediction of the monsoon and a better understanding of the all the cloud systems, which is precipitating or non-precipitating. Then only the better understanding monsoon will come. So that's what is my main stress, that we should go one step back to the precipitation, that is rain, that is the cloud. Once we understand clouds thoroughly, so the great research will evolve. Yes, sir. Thank you very much.
Great. Thank you very much. Keep doing good work. All the best. So with this excellent lecture by Kalapu Reddy ji, I invite now our first oral speaker, Anjumol Raju. He's from SPL, and he's going to talk about an atmospheric inverse modeling approach for assessing CO2 and methane fluxes over the peninsular India using measurements from Thumba. Is he available, Anjumol?
Yes, sir. Am I audible?
Yes, fantastic. Go ahead, please.
Okay, sir. Sir, is my slides are visible?
Yes.
Okay. Okay, sir. Good evening to all. My title for the presentation is An Atmospheric Inverse Modeling Approach for Assessing CO2 and CH4 Fluxes over the Peninsular India using measurements from Tumba.
Just a minute. You have 9 plus 1, 10 minutes. So please
Okay,
wrap
sir.
up in 9 minutes, and then you will have one or two questions. Okay, thank you.
Okay, sir.
Go ahead.
CO2 and CH4 are two significant greenhouse gases present in the Earth's atmosphere, and these two gases are emitted into the atmosphere from different sources, which includes both natural process and anthropogenic activities. After the Industrial Revolution, there is a substantial increase in the emission of these two gases made to the anthropogenic activities, which to enhance the greenhouse effect and global warming. In this scenario, it is very essential to have an accurate estimate of these fluxes for
I think there is some connection problem at the other end. Hello, Anjumol. Are you there? No. I think we have some internet problem at the speaker's end. We are trying to contact her. She is talking, but I think, yeah, we are not able to hear. But anyway, her slide is going on. Hello. She's muted. Oh, she's muted. Yeah, yeah. You have to call her because yeah, that's what happened by mistake. She must have muted herself. Yeah, but then now even her slides are gone.
Sir, maybe network issue.
I think we are having a problem at the speaker's end, so we will invite her again, once again, if we have time. So if next speaker, Arul Lalan, is available, we can invite him. Is Arul Lalan T available?
Yes, sir.
Yeah, great. So please, I think I invite you, and he's from IMD, India Meteorological Department. He's going to talk about prediction of western disturbances tracks using NWP models. Western disturbances, as all of you must be knowing, are very important weather systems in the winter season, which give rain and snow to the especially northwest India, and very useful for agricultural activities. And maybe a lot of water requirement comes from the ice which falls on the mountains. So welcome, Dr. Arulanan. Please go ahead. You have 9 plus 1 minute, 1 minute for the question, and 9. So please try to finish within time. Go ahead.
Sir, is my screen visible?
Yes.
Yeah, okay, so thank you. I welcome for this presentation, prediction of western disturbance tracks using NWP models. Little introduction, like a western disturbance, we know that it's a cyclonic subtension or trough in the mid and lower tropospheric levels, or as a low pressure area on the surface, which occurs in the middle latitude, westerlies, and originates over the Mediterranean Sea, Caspian Sea, and the Black Sea, and finally it moves towards the eastwards across the North India. This is the formal definition by the IMD. And we know that WDs are synaptic scale. It's a vertical perturbation embedded in the subtropical westerly jet stream. They are often associated with extreme rainfall events in the Karakoram and Hindu Kush regions of Pakistan and North India. Also, recent study done by the Dr. Karen M.R. Hand et al. 2017 defined the algorithm to track the WDDs, and they found nearly 3,000 tracks using ERA interim reanalysis from 1979 to 2016. Also, they elaborated the WD tracks in terms of its associated precipitation. In the current study, we implemented the same algorithm using NCMRWF operational global unified model at a 12 kilometer resolution, and using its analysis, also its ensemble forecast. It's like it is having one control and 22 members, forecast up to 10 days to predict the western WD tracks and its associated precipitation. This is the we can see that the western disturbance tracks, and it is published by the Hand et al. 2017. This is our area of interest, which we can see marked in the red box. And the similar kind of tracks I replicated using ERA interim same data set. But after a little modification we have done with the consultation of Hand et al. Like we are able to reproduce the same similar tracks using similar algorithm. The methodology is like we have to use the compute the mean relative vorticity from 300 to 500 hectopascal and truncate to the spectral resolution of T63 and mask the negative values, and finally then find the local maxima at radius of 850 kilometer distance, and finally find the next movement of this relative vorticity at a distance of 1000 kilometer per 6 hour, and group them together as a tracking point. And finally, we have to apply some 3 filters, like a stub length shorter than 2 days are rejected, and tracks that do not pass through the Pakistan North India, like already I mentioned the previous slide, that red box, whatever not passing through, we are rejecting, and tracks whose genesis are east of their lysis and thus do not propagate eastward or rejected. Once all the filters is applied, then these tracks are capable to show the pathway of western disturbance. Like we are comparing with era of 5 reanalysis and NCM analysis. This is the western disturbance tracks from December 2019 and January 2020. We found there are 23 western disturbance tracks. Blues are showing from November to December 2019, blue lines, and red line shows that January 2020. Similarly, income analysis also predicting like similar amount, like 23 WD tracks able to find it. Like we can say almost like similar this red pattern in January, though it's a different number in the different months. Like it's a 15 here, 12, and here it's 8 and 11. That may occur because of the transition between from December to January. So with this confidence, now we are going to the further. Like here we are discussing about the medium range prediction. This is forecast prediction from first initial condition is based on 1st February. So it's from 1st February to 10 days analysis. Sorry, it's not prediction. This is analysis we are discussing now. Like 1st February to 10th February 2020, we are able to see that 3 different tracks in these 10 days. Like the blue one shows that from 1st February to 4th February, and the brown one shows from 3rd February to 10th February, and orange shows that this one shows from 6th February to 9th February. So we are focusing on this box, whatever the it is passing through from whatever the way, but it has to pass through this region, this border. That's what we are considering for the WD. And now we are coming to the forecast. Since we have NCMRWF is running for the ensemble forecast at a very high resolution, that's a 0.12 by 0.18 degree with 23 members. So these are all, it is having, this is based on initial condition based on 1st February 2020. It is able to predict 6 different tracks, which means 6 different initial time for the western disturbance occurrence. Like different colors shows that different time initiation with a different ensemble members. So we can see that at least this one single member able to predict this orange, and like similar track, this kind of track also coming here, but not exactly matching. It's analysis. This is a better forecast. Now we are connecting with the rainfall. This is the same as the previous figure. Just in the background, I added the GPM precipitation, observed precipitation, 24 hourly. Since it's the global region, I took the GPM. And this is center point around 3 to 3 degree square box I took for the showcasing the background as the GPM precipitation. Here we can see that at least this region, Odisha and coastal Andhra Pradesh, this region gives like more than 5 millimeter of rainfall. Now we are comparing with the NEBS, that's an ensemble forecast precipitation, which gives that it's a forecast only, forecast with greater than 90th percentile from the ensemble. It gives, though it gives very heavy, like more than 60 millimeter, but in observation it's more than like a 5 to 10 only. This region gives some heavy, since it's a 90th percentile. If you would have taken the mean, then it might have reduced. But I just wanted to show that possibility of this study. So we can make it as operationalized, and we can further study on this, how it is capable to capture the track as well as the associated precipitation. Mainly we are focusing on this Western Himalayas, which gives a more influenced by the western disturbance. Sometimes it's also influencing on the southwest monsoon and interacts with easterly and westerly. It makes more rainfall over the Uttarakhand, like in 2015 case. So we need to study further. So the key points are like income analysis. Western disturbance tracks are capable with the era of high during November and December.
of December and January of 2019 and 2020. Ensemble forecasts are able to predict the WT tracks, but further we need to filter out. And again, ensemble are able to forecast the precipitation associated with the WT tracks. The scope for the future work, like we have to study more statistical verification for the WT tracks using ensemble forecast and its associated analysis in terms of position and start date, end date of tracks, along with the associated precipitation. Also need to study using IMD GEFS, that also yet another 12 kilometer global real-time analysis, ensemble forecast model, along with the TIGI multimodal forecast also we are planning to study, and can be studied during all the month of year. Also apply the same algorithm for the extended range and subsequent seasonal prediction. These are the reference. Any questions or suggestions would be more helpful. Copy the same.
Oh, I think the question is from Umesh Prasad Verma from MIT University. He wants to know what basic principles are implied in the processing of Western disturbance calibration.
We use that relative vorticity from the winds we are computing relative vorticity from 300 to 500 hectopascal mean. Relative vorticity will explain the rotation in terms of cyclonic circulation, cyclonic kind of circulation. It gives the, it will tell if it is positive relative vorticity, it gives that cyclonic circulation. So we have taken the very mid-level of atmosphere relative vorticity, because at that altitude, mid-latitude, it brings the moisture from the Mediterranean Sea and the Caspian Sea. So that brings to the our Western Himalayas.
Okay, thank you. And there is one comment by Kiran Hunt. She says it's an excellent work. Are you planning to publish it anywhere?
Yes, so first we have to make it operationalized, and he is a co-author. We are using his code only. We are trying to make it for more multimodal, make it as a robust one. Ultimately, we have to publish. This is my PhD work.
Oh, wonderful, wonderful. Very good. I think this is the kind of thing we require in IMD, especially it's an operational forecasters need this kind of information. But luckily, I'll tell you, it's much easier to predict Western disturbances over Indian latitudes. And I think if you see season-wise forecast, winter season is much, much easier to predict. But yes, there is always a scope for further improvement. And I'm sure this kind of work, I mean, if carried over a longer period, will definitely help in the sub-seasonal scale forecast, which is very, very useful for the farming community, especially in the Northwest India. So I have a small question, because we have a time, one or two speakers are not there. So my question, your research was able to capture the recent event of extreme rainfall over Uttarakhand in October 2021?
So this year I couldn't study on WD because I was busy in many things, settled down in IMD, many training was there. But eventually, end of this year, I'll be studying using this year case study.
Okay, fine. Thank you. Thank you for the excellent talk. All the best for your future.
Thank you, sir.
So with this, we move to the next speaker. And the next speaker is Sisma Samuel. She's from ISRO. And she's going to talk about intra-seasonal variation of tropical deep convective clouds associated with sea surface temperatures. Over to Sisma.
Am I
You have
audible?
10 minutes, 9 minutes, or 8 minutes for the presentation and 2 minutes for the questions.
Sir, am I
Please try to
audible?
finish.
Hello.
Yes, you are audible. Go ahead.
Okay. Hope my presentation is visible.
Yes.
Okay. Good evening all. Today I'll be presenting on the intraseasonal variation of tropical deep convective cloud cores associated with sea surface temperatures. So this is the outline of my presentation, introduction, data used for the study and the methodologies adopted and followed by the results. So deep convective clouds over the tropics play a major role in transporting heat, moisture, and momentum from the lower to the upper troposphere. They modify the radiation balance by reflecting the incoming short wave and trapping the outgoing long wave radiation. They modify the hydrological cycle and thermal structure of the atmosphere. So these clouds can reach up to an altitude of up to 16, 17 kilometers, and they can reach up to the tropopause, and they modify the chemistry, thermal structure, and moisture content of the upper troposphere and UTLS region. So the development of clouds are associated mostly with a host of processes such as static energy, moisture content of the troposphere, atmospheric stability, atmospheric convergence, and vertical winds. So over this tropical ocean, all these parameters are substantially influenced by the sea surface temperature. So a sea surface temperature threshold of around 26 to 27 degrees Celsius are required for the conducive development of clouds, and the occurrence increases with the sea surface temperature up to 29.5 to 30 degrees Celsius and decreases for a further increase in sea surface temperature. So the reduction in convection is at higher temperatures are associated with the large scale subsidence followed by this nearby deep convection. So if we consider since sea surface temperature, since clouds act as a limiting factor for sea surface temperature, the simultaneous correlation between these two variables are required to single out the effect of one on another. From the literature, we are seeing that when sea surface temperature forces this atmospheric instability, then sea surface temperature leads to the clouds, and when this when the clouds form and they blocks things in the incoming shortwave radiations, then this atmospheric circulation variabilities drives this the sea surface temperature. That's clouds leads to this SST in this current. So these studies requires data with high temporal sampling. So the megatropics, which is an Indo-French mission, which is a low inclined orbits, provides better sampling over the tropics with minimum of 3 to 6 samplings over within the tropics. The low inclination orbit. Low inclination satellite TRMM provides the microwave SSTs, which are nearly transparent to clouds and provides measurements and cloudy conditions also. Along with these instruments, free tropospheric humidity derived from surface wind convergence from scatterometers and flux data from reanalysis on daily mean basis are estimated. So to identify deep convective cloud cores from the SAFIR, which is payload aboard megatropics, that measures in the water vapor peak absorption channel around 183, which has contributions from this entire tropospheric column. And the brightness temperature difference between these channels are used to identify these deep convective clouds. So using this methodology, deep convective cloud cores are identified over this entire tropics for the period 2011 to 18, and the pattern and the occurrence frequencies for each grid is calculated as pixels, which are identified as convective to total number of observations. So the right panel shows the variation of the occurrence of deep convective clouds associated with a simultaneous SST, and we can see that around 26.5 degrees Celsius is required, and above that the increase in occurrence of deep convective clouds with SST is significant about 26 and maximizes and decreases for a further increase in SST. So question arises that are SSTs important for convection beyond this upper threshold? So to study this simultaneous effect, daily mean SST from TRMM and daily mean deep convective cloud cores derived from megatropic SAFIR are identified and are selected over two regions with the sea surface temperature above a minimum threshold of maximum occurrence, and a 5-day running mean of both these data sets are obtained, and their anomaly is obtained by removing the seasonal mean. And the right panel shows the variation of both sea surface temperature and the occurrence of deep convective clouds on a daily mean basis over this Indian Ocean region. So we can see that the maximum occurrence is not simultaneous, but with a lag of several days. So in this context, the correlation of anomalies of SST to deep convective clouds is calculated 20 days before and after by analyzing this lead lag correlations. So over this Indian Ocean, we can see that a maximum correlation is obtained with a lag of 7 days over this Indian Ocean for deep convective cloud cores with respect to sea surface temperature. And over the Western Pacific Ocean, the lag is slightly higher to around 10 to 12 days. So the pattern follows for sea surface latent heat flux also. The lag was with respect to SST was found to be around 3 to 4 days. And for pre-tropospheric humidity almost follows the similar pattern as that of deep convective clouds. So this panel shows the combined lead lag correlation anomalies of parameters such as downwelling shortwave flux, surface latent heat flux, pre-tropospheric humidity, and deep convective cloud cores. It was found that the correlation was that for the downwelling shortwave radiation peaks first and resulting in a high SST followed by an increased surface latent heat flux and the occurrence of deep convective clouds and the maximum in pre-tropospheric humidity with a lag of around 7 days over this over the Indian Ocean region. Similar pattern is followed for this for the Western Pacific region, but with a lag of 12 days. So when we consider this seasonal lag, which were the response over this equatorial Indian Ocean was found to be faster compared to Western Pacific Ocean, which is mainly associated with the strong surface wind convergence over this region, which results in a faster response over the region. The response of SST to changes in response of atmosphere to changes in SST was faster over the equatorial Indian Ocean due to the strong surface wind convergence prevailing there. So now, if you take into account after this cloud formation, a simultaneous correlation between the downwelling shortwave flux and deep convective cloud cores was taken, and it was found that the correlation with the no lag was found to be highly negative, which is results in the strong reflection of the incoming downwelling shortwave radiations by the clouds. So it was found that basically it takes a time for this convection to respond to changes in SST. So if we take the simultaneous occurrence of deep convective cloud cores with SST, it was found that it reaches up to a maximum at a threshold and was found to be decreasing over both the regions, over the Indian Ocean and Western Pacific Ocean. However, if you remove the lag, which was obtained around 7 days or for each seasonal lag, accordingly each seasonal lag was remained, it was found that no such upper threshold for convection was obtained on the variation of occurrence we can see with respect to sea surface temperatures. So from the study, the conclusions are that for SST of about 26 to 27 degrees Celsius are required for the conducive development of deep convective cloud cores, and it maximizes around 30 and decreases for a further when we see the simultaneous variation. And the dependence of dependence of deep convective cloud cores to SST is not instantaneous, but with a lag of few days. And the occurrence, and along with that, the dependence also shows spatial variability, with equatorial Indian Ocean having a faster response compared to the West Pacific with a lag of around 7 and 12 days respectively. So if you consider the atmospheric parameters, the downwelling shortwave flux peak results in a higher SST followed by increased surface latent heat flux, pre-tropospheric humidity, and deep convective cloud score. And if we remove the corresponding response time of the deep convective clouds to SST, and we see the variation of occurrence of deep convective clouds to SST, it was found that such an upper threshold for maximum occurrence of convection was not found to exist. So the study found applications such as the ocean atmospheric interactions on sub-seasonal timescales are very significant in short-term weather predictions, and also helps in the validations of coupled models. So thank you. And these are the references.
Thank you very much,
Okay.
Sisma, for nicely explaining the role of tropical deep convective clouds and its relations with the sea surface temperatures. And definitely it will help in improving the weather forecast and prediction using the coupled models. So do you have any plans to join IMD in future?
I am doing PhD in ISRO. Currently, I am doing.
Okay. Fine. But I think it's a very good research, and especially the satellite meteorology, it has immensely contributed to weather forecasting. Earlier we never used to have information over mountains and over oceans, and what was happening we were not aware of. But with the satellite, you have all kind of information, even about air quality. I mean, you can go for, I mean, a number of applications. So excellent, I mean, excellent work being done at ISRO. And ultimately, it helps India Meteorological Department, the operational weather forecasters, in further, I mean, giving the accurate weather forecast and thereby helping the society. So I'm sure that all the basic research being done at ISRO will be useful in near future as well. Thank you. All the best.
Thank you,
All the
sir.
best. If there is any question, we will take up. No more question? Okay. No question. Thank you. Thank you very much. All the best. I'll just mention there was one question for the last speaker. Somebody had asked, do all the western disturbances give the precipitation? No. You have active weather WDs and passive WDs. It was only the active WDs which give you weather. That means rainfall, snowfall, or even hail. But the passive ones, just they come, there's a cloudiness, but there's no precipitation. So all the WDs do not give precipitation. With this, we move to, I think I'll say the last presentation of this session by Dr. Sudarshan Bera, as Sudesh and Sunil Kumar are not available. So Anshumal Raju is there. Okay, just a minute. If Anjumal is ready.
Yes, sir.
Yeah, fine. I think there was some internet problem at your end. So I think you can restart, but be brief. Okay.
Okay, sir. So should I start from the first slide?
Yeah, you please start.
Okay, sir. Sir, is it visible?
Yes.
Okay. Then my title is An Atmospheric Inverse Modeling Approach for Assessing CO2 and CH4 Fluxes over the Peninsular India using measurements from Tumba. CO2 and CH4 are two significant greenhouse gases present in the atmosphere. So these two gases are emitted to the atmosphere from both natural process and anthropogenic activities. There is a substantial increase in the emission of these gases after the Industrial Revolution, mainly because of anthropogenic activities. In this scenario, it is very essential to have an accurate estimate of the fluxes of these gases, and for a better understanding of the carbon budget and also for developing climate change mitigation policies. Here, inverse modeling is a technique that is used to optimally estimate the emission of these gases. Here, by definition, inverse modeling is the question of finding best representation of a required parameter by giving measurements made and also by giving prior information. In the cases of fluxes, inverse modeling is the process in which the fluxes are estimated from atmospheric mixing ratio measurements by considering transport and prior fluxes. In this study, the required parameters are prior fluxes, mixing ratio measurements, and transport model. Here, the prior CH4 fluxes includes anthropogenic emission, wetland emission, and emission from termites, wildfire, geological emission, and soil sink. And the prior CO2 fluxes includes fossil fuel fluxes, biosphere fluxes. And the CO2 and CH4 mixing ratio measurements are taken from the station Tumba during the period 2017 to 2018. And here the Lagrangian particle dispersion model FluxPart is used to get the transport component. The meteorological feeds from NSEP are used to drive the model. In the transport model simulations, the particles are released from the measurement location on the date of observations, and 7 days backward simulations are carried out. And there are two outputs from the transport model. That is, one is source-receptor relationship, which gives a measure of the change in mixing ratio at the receptor location due to fluxes from different sources. And the next one is the sensitivity to mixing ratio at those points in space and time where backward trajectories terminate. This will be used in the calculation of background mixing ratio. Then coming to the methodology, here we are using Bayesian statistics to do inversion. The advantages of using Bayesian statistics is that here it allows to combine the previous knowledge with the new knowledge. Here we have one cost function j of x. In order to get an optimal estimate of the posterior flux, we need to minimize the cost function. So after minimizing the cost function, we will have the optimal estimate, that is x cap. And this figure shows the schematic representation of the inversion process. Here the source receptor relationship obtained from the flux path model is multiplied with the prior fluxes and takes the sum. And this will give the enhancement in mixing ratio. By adding this enhancement with the background mixing ratio will give the model mixing ratio. Then in the inversion procedure, the difference between model mixing ratio and observation is minimized, and we will get the optimized fluxes, that is X cap. Then coming to the result, this is the result for CH4 inversion. In the first figure, the first plot shows the annual mean prior fluxes, that is the flux that we obtained from the inventories, and the second figure shows the posterior flux, that is the flux that we obtained after inversion, and the third plot shows the difference between posterior and prior fluxes. Here it is seen that there is an enhancement in CH4 fluxes after inversion, and this enhancement is mainly over the Tumba region, and the magnitude of enhancement is 1 order less than the prior fluxes. Here the second figure shows the modeled and measured CH4 mixing ratio. It's a time series plot. Here the red points shows the observation, and the blue points shows the modeled mixing ratio using prior fluxes, and the green one shows the same with the posterior fluxes. Here the modeled mixing ratio shows almost all the features of observation, and we calculated the RMSE value for prior and posterior concentration. Then after the inversion, that is the RMSE value for the posterior concentration is reduced compared to the prior one. Then this figure shows the seasonal pattern for posterior fluxes, that is for winter, pre-monsoon, monsoon, and post-monsoon. The first row shows the posterior fluxes, and the second row shows the difference between posterior and prior fluxes. Here the correction in flux is more during OND, and it is very less during JJS. Then in the case of CO2 inversion, the first figure shows prior fluxes and annual mean prior fluxes and posterior fluxes and the difference. Here also there is an enhancement in CO2 fluxes over the Tumba region. And the figure 5 shows the measured and modeled CO2 mixing ratio using both prior and posterior fluxes. And here also the RMSE value is reduced after inversion. Then this figure shows the seasonal pattern of posterior CO2 fluxes and their difference from prior fluxes. And here the correction is limited only to the Tumba region. And coming to the conclusion, in this study, we understood that after the inversion, there is an enhancement in CO2 and CH4 emissions from the peninsular India, and it is mainly over the Tumba region. And the CO2 mixing ratio obtained using posterior fluxes are more closer to the observation compared to the prior one. And here there is a reduction in RMSE value after inversion. This indicates the influence of observation in the optimization process. Thank you.
Thank you very much. Now we
Thank you,
can
sir.
take 1 or 2 questions if there are. Yeah, there is a question from again. Okay, no. Okay. I mean, what is the major cause of CO2, as you said, CO2 and methane? Methane, why you have observed? I mean, they're enhanced.
Compared to the prior, are you asking? Compared to the prior, we got an enhanced flux. Is that you are asking?
Yeah.
Sir, the prior, no, the prior flux misses lots of information. It is based on activity data and source information. So it is prone to have uncertainty. So in the inversion process, we are optimizing the fluxes by considering the information from that is present in the observation. So some
source of methane over that region.
Sorry, sir.
What is the major source of ozone?
Ozone.
Methane. Sorry.
So major source is anthropogenic emission for methane, and major natural source is wetland.
Wetlands. Okay. Major wetlands. Okay.
Sir.
Okay. Fine. Thank you.
Okay. Thank you, sir.
Good. So with this, we move to the last presentation of this session by Dr. Sudarshan Bera. He's from Indian Institute of Tropical Meteorology, and he's going to talk about properties of convective clouds in dry and wet environment of monsoon using large eddy simulation and observations. Is it okay? Are you available? Yes?
Yes,
Sudarshan?
yes, sir. Yes.
Okay, so you have 10 minutes, maybe 12 minutes you can take. We have enough time. So please go ahead.
Yes. Yeah. Can you see my screen?
Yes. Yes.
Okay. Okay. Good evening, all, and I thank session chair and organizer for giving me this opportunity to present my work. Title of my work is Properties of Convective Clouds in Dry and Wet Environment of Monsoon using Large Eddy Simulation and Observation. And I presently work at Indian Institute of Tropical Meteorology, IIT Pune, and I acknowledge that this work has been contributed by my two colleagues, Jaychandan and Dr. Tharapavakaran. So this is the kind of outline of my talk, and the present slide actually shows the motivation and objective for this work. So you can see on the upper plot, actually this shows the temporal variation of water vapor mixing ratio in the atmosphere up to 10 kilometer height. And this observation has been taken by radiation day at Mehboob Nagar near Hyderabad during CAIPEX 2011. And in lower panel, actually, you can see there is a, and when I made the mean profile of atmospheric potential temperature, water vapor mixing ratio and relative humidity, you can see there is very low variance associated with potential temperature. However, you can see very large variance with relative humidity and moisture. Moisture being an important weather and climate parameter as mentioned by previous speaker. So coming to the next slide, actually here I am showing radiation observation of water vapor mixing ratio and moistatic energy, which is denoted by MAC in the middle panel. And in the lower panel, you can see the daily mean rainfall, which is taken from IMD graded rainfall data. And upper two panel, actually, those are from radiation observation. And you can see that there are distinct regime. You can see the temporal variation starting from 1st August, and it is nearly 4-month observation up to mid-November. And you can see there are distinct differences at different phases during the time. And you can see there is a mid-level high moistatic energy when there is a continuous rainfall. So those this spell actually I'm mentioning as moist spell. You can say this is kind of active monsoon spell, where you have huge moistatic energy at the middle level of the atmosphere. And then there is a decrease in the middle level moistatic energy, and those spell actually associate with intermittent rain. There is infrequent rainfall on some days. And actually after that, there is no rainfall, almost no rainfall, and moistatic energy decreases in mid-level as well as in the lower level. And this spell I am considering as the post-monsoon, when there is withdrawal of the monsoon happened already. So based on these three spells during the observation, I am now looking the large-scale wind circulation associated with this observation location. You can see which is denoted by this black dot, which is near to Hyderabad. And during the moist spell, you can see very well-defined westerly wind associated with this. And this is the contour is for temperature. And during the dry spell, you can see the wind has changed a little bit, and there is a little bit northwesterly component, which is bringing some pollution. And in the lower panel, it is the cloud condensation liquid number concentration you can see. And the third one is associated with post-monsoon spell. And you can see the complete reversal of the wind. So wind is coming from northeast. So CCN actually, which is very low during the active spell, or you can see the moist spell of the monsoon, which is nearly 2 to 300 for 2% supersaturation. And then there is a continuous increase in the CCN and high CCN for the post-monsoon. So based on this observation, I have made some kind of scientific objective to study this work. So first objective is to investigate the cloud development in different moisture conditions of the monsoon, which is needed, and then investigate the controlling parameter of cloud development during different phases,
which is like kind of comparison with thermodynamic profile and CCN, and then comparison of model simulation with observation. So this is my model setup. Model I'm using WRF LES model with bulk microphysics scheme. Domain is around 30 by 30 kilometer in horizontal and 20 kilometer vertical domain. And sounding for model initialization, I'm using sounding for these three distinct phases: moist, dry, and post monsoon. Mean sounding from radiation day. And CCN cases, there are two CCN cases. One is 300 and one is 2000, which are representative for clean and polluted conditions. So this is kind of atmospheric profile for these three distinct spell: moist, dry, and post. You can see there is a rapid change in relative humidity in the with height. And when we look at potential temperature, you can see during the moist spell, actually there is moist spell and dry spell. They are having almost similar potential temperature in the upper atmosphere. However, for post monsoon, there is a cooling, and lower level also there is a little bit cooling associated with this post monsoon. So this is a model simulation from the WRF model, WRF LES model. And the first panel, it shows liquid water path for moist, dry, and post monsoon. You can see liquid water path is almost overlapping for moist and dry spell, dry case here, and up to 6th hour of the simulation. And then after onward, actually there is a decay in the dry spell simulation, because the boundary layer moisture already transported to upper atmosphere, so cloud started decaying. However, for the moist case, which is presented by the black line, you can see there is a continuous growth in the cloud. So cloud fraction also, you can see there is a continuous increase in the cloud fraction in the domain for intermediate for the dry spell, and very shallow cloud for the post monsoon case. So this is a vertical distribution of cloud fraction in the model domain for different time of the simulation. And you can see for moist case, domain is becoming almost fully cloudy at 6th hour of the simulation, and for dry spell it is kind of partially clouded, and for post monsoon it is relatively scattered cloud, which you can actually imagine in the reality. During the monsoon it is fully clouded, then during dry spell you will have the partial cloud, and during the post monsoon very few fraction of the cloud. So in this slide, I am showing vertical distribution of microphysical parameter, which is liquid water content denoted by QL, then Q ice, which is ice water content, and Q rain, which is rainwater content in the model cloud. So for moist case, you can see very deep cloud reaching maybe well up to 6 kilometers, you can say, and there is a huge amount of ice and as well as rainwater. So this monsoon, the moist monsoon cloud actually produce ice water as well as rainwater. However, during the dry case simulation, we have observed that it is producing good amount of liquid water. However, there is very little amount of ice, and there is no rainwater. So the clouds are actually not able to produce rain. And during post monsoon, being the clouds very shallow, there is no ice water as well as rainwater. So these are some of the dynamical parameters we need to understand how those clouds are developing during different spell of monsoon. So the left one is in cloud buoyancy, then vertical velocity in the middle, and the convective mass flux in the cloud core. You can see, so for buoyancy, you can notice there is a distinct differences. For the dry spell, where the mid-level atmosphere is relatively dry, you can see the buoyancy actually relatively higher. So because of higher buoyancy, the in-cloud updrafts is greater for this condition. However, during the moist monsoon condition, you will see the buoyancy is positive for a deeper atmosphere. However, the vertical velocity is intermediate, and for post monsoon, and there is almost no positive buoyancy. So clouds are being the forced convection in the atmosphere, and vertical velocity is quite low. So the convective mass flux being for the moist monsoon case, as it is having the very good amount of cloud fraction, so mass flux is highest, and intermediate for the dry spell, and very small for the post monsoon case. And I have to mention that this dash line here, I'm actually comparing the high CCN case, which is presented by this dash line, and low CCN case, which is the solid line. And you can see for the high CCN case, there is actually a negative effect. So buoyancy is little bit decreased,
and which is reflected in the dynamical vertical velocity. You can see there is a decrease in the abrupt speed as well as in the mass flux. So this is these are another type of microphysical distribution in the height. You can see first one is doublet number concentration, which is denoted by ND, then RM, which is mean doublet mean size, and then QL, which is liquid water content. And these are for three distinct cloud simulation, the black being the moist, red being the dry, and blue being the post. So you can see the doublet number concentration is the minimum for the moist case. You can imagine during the monsoon case, the doublet number concentration is relatively high, relatively low. And for dry case, it is kind of intermediate. And for post-monsoon, this is quite high. And I must mention that for this simulation, actually, I have started from the same initial CCN condition. However, the cloud dynamics, actually, it is altering the doublet number concentration in the cloud. So at the end of fourth out of the simulation, you can see there is a distinct differences in the number concentration. And same thing has been reflected in the mean radii of the cloud doublets. And where you can see the largest doublet, even it is reaching up to 12 micron, which is the threshold for raindrop formation in the cloud. So for the monsoon cloud, actually being able to produce the rainwater. However, for the dry case, which is presented by red line, you can see the doublet size is quite low, as the doublet number concentration is high, and for post monsoon, the doublet size is even lower. However,
please wrap up.
Liquid water content, you can see liquid water content is relatively higher for the dry monsoon case compared to the moist monsoon case. So I'm now this slide I'm trying to compare some of the model parameter, which is doublet number concentration, mean radii, and liquid water.
Please wrap up. Please wrap up. Finish it.
Sorry, sir.
Please, complete your talk. Now
okay,
time
sir.
is going to be over.
Okay. So these three are the representative cases for the moist, dry, and post-monsoon. So you can see the kind of comparison here. We can see that for dry case, which is 7th October, we can see the doublet number concentration is quite higher compared to the moist case. And similar type of trend we have seen in mean radii and liquid water content. So the simulation is kind of able to produce the actual observation. And with this, I conclude my talk. So cloud simulation with WRA values carried for different moisture condition of the monsoon season, and which are termed as moist, dry, and post-monsoon. Microphysical and dynamical cloud properties are studied. Moist monsoon clouds are deeper and exhibit higher fractional cloud cover and produce rain. Dry monsoon clouds have higher positive buoyancy and abrupt velocity below cloud top level. But at cloud top level, there is a significant negative buoyancy that restricted cloud growth further. And higher doublet number concentration and liquid water content found in dry monsoon clouds from both simulation and observation. So thank you, and I like on some, if any question, I will be happy to answer.
Thank you, Sudarshan. And there are two questions.
Yes,
we can take it. Then first one is again from Umesh Prasad Verma of MET Jaipur. Which sort of tools are employed for processing these fluxes variation?
Fluxes, you mean mass flux? Mass flux, you mean to say?
Okay. I don't know.
This is convective mass flux, and there is a equation for that. So which is product of cloud fraction multiplied by air density and vertical velocity. So this is the product which is termed as convective mass flux.
Okay. There is another question by Reshma. What cumulus parameterization was used in the simulation?
Here, this is WRF simulation. So this is bulk microphysics scheme. I have used WDM6 microphysics scheme in WRF model, which is publicly available.
Thank you very much, Sudarshan, for nicely answering the question and even for the talk. And I'm sure that this kind of research will definitely help in further improvement in forecasting. So with this, we wrap up this session. There was one lead talk and by Dr. Ajay Mohan from Abu Dhabi, and there was another invited talk by Dr. MCR Kalapur Reddy, and there were 4 oral presentations. And especially the The topics selected for this session were excellent. It had covered observation part and modeling and even the test bed and then the prediction aspects. But however, the test bed paper, I mean, was missed, but then it was very well covered topics, and it's very heartening to know that a lot of practical research using cutting edge technologies going on, and definitely it will lead to further improvements in operational weather forecast, and definitely it will contribute to the society. So with this, because I have already wrapped up even after every presentation, so I'm not going to repeat that. So I'm thankful to all the speakers for the excellent presentation, and I'm thankful to the Cochin University for organizing this Intromet, and especially this the topic of this session was very innovative, and I'm thankful to all of them, especially the team led by Dr. Mohan Kumarji and Abhilashji and their entire team. Congratulations and best wishes. Thank you very much for giving me this opportunity.
Thank you, Sri Anand Keshavma, for chairing this session. With this, we are ending our technical sessions today. But we have another important talk after around 6:30. Professor Annamani Memorial Public Lecture. So we will reassemble at 6:30 for the public lecture. Before that, there is one more announcement. Tomorrow's plenary session will start at 9 a.m. Okay, that's it. Thank you.
Thanks to organizers. Thank you very much.
ഇപ്പൊ സംസാരിക്കുന്നത് കേൾക്കാം. അപ്പൊ ഞാൻ ഇത് മ്യൂട്ട് ചെയ്താൽ ഞാൻ Sir, hello, sir. Can you hear?
I can hear you very well.
Okay, sir. Okay. Yeah. We'll wait for the chairman, Dr. Professor C.S. Bhatt is there. I will see him whether he is coming or not. So I think you are ready, and your presentation is also okay, sir. We'll try now. Sir, whether you are having a PPT or you can directly speak.
See, they're asking something.
No. Sir, can you hear?
I can hear you.
Whether you are presenting with the slides or without PPT. Presenting.
That I didn't hear properly.
Whether you are giving a presentation or you are talking only.
I'm talking with a script, but I'm not reading it.
Okay.
I have the points with me.
Okay.
And then I will continue to read it. And I have one picture to be projected.
Okay, sir.
not picture, a graph should to be projected. That also I have prepared.
You can just see, try it, sir, whether it is working or not. We can see that.
Oh, that's the picture I want to project.
Okay, okay. Sir. That is not seen now. You put share screen. Yes, 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 yes. Yes, it is coming, sir. Oh, this is our well-known picture, I know.
Yeah.
Yeah, I think I have seen from your UNE. I
Okay.
referred your thesis also earlier.
It is a classic picture.
Yeah, I know. Okay.
That's it.
Sir, Professor Bhatt is the chairman. He has got some other work earlier. Anyway, we will start at 6:30, exactly 6:30. Sir. Sir, yeah, is it audible, sir? Sir.
They asked you if it is
Good evening, Professor Goswami. Hello.
Good evening.
Good evening. Good evening. Yeah.
Good evening. Good to see you.
Yeah, we will 6:30. We will start.
I thought I'll try a little bit listen to.
No, I think your session is tomorrow.
Tomorrow.
You know it is. You are okay.
So how is it going? Everything?
Going very well. Yesterday we released the special postal cover. Yesterday we released all the 3 stalwarts.
Okay.
And the yesterday you attended the meeting. Yesterday we have got
yesterday inaugural I attended a little bit, but not after that.
Okay. Professor R. Anandakrishnan Memorial lecture JS has gone.
No, I think
it was delivered.
Evening I was busy with something else.
Yeah. And today I think.
Today also morning I attended one lecture, Brian Mapes lecture I attended.
Okay.
And after that I had to do something.
Okay. So today Professor Bhatt is the chairman. I think he has got some other work, I think PAC meeting or something, CRB meeting or something. Okay. I think he's told that sometimes he may be late. Yes, given. So 6:30 anyway we will start.
Okay, great. So you must be quite busy. We'll talk after this meeting is over. Sometime we'll chat.
Yeah, right.
Okay.
Anyway, we will.
Okay. So shall we begin?
Yeah, you can start, you can begin. You can introduce introduction. You can give.
Okay. Good evening to all. Welcome to the second day of Memorial Public Lecture. We will start with a brief introduction of Professor Anna Mani. Ms. Anna Mani was born on 23rd August 1918 in Pyramid in Kerala. She obtained her BSc Honours in 1939 from the Madras Presidency College. Her scientific career began with C.V. Raman at the Indian Institute of Science, Bangalore, where she studied the fluorescence and absorption patterns and spectra of diamonds. Mani was fond of laboratory work and liked instrumentation. In 1945, she went to the Imperial College, London, where she met Brunt. He directed her to the British Meteorological Office, where she spent the next 1 year at the Harrow Laboratories of the Instruments Division of the Met Office, studying the evolution of weather instruments. During this period, she visited several field observatories and manufacturers of meteorological instruments in England and Scotland to familiarize herself with exposure criteria for field instruments and observational practices. Later, she joined in India Meteorological Department. She made several contributions to meteorological instrumentation, conducted research and published numerous papers on solar radiation, atmospheric ozone and wind energy measurements. She retired as the Deputy Director General of the Indian Meteorological Department in 1976 and served as a visiting professor at the Raman Research Institute. She was associated with many scientific organizations such as the Indian National Science Academy, American Meteorological Society, International Solar Energy Society, World Meteorological Organization, the International Association for Meteorology and Atmospheric Physics, etc. She received the INSA K.R. Ramanathan Medal in 1987. In 1994, she suffered from a stroke and deceased on August 16, 2001 in Thiruvananthapuram. The lecture will be delivered by Dr. C.R. Sridharan sir. He is the retired Director General, India Meteorological Department and Instrumentation Designer, and he is currently residing in Mumbai. He served in IMD from 1962 to 1990 at various key positions. He was the leader of the second scientific expedition in Antarctica in 1985. During this expedition, a full-fledged surface observatory was set up at Antarctica with remote recording facilities for various atmospheric parameters at different levels. The development of ozone sonde for operational purposes is the significant contribution of Dr. C.R. Sridharan to the meteorological scientific community in India. Ms. Anna Mani was his mentor and supporter. As an ardent disciple, Dr. C.R. Sridharan would like to share his knowledge of Ms. Anna Mani's dedication, vision, commitment, and leadership with the youngsters. We are happy to invite Dr. C.R. Sridharan to narrate his inspiring and motivating incidents with Ms. Anna Mani in this public lecture. The session will be chaired by Professor G.S. Bhatt. He is a professor at the Center for Atmospheric and Oceanic Sciences of the Indian Institute of Science. He is well known for his studies on tropical convection, cloud physics and dynamics, atmospheric boundary layer, laboratory modeling of atmospheric phenomena, ocean atmospheric coupling, etc. He received Shanti Swarup Bhatnagar Award, J.C. Bose Fellowship, and mm, PRL Award. Thank you.
Professor Bhatt will join. He was busy with many meeting, and of course we will join later. Sir, we can start the lecture.
Good evening, everybody. I must, to begin with, thank Dr. Mohan Kumar for giving me this wonderful opportunity to speak about the life and work of Miss Anna Mani, with whom I had almost 2 decades of association. And when he called and told me that he would like me to present a talk on this occasion, I told him immediately that I considered it as a great honor you have bestowed on me. But it came as 30 years after I retired from the Indian Meteorological Department. This is the first time I was called upon to talk about somebody whom I greatly adored, admired, and think of so many times. She was my mentor, and today, what a beautiful scientific life I had looking back down the memory lane. I had such a wonderful experience, all that because she put me into the right line and then gave me all the opportunities to do whatever I thought was relevant and stood by me throughout the period. She was in Pune with me and later on in Delhi when she went on transfer, and finally, even after retirement, we were connected with what she was doing. And therefore, it is just like the story of my own life and career after I joined the Pune Met Office. So, coming to Miss Anna Mani, I already a brief summary of her life has been given here, but I shall continue to augment it. The childhood, going to the childhood of Miss Anna Mani. I have a little difficulty in calling her Anna because that was a privilege I found for very few people to call her by her first name. The only 2 people I have heard her calling Anna are Dr. Ramanathan and Dr. Vikram Sarabhai. Nobody else. So even to pronounce that name during my lecture, Anna name, I consider it too much liberty I'm taking with him. So kindly excuse me. I will mention her only as Miss Mani, as we used to do in the instruments division throughout her career in the instruments division. Coming back to Anna Mani's childhood, she was born in a very well-to-do Syrian Christian family, and her father was a civil engineer, and she was the 7th of 8 children. And right from the beginning, as she grew up, she was a voracious reader. That is the one thing which came out in her childhood. to the extent that she read all the Malayalam books available at home and in the library close by. And eventually, on her 8th birthday, her father presented her with 2 diamond earrings. She politely returned it to him and asked for instead Encyclopedia Britannica. So that was Anamani. What she wanted, she clearly expressed and got it. So her higher education, in the younger days, she started liking physics and finally decided that her career in life will be based on that love of physics. So what she did was when she was ready for the college, she finally went to Pachayappa's college and then took a degree in BSc honors in physics and chemistry. And then by the time it was 1940-45, after that degree, she came to Indian Institute of Science Research Division and worked in the Dr. C.V. Raman laboratory. And again, the diamond seems to be pursuing her wherever she went. So she was given work on understanding the fluorescence of ruby and diamond in the Raman Research Institute. And the 5 years she spent in IISc, she had written 5 independent papers in her own name. And at the end of that, 1945, she decided to go to London, initially with the intention of continuing her studies in physics, but in reality, she has ended up by studying meteorological instruments in London for 3 years, as already mentioned in the introduction. She spent a lot of time in understanding everything about meteorological instruments. So after 3 years of this intensive study in London, in 1948, she came back and she joined the Indian Meteorological Department. She joined in the Instruments Division at Pune, which was then being looked after by Mr. S.P. Venkateswaran, a stalwart in instrumentation. After she joined, her first job was to standardize all the meteorological instruments at that time being manufactured in the Instruments Division. Incidentally, the Instruments Division had a wonderful workshop at that time, which was the envy of all the engineering manufacturing companies in Pune. Why I'm saying that is the special precision machinery that was available was not available with anybody in the Pune engineering companies. So people from those companies used to take her permission and use her goodwill to carry out important work with high precision machinery, which was available in the Met Office Instruments division. So that was a unique thing, and almost 100 different types of big and small instruments were being manufactured at that time in the instruments division under S.P. Venkateswaran. Therefore, they had about 120 workers. The whole setup was such that raw materials go into the workshop and completely finished product comes out with the package and packing and everything. And side by side, the calibration facilities for the instruments that were being manufactured were also set up. We had a unique windmill, which could, in which every instrument, every anemometer that was manufactured there was calibrated. And we also had low temperature facilities with which instruments could be calibrated, and radio sounds particularly could be calibrated before launch those days. So the instruments which can be subjected to up to minus 80 degrees centigrade, that type of facilities were available in low temperature area also. The entire work excited Miss Mani, and she realized that all these instruments, nearly 100 in all, had to be standardized. So she set up a lab with the expert people to help her in all the final drawings and all that. I still remember Kalyankar, the chief of that laboratory, where all the specifications were drawn up for 100 and odd instruments. So once that job was completed, Miss Mani turned her attention to the setting up of radiation measurements throughout the India. That means a radiation network for the whole of India. That was her dream. Pyranometers, pyrheliometers, these were the these were the most important instruments you had to deploy. So this she started manufacturing, designing, testing, and then manufacturing. And in that arduous job, she was helped by Mr. Uman Chako. He was the man who spent a lot of time helping Miss Mani in that endeavor to create the first all Indian solar radiation measurement network. So after successfully designing that radiation network, she was in a mood to take up new job, and that was the time when Dr. Ramanathan, K.R. Ramanathan, at the time the director of Physical Research Laboratory, Ahmedabad, called her, and she went and met him. She was treating Professor Ramanathan like her father, so much affection she had for him. He had for her, and she had for him. So Professor Ramanathan told her that there is an urgent need for developing instruments which are capable of measuring the vertical distribution of ozone in the atmosphere. The importance was that the entire tropical region of the earth, India was the only country with the capability to manufacture, test it, and then fly regularly and collect the ozone information over the tropics. So we were the only country which had the capability to do that. So all this was impressed upon Miss Mani, and she naturally, whatever he asked her anytime, she took it very, very seriously. So she came and started the figuring out how to do that work. Who can create an ozone sonde? Finally, she was told that a professor in Wilson College, Bombay, is the student of Dr. Brewer in Cambridge. And Dr. Brewer is the man who designed the British ozone sonde. So she found out and then went and talked to Dr. Simmons. He was one of the lecturers in the Wilson College physics department, and told him, asked him whether he can help us make, design and manufacture and fly ozone sondes in India. She offered all the help required, workshop help, as well as the other financial help for buying the components and everything. Dr. Simmons was overjoyed at that invitation, and then he also got a student to work with him on the ozone sonde, making it as his PhD subject. So his name was Dharkar. So Simmons and Dharkar together started working on designing, manufacturing, testing, and flying the Indian ozone sonde. Those days, I was flying balloons from Visakhapatnam, where I was in charge of the Visakhapatnam Radio Sonde Observatory in the Andhra University campus. So I did not know all this was happening. But then suddenly I got a promotion as an assistant meteorologist from the UPSC. After 6 years of being a non-gazetted officer, I first time became a gazetted rank, and I was transferred. And Miss Mani had heard something about me and asked Dr. Mathur in Delhi to post me to Pune Instruments Division. That is how I went to Pune. By the time I reached Pune, Dr. Simmons had already started his instruments, and nearly 5 ozone sondes he designed with Dharkar in Bombay and brought to Pune and flew it with the help of the staff in the Pune Observatory. And then when I went there, that was the status quo. All that 5 instruments had some problem or other. They did not detect ozone in the atmosphere. So when I went there, I could also watch Dr. Simmons coming and then flying instruments. So his count, the number of instruments he flew, went up to 9. So these another 4 instruments were launched when I was also present there. But unfortunately, even those 4 did not give any ozone. In short, the instruments did not work properly at all. So this was the time I started wondering if at this stage, who will make the ozone sonde? It is not great technology or anything. You know the fundamentals. Air from the atmosphere is sucked in with a miniature pump and bubbled through potassium iodide solution. And every molecule the potassium iodide solution encounters, it will release an iodine atom. Now, if you put 2 electrodes in that solution, that atom, iodine atom, liberated by the ozone interaction, will send a small current through the electrodes. So you can get an external signal. So, what happened? Hello? Huh?
We can hear. Yeah.
Is it okay?
It's okay. Okay.
Okay.
It's fine.
Sorry. So this was the ozone sound was basically sucking in the atmospheric air into potassium iodide solution, and each ozone molecule that goes into the solution liberates an iodine atom which can send a current through the external circuit. This is the fundamental principle, but that current is extremely feeble. 2 or 3 microamperes current only you could get by in a live ozone sound. So, but that current is directly proportional to the number of molecules of ozone that has gone in. That is 1:1, very clear. So if you could amplify that current to a sufficient level and modulate a transmitter and get the signal down from the balloon, you have made an ozone sound. So that, in short, was the job at hand. So somehow I started getting interested in why Dr. Simmons was failing in in all his attempts. And I came to the conclusion that he was trying to do everything about the ozone sound, everything, including the ground equipment on which he wants to receive the signal, he will design. The transmitter he will design, amplifier he designs. Of course, that has to be done, no doubt about it. So like this, he had taken far too many complex situations involved in the instrument, and because of that, one thing or other used to fail in each flight, and that is why it was not successful. So I decided that I can try that. Why don't? So I started working after office hours and late into the night and design. And one by one, I attacked the problem. And finally, I got an amplifier stable enough to be sent in flight, which can amplify the current, and rest of the things were already available. We were flying balloons and getting signal from the balloons for ages now. So there's no point in trying to design a transmitter for that. And I only stopped with that the sensor amplifier, that's all. And amplify it to a level you can modulate a transmitter. So this I did, and I did quite a number of tests with each one of them, then put them together in the form of an ozone sound. So one day, after all these trials, I was coming out of the office at about 9:30 in the night and stepping down to the ground floor. In front of me, I found Miss Mani also after finishing his files, which was her favorite time for looking after the files was after the office hours. And then she was leaving the office, and then hearing my footsteps behind her, she turned around, and by the time we were outside on the ground, and she asked, "What are you doing here?" I said I was testing some subsystems. What subsystem? Subsystem for an ozone zone. What? She said, what? Ozone zone. I said, and suddenly something came to me. The sun, the moon was visible, and we were under a small mango tree talking to her. And I suddenly got an energy. I said, why don't you tell her what you have done? I said, ma'am, I think I can make the ozone sound. What? She said, what are you waiting for? My God. And then she was opening her vanity bag and taking out something. What was it? The key to the main building. Here it is. She almost threw it at me. Do it. Now, to make the long story short, within exactly 30 days of that challenge, we flew our very first ozone sonde on a September night, 3:30 in the night. 6 of us were there. 2 of my officer colleagues wanted to see how it is going. Then the other people were filling the balloon and all that. We launched the balloon with the very first ozone sonde. And believe it or not, that ozone sonde went up to the maximum possible height our available balloons could take it, and then burst and came down in a parachute. But the significant thing is that right from the launch, it started sending up the data on the ozone the instrument encountered. So after more than an hour flight, more than 1.5 hours flight, which included the balloon going up and then coming down in a parachute, we had the complete records of upward going and downward coming record. And we were extremely happy. All of us celebrated it by hugging each other and congratulating each other. And then I thought, okay, this is worth waking up Miss Mani. So she used to stay in the office quarters about 5 minutes away from there. So I called her. I had no qualms about that. I called her and said, Madam, we have ozone. What? Ozone? Can I come there? I said, come on, don't come there now. Tomorrow morning, I will come there and show you everything. Now you take rest. But it is a beautiful record. It is not only the record, the ozone as the balloon went up, but a replica of that was created as it was coming down. So it was a beautiful proof that what was recorded was not by fluke. So Miss Mani was absolutely excited. She said, come on, tomorrow we'll go and show it to Dr. Ramnathan. So we both together went by train to Physical Research Laboratory and showed the whole records to Ramnathan. And I still remember the beautiful expression in his face. He looked at Miss Mani and then said, very well, very well, very good, very good. And then he came to me and then patted me on my back. That was the great pat I will never, ever forget. So that was the day the Indian ozone sonde was born. We never stopped at that. We immediately started manufacturing more of this. And I must give due credit to Dr. Simmons, who taught me how to design, how to manufacture the plastic products involved in that in ozone sonde, how to design the dyes and injection molds and all that. She taught me. He taught me, and he was magnanimous. When finally he came and saw our product, he was magnanimous, and I had the privilege of supplying that data, ozone data drawn by our ozone sondes for his student for taking his PhD also, ultimately. So we returned the favor in that way. Anyway, we didn't, um, we started then a systematic project of manufacturing ozone, identified some very good mechanics for the job, and entire workshop was available for me for doing anything I wanted. That was the freedom she gave me. And with that, we started manufacturing, recruited a few more boys to test it, calibrate it, and help me with the other rituals before launching the balloon. And ultimately, in about a month's time, we started flying the ozone sonde both from Thiruvananthapuram and New Delhi. That becomes a latitude, longitude. So 3 stations were started within a month and then continued. Monthly flights from these stations continued. And Miss Mani immediately told the World Meteorological Organization, India has its own ozone sonde. Here are the samples, etc., data. And they were also very happy. And after about 40 soundings of the ozone sonde, the World Meteorological Organization wanted to see whether we are making a good ozone sonde which can stand the test of comparison, international comparison. So a comparison for ozone sondes from 5 countries were organized in Hohenpeisenberg, Germany, and India was invited to participate. And I'm very proud to tell you that Indian ozone sonde took part by flying 14 ozone sondes. I alone had to do that because they could not send 2 people. And I said, come on, I'll manage the whole thing myself. So there we launched the balloon and got absolute okay, and it compared very favorably with the ozone sondes from the rest of the world. So that's the way the ozone sonde was approved by the World Meteorological Organization also. And another 3 years later, a second similar ozone sonde comparison was carried out in Canada, Saskatchewan, Canada. So that there also we had a equal success with our ozone sondes. So the ozone data became established, and we had published all this data that was available. And once the ozone instrument was standardized, there was no problem in increasing the number of stations. And then we naturally became interested in the ozone distribution in the international level. The British had a Dobson spectrophotometer measuring total ozone from the Antarctic. It is not sending up any gadget, it's only a spectrophotometer, Dobson spectrophotometer, looking into a vertical column of air up to the top of the atmosphere and deciding on the number of ozone molecules a ray of light, sunlight, encounters when it enters from outside the atmosphere to inside the spectrophotometer. So now, depending on the number of molecules it encounters, the ultraviolet spectrum is modified. And from that, very precise measurements can be made of the total number of molecules the sunlight confronts when it is coming down into the instrument. So this is called a Dobson spectrophotometer. India already was operating 3 Dobson spectrophotometers, one from Kodaikanal, another from Pune, and a third from New Delhi. But that, mind you, only measures the total ozone, not the vertical distribution. Vertical distribution is a totally different thing. Now, what happened was the British had already installed one such Dobson spectrophotometer in Halley Bay in Antarctica and making regular observations for many, many years. And one of the British scientists analyzed that data for many years, suddenly found during September month for the past 10 years or so, there is a sudden unexplained decrease in the total ozone over Halley Bay. That was repeating year after year for about 7 to 10 days every September. This was happening. What was the reason? Nobody knew at that point in time that already the impurities we relentlessly throw out into the atmosphere in the developed part of the world, though it takes time, they finally find their destination in the Antarctic. And the Antarctic has the unique feature of the not being bright all the time. Half the year, the sunlight doesn't reach there. But when the sunlight manages to reach there, and that sunlight can interact with these chlorofluorocarbon dust from all the refrigerators and air conditioners the civilized man has thrown into the atmosphere without any consideration that it could be a dangerous thing for the ozone. So ultimately, there were scientists working in USA who had specialized in the interaction between ozone and chlorofluorocarbons, and they speculated that this could be the September ozone depletion, could be because of the chlorofluorocarbons reaching the atmosphere where the ozone layer is around the ozone layer, and then finally when the sun reaches there, and that reaches only during the southern transit. At that time only the sun has an access to the ozone and the CFCs that are going to create trouble. So those CFCs, under the influence of the new sun rays, interact with the ozone and deplete it, and the equations were reeled out how that happens, and they could be easily verified in the laboratory. So once that theory came, Professor Rowland and Molina, his student, they are the ones. Rowland and Molina Rowland got they got the Nobel Prize for just saying what I said, because it was a very, very important discovery and a very, very important solution they gave to the ozone distribution in the, destruction in the Antarctic. Incidentally, the newspapers used to call it ozone hole. So the public at large knows it by the name ozone hole. Ozone hole over Antarctica became the news of the day. And President Reagan was told by his scientific advisory committee that this is going to be very dangerous. And ultimately, if something happens, USA will be uh, found fault with by the international community for creating the possibility of sending all that unwanted CFCs into and throwing it out into the atmosphere. And then, because they are the most industrialized nation, so they are naturally the most important polluters also. So Reagan felt guilty about it and immediately ordered his entire scientific community to organize a grand research into Antarctica to find out what is the real cause of the ozone hole, why ozone is selectively getting destroyed during such and such a period. So once that thing came, and there was a solution. The American units tried their very best to measure ozone right from the ground and from helicopters, then rockets, then uh, balloons, and then even from the satellites. They made such a, and then from high-speed aircraft, almost every possible sort of platform they invoked and used it liberally, and then did one entire season of measurements in September, and then came out with their finding that what Rowland and Molina said was correct. This is on account of the CFCs which have come collected to such an extent that when the new sunlight came into the Antarctic during the transit of the sun to the south, and the very first rays reached the stratosphere where the ozone is maximum. This happens. But then it comes out after a few days. But however short the period was, this particular ozone hole and how it is created and our knowledge of that became a very big eye opener to us to make sure that we are on good this thing. We are on the right track. Therefore, the by this time, Miss Mani had already gone to Delhi from Pune and then retired, and then she went to uh, Bangalore to set up her own activities. And she joined the Raman Research Institute for 3 years and making a millimeter wave telescope, helping the RRI, Raman Research Institute, to make a millimeter telescope, and then continued her activities with the solar radiation, her pet topics, and she had one of the most important publications of her career, of her life, that is Solar Radiation of India, Solar Radiation over India, 1980, and then a handbook of solar radiation over India, 1981. And then a third publication, Wind Energy Data for India, 1983. These three publications from her stand out as one of her major contributions after retirement. And that is because this has become the Bible for people who wanted to start even industry based on solar radiation, as well as wind energy. So the three publications I mentioned are the most sought after publications of Miss Mani, the Bible for the people who want to design wind energy conversion, as well as solar energy conversion to electricity. So Miss Mani could continue her activity, and she had a lot of recognition in many areas. One of the awards that stand out is the INSA, Indian National Scientific Solar INSA K.R. Ramanathan Medal, 1987. And then finally, in 1994, she passed away, and she was with her sister Chellamma Chandi in Thiruvananthapuram. She was sick for about 6 years after the stroke she suffered, and she was finally cremated at the electric crematorium in Thiruvananthapuram. That is the short life and story of Miss Anna Mani. She has left an indelible impression through her work, through her passion, and through her absolute speciality of perfection. So the precision coupled with the perfection, she has left such an indelible impression on the entire scientific community. And that has brought her lots of recognition from all over the world. I do not want to repeat what was already repeated just before this. And that, in short, was the Miss Mani I knew, and whom I dare not call Miss Anna Mani. She was my mentor, and I would not have been sitting here today talking about her, but for the absolute kindness and the amount of freedom she gave me. I could walk into her room anytime. No time she has said, "Why did you come?" No. Immediately she knew that something I wanted to discuss with her. That was the thing. But she was equally strict with me also. I remember very well one incident. When my first baby was born, I went and told her I have got a girl. I would like to go and see her. Why? You have done your job. She said, We have work here. Don't go. My God, I saw that girl after 5 months. That was when I could get her permission to go and see my baby. So when my second girl and the third girl arrived, I learned the lesson. I never asked her that I want to go and meet. They came in quick succession. I never went and asked her for permission to go. I met all the three daughters after they were 5 months old. Not bad. So these are things that you have to take into account, but it's not done with any bad intention or to hurt you. But that was her yardstick of commitment to the work you are doing and a relative importance of the things that happen in your family. So I had learned a lot, and Miss Mani was a legend. As soon as she comes to the office in the morning, the dog comes ahead of her and it rushes in and announces that madam is on the way. So immediately the word of mouth, everybody is sitting back and starting work, and the whole workshop, everything. She had such a tremendous impact as a human being, as an officer, as a person for extremely high values and everything that goes with a great human being. So that was Miss Mani. One can never forget that. My wife can never forget that. We went to America because she had arranged for 3 years of our American trip after he retired through a professor in Utah State University. And one fine morning, we were staying in the quarters of the American students who were staying there. This is Utah State. I was, for 3 years, I was doing a job there. And suddenly, one fine morning, she lands up in Utah because the professor there, Professor Inge, was her friend. So she came to visit her and also to visit us. That was the human element in Miss Mani. She never ever ignored us, whether we were around or not. And my children were also the receivers of that affection. We were all very lucky that we had such a wonderful human being to take care of us throughout our life. So that's about what I have to say. If there is any question or anything, I can.
Yes, sir. I think this is a very good information about the dedication and committed work of Ms. Annamani and your association with her. Why? Because at that time we have seen that many stalwarts like Ms. Annamani, Professor Anandakrishnan, and P.R. Pisharadi, all people worked with the Sir C.V. Raman. They came to IMD. Why Sir Raman has to direct all these excellent people come to IMD at that time? Because they are working there in the spectroscopy. Then suddenly they are coming to the weather department. What is any reason for that? I think can you?
There were very few opportunities. I still remember when I passed my MSc with a first class, I had to be content with the best job I got was a demonstrator job in Chittoor College, 80 rupees per month. So I went to my father and mother and I said, Mom, I want to get out of Kerala. I don't want to. I'm going to apply left and right in UPSC. So UPSC gave me the opportunity to get a job in IMD. And then My father and mother both were crying. Why do you want to go out? I am here a professor in CMS college for the past so many years, and I want to retire here. What's wrong with me? He asked. I said, come on, Dad, you have 5 children, and I am only one. I am the only one who has the academics which can entitle me to a job outside Kerala. So let me go. But let me go. I want to go and see the world and report to you. I said, in English only we were talking. I want to see the world and come and report to you. Then mother was sitting there and said, come on, അവൻ പോട്ടെ അവന് പോണമെങ്കിൽ പോട്ടെ, let him go if he wants, she said in Malayalam to him. And then he said, okay, you are all career minded. I said, no, Dad, it's not career minded, it is opportunities. It's opportunity. I don't want to teach Newton's laws of motion throughout my life. That doesn't help me in any way whatsoever. I want to share the knowledge. And that was a great decision I made. I was not after money, but I was after opportunities. I was after opportunity. And today I am proud that I made that decision and stuck to it. Because that alone, that inquisitiveness alone will take you forward. Otherwise, you are just rotting. So I had, unfortunately, when I went for Hohenpeisenberg international comparisons for the first time and came back and wanted to tell my dad that this is what I experienced, he was no more. So I didn't have the privilege of telling him that I have seen the world and I have begun seeing the world. And then that was a journey which was unbelievable, taking me finally to the Antarctic. And the final, after spending 4 months on the Antarctic ice, bare ice, and sleeping there and enjoying every bit of it. And when I am returning, what is there? A big penguin. There are 2 types of penguins in Antarctica. One is Adelaide penguins, which are only 1 foot tall. The other one is 4 feet tall. A big penguin, the bigger one, that comes to bid me farewell. I was amazed. Throughout our 4-month stay, we had not seen the emperor penguin at all. And here it is. So one of my treasured photographs is the photograph with that the emperor penguin in the Antarctic. Our ship close by, you can also be seen in the picture. So that was an absolutely memorable experience. And sometimes, yes, my children also say, how can you go on such a very risky expedition, leaving us here? Then when I came back, we all sat together praying, and then they said, come on, Dad, you don't boast too much about your being very careful and all that. We were praying for you every day, huddled together, 3 of us and our mother, at least for 1 hour every day. Take care of my dad. Take care of our dad. And it was true, because I had 3 near encounters with death while I was in Antarctica. One was such a silly thing that I was in charge of the electrical supply in the Antarctic, and I had a running generator which I had to recharge every now and then for petrol. So I designed a sort of mechanism by which automatically the petrol will be pumped from one thing to the generator. And the petrol spilt all over the place, but I didn't notice it. And one day my boss, Dr. Reina, comes and sees this and says, what is this nonsense you have done, Dr. Sridharan? You are wearing dress which can create, if you rub, it will create sparks and you will blow up the whole thing, including yourself. So like that over active things also. Another was going in a scooter, Antarctic scooter, and suddenly you were going to fall down in a 40 feet gap that had developed the previous night. I virtually released the hand from the scooter. They are designed like that. The moment, then it stopped. Got out, put it on reverse, and came back. And the third one again was to do with careless people while balloon is being launched with the hydrogen from the ship. While we were returning, they will come smoking. And one guy almost blew up the whole ship. Along with that, I would have gone. So like this, there were many instances of near-death experience. But the most beautiful experience was that at the snow scooter, with the snow scooter, you go out at least 5-6 kilometers away from the tents and then go out, then you can't see the lights anywhere. And I got out from the tent, from the scooter, and I was watching the magnificent Antarctic sky and the totally unimaginable star cluster and the brightness and the shining and all that. And watching that, I became completely oblivious to my existence. How long I did that, I did not know. After some time, I had to hit myself to see whether I am alive or not. And then I hit my thighs and then I woke up. So when in one lecture, when I mentioned this, one of these guys got up and said, sir, that you had a samadhi, a brief samadhi, your soul was out of your body. Maybe, I don't know. So like that, it was a absolutely magnificent experience.
Yeah, it's a fantastic experience that you had in Antarctica. Okay, sir. Thank you very much for giving an excellent and enlightening talk.
Thank you so much. I have to thank you for everything, because this is my last opportunity and last chance to talk in public. I very much appreciate what you did, and it has been a very, very beautiful gesture from your side, and I shall never forget that. Thank you so much.
Yeah,
Everybody.
Yeah, the Indian Meteorological Society, I would like to again thank you, sir, for coming here and accepting our invitation and giving this enlightened talk. Thank you, sir. Thank you. Thank you all.
There is a small announcement. Tomorrow the session will start at 9 o'clock instead of 9:30.
Start with the first theory presentation of
The first plenary session will start with Dr. K. Ravichandran, M. Ravichandran. Thank you.
Who, Manish? Is Manish in the control room? You can close the meeting.
I'll just call him and ask him to close the meeting.
Close it, okay.
You can unmute.
Huh.
I'll hang up.